Oh, yeah, lightning. Don't you love watching electrical storms on a warm summer night? This is Dr. Nick for the Ecg Academy, and we're going to be talking about electricity. And you're wondering, well, what does this have to do with this? Well, this is the electricity that your heart is generating. And in order to read an electrocardiogram, you have to know something about electricity. So that's what this lesson is all about. This lesson has to do with the basic electrical concepts that you really need to know in order to be able to read an electrocardiogram. When we talk about basic electrical concepts, you really have to get all the way back to the atom. The atom, as you know, is the basic building block of matter. Everything is made of atoms, and the atom consists of a number of different parts. There's a central part that we call the nucleus, and the nucleus consists of a couple of subatomic particles. Those are the pieces that actually make up the atom. There are protons in the nucleus, and there are neutrons. Now, the difference is, and they're different colors here, the protons have a positive electrical charge, whereas the neutrons don't have any charge. Now, aside from the nucleus, there are these other particles that are flying around like moons around a planet, and these are known as electrons. Electrons are negatively charged, and they're flying around at different distances from the nucleus. Now, this is a picture of a carbon atom. Carbon is a very common compound, and it's in all of us. And in carbon, there happens to be 6 protons, and there are also 6 electrons. Most atoms in the normal state have an equal number of protons and electrons. And as a result, there's no electrical charge associated with a normal atom. Now, what is electricity? Well, most scientists think of electricity as the flow of electrons. And now, how can electrons flow if they're attached to this nucleus? Well, it turns out certain materials have electrons that are kind of loosely attached. And those electrons can be moved around, can be passed from one atom to another. These materials are known as metals. Well, we all know metals, right? Iron, copper, zinc, aluminum, those are all metals. Well, it turns out metals have a loosely connected electron. And if you have a bunch of atoms kind of all sort of like close to each other, then what happens is the electrons can jump from one atom to another to another. Imagine a wire, a copper wire, and what happens is if you shove a bunch of electrons in one end of the copper wire, it pushes all the electrons along the way, and other electrons come out the other end. And so the movement of electrons along this wire is known as electricity. Okay, that's the most basic concept of what electricity is. Well, we usually don't talk about electrons in humans because you don't have a lot of electrons passing through our bodies unless, of course, you actually get hit by lightning. But what we talk about are other charged particles. The charged particles in the body are known as ions. Now, what the heck is an ion? Well, let's talk about sodium. Sodium, otherwise abbreviated as Na in the chemical list of elements that we know as the periodic table. Sodium, here's a picture of sodium, has 11 protons in the middle of it. So there's 11 positive charges in the nucleus of sodium. And the electrons in a normal atom sort of group together in distances from the nucleus known as electron shells. As you can see that there is one electron in this outer shell of sodium that's sort of farthest away. And so it's really loosely attached to the whole atom itself. Now, there are 11 electrons, right? 11 negative charges. So normally a sodium atom has no charge. But what's the most common compound in our body is probably salt, or sodium chloride. Now, when sodium chloride is dissolved in water, such as is in our body, what happens is the sodium and the chloride tend to sort of split apart when they go into solution. And the chloride really, really loves to hang on to an extra electron, and the sodium loses this electron. As a result, there are instead of 11 electrons associated with it, there's only 10. So in a sodium ion, one electron is missing, and as a result, there's one extra proton. There's 11 protons, and there's only 10 electrons, and so the sodium ion is abbreviated Na with a positive charge, a plus sign, meaning that it's charged. So just like electrons moving along a wire, the movement of charged ions such as sodium, and another common ion that we see is potassium in the body, and that's just like sodium can lose an electron and become a potassium ion. The movement of these charged particles is what creates electrical currents within the body. And specifically with the heart muscle cell, if you imagine the cell as being surrounded by a membrane, a thin wall around the cell, what can happen is sodium can rush into the cell and make the inside of the cell more positive. That change in electrical charge, that movement of electrical ions or charged particles, is what generates electrical activity. So now in the next lesson, we're going to talk about how do we record these electrical signals, what's the basic electronic components in a circuit, and we're going to get into much more detail this whole electrical generation of signals in the heart, and later lessons having to do with the cardiovascular electrophysiology. So in the meantime, this is Dr. Nick, and I hope you enjoyed this lesson, and stay tuned for the next one. Hi, this is Dr. Nick from the Ecg Academy with Chapter 2 in this basic section of electricity. We're going to talk about electrical circuits, and don't worry, you don't need to know this whole ugly-looking circuitry thing, but I am going to talk about some basic ideas, some concepts in electrical circuitry, because, after all, electrocardiograms are recorded by electrical instruments, and you kind of have to know a little something about what you're dealing with. So let's get rid of this horrible thing, but between you and me, my favorite place to hang out when I was in high school was Radio Shack. Oh my God, my soldering iron was my best friend. Just kidding, but maybe not. Anyway, we're going to get rid of this circuit, and we're going to talk about movement of electrons. This is what electricity is. And, we sort of talked about a wire and electrons moving through a wire. So you can imagine all these electrical charges that are somehow able to move in a circuit. Well, what's going to push them, though? How can electrons move around in the circuit and there's nothing there that pushes them? Well, in a normal electrical circuit, we have some kind of push to the electrons, and that's what we use batteries for. So a battery is basically a source of electricity because what it does is it takes a chemical reaction and converts it into electrical energy that allows electrons to get pushed out the negative pole, and that provides the force to allow electrical currents to move. When we draw electrical circuits, we use special signs or symbols to represent different electrical components, and a battery is generally drawn with a symbol that looks like this. That just simply means a battery. Now, the smaller line is always represented. You can remember the small line looks like a minus sign, so that's the minus sign, and this is the plus end of the battery. And if you imagine a wire that leads in a circle, okay, this would be an example of an electric circuit, where the electrons are pushed out the negative end and they flow around in a circle and they return to the positive end. Okay, so that's the most basic kind of circuit. Of course, if you just simply connect a wire from one end of the battery to the other, the battery would just get used up. It would turn hot because heat is evolved in the chemical reaction. So let's think of something a little bit more interesting than just a wire. So we'll start with our battery, and then we'll let this electrical current do some work. Let's say we attach it to a light bulb. That's right. So a light bulb is generally drawn look like this because it kind of looks like the filament in a light bulb. You know how a light bulb looks like this? Well, that little loopy thing represents the filament. So now you connect the circuit, and so electrons flow out and they go through here, and as they reach the light bulb, it, lo and behold, causes the light bulb to glow. So a light bulb is something that does work, and generally things that do work create some kind of resistance for the electrical current. So you want to draw it as a different type of circuit, you can just draw this as a resistor, which is some kind of resistance. And then when we talk about the human body, sometimes we're applying electrical energy to the human body, and the body itself acts as a resistor. So here's a simple circuit. If we just let this current flow, of course, what will happen is the battery eventually will drain, and it's not very interesting. So there has to be some way to sort of stop and start the flow of electrical current, and that's what switches are for. So if I were to just sort of like interrupt this circuit here, now, of course, you have a break in the circuit. It's called an open circuit for those electricians out there. But we have to be able to close this circuit when we want to. So the electrical symbol for a switch has two little dots there and a line that represents sort of like a push button or a switch, so that this line can then close, if you want, to allow the circuit to flow. So when the switch is closed, then the electricity flows the way it's supposed to. And then when you open the circuit by opening this switch, then the circuit stops. That's all well and good, but how do we actually measure what's going on here? Well, there are a bunch of electrical components that can be used to monitor how much current is flowing. And if you imagine sort of some kind of a meter that would measure this electrical current, we would actually represent this as a circle with a V, and that's like a voltmeter, because the amount of force that the battery provides in moving the electrons around in a circuit is measured in volts. So a 9-volt battery has a lot more force than a 1.5-volt battery. So the voltage describes how rapidly these electrons are flowing around the circuit. And, voltmeters can look like anything from like a cute little meter, da-da-da-da-da, that the needle bounces when the voltage goes up. But when we're recording electrocardiograms, what we use is a kind of a voltmeter, but it's turned on its side. And instead of a needle, it uses a pen or some electronic equivalent of such, so that when the needle bounces back and forth with the variations of the voltage, it draws a line, and that gives us the squiggles that we commonly look at and reading a cardiogram. So imagine an ECG machine is kind of like a voltage meter, a voltimeter, or a means of displaying on paper, or of course on a screen if you're looking at a cardiac monitor, the variation in the voltage that's flowing around the circuit being, of course, the human body somehow. And we're going to talk about how electrical signals are in fact recorded, what the different kind of recording systems look like, and it'll give us a sort of a basis to understand the concept of an electrocardiographic lead and how we use different leads to determine what direction voltage is going in. Because when the heart beats, it produces voltage that actually has a direction. And we'll talk a lot more about that in the next video. Thanks for watching. Ow! I think I just got shocked. This is Dr. Nick from the Ecg Academy, and we're going to talk about how do we record electrical events in the body, because it's very important that you understand these kinds of recording systems in order to be able to figure out how ECG machines work and the kinds of things that can go wrong with them. And it's really a basic concept in learning to read an ECG. So we'll get rid of our little voltmeter here, and we'll start to talk about circuits again. Just like the last lesson, we're going to talk about basic circuitry. This is the last time we'll do this, so don't worry. We're going to get to the good stuff soon. Anyway, a regular circuit would consist of a battery. This would be the negative end of the battery, and the battery would provide the force that would push electrons through the circuit. You could have a switch here that would control when the electrical energy flows, and then the electrical symbol for a resistor would look like a little squiggle like that, and that would be your body or anything inside your body. And then we have to have a means of measuring the amount of electrical energy that's flowing through the circuit. So I put down sort of a symbol for a voltmeter of some sort. So nothing happens when the switch is open, but when you close the switch, current flows through the circuit, and the voltmeter will pick up this flow of energy. Okay? So that's fine if you're an electrical engineer. But when we're dealing with human electrical recording systems, we have to think in terms of bodies and how we record electrical events in the body. And if you've ever had an electrocardiogram done, you know that they use little sticky electrodes that go on your skin to pick up the electrical signals. So we need to understand how we're able to record electrical signals from the body. And there are generally two ways of recording electrical events on the surface of the skin or inside the body, in fact. And those two ways are unipolar recording systems and bipolar recording systems. And we'll talk about the differences. It's important to understand the concept in ECGs because it lets you figure out how to interpret the tracings. Imagine you have one of these sticky electrodes and this on your body someplace, and there's a wire, and that wire leads to a sort of a fancy voltmeter. And then the other end of the voltmeter, well, it's connected somewhere, and the electrical symbol for a ground is this, because that's just sort of handy. What with this unipolar recording system, and it's named that because there's one pole that's recording the electrical activity. What the system does is anytime the electrical voltage at this pole is different from the ground, then that records something. It registers on the voltmeter. So, a voltmeter would be normally looking like this somehow, but remember in electrocardiogram, we're going to turn this voltmeter on its side, and we're going to sort of use a pen to record the electrical activity on a piece of paper that happens to be moving. All right, that's sort of the basic concept here. But now imagine what happens if a bunch of positively charged ions, say sodium or whatever, some electrical event is traveling. It has to be traveling towards this recording system. Now, initially, you would not actually record any voltage difference, so you'd kind of have this flat line that's coming out of this recording system. But now what happens when this positive charge stuff kind of reaches this electrode is now the voltage is going to be different at this electrode versus down here at the ground. And what will happen is this voltmeter will register a positive deflection. And as the positive charges gradually move away, once they leave the area, then what will happen is the voltmeter will return to a zero state, and then these things can go on and move away. So that's how we're able to record signals using this kind of a unipolar recording system. Okay, so now what happens if instead of this sort of like generic ground, we use a second pole? We use another electrode, let's say over here, and we connect this electrode to the other end of the voltmeter. Okay, so you still have this voltmeter, but now what it's doing is recording the electrical difference between these two poles. So anytime one pole is different as far as the electrical charge surrounding it is concerned, then it's going to register on this voltmeter. So we have two poles. What do you think? That's right. This is called a bipolar recording system. Okay, so let's erase this whole thing. We still have our voltmeter, but now we have to bring our positive charges back. Okay, so now let's say our positive charges are back over here again. Right now, there's no electrical difference between these two poles, and so our voltmeter is just measuring 0 volts. So now the positive charges come by, and you have this electrical event that's sort of moving. And the first thing that's going to happen is it's going to hit that first pole. And so the first pole is now going to be more positive than the other pole. And so what happens is the signal is going to measure a positive deflection because you've got voltage in this one sign here. As the positive charges move forward, what can happen then is both poles receive the same signal, the positive energy here. And what happens is now the voltage will go back to 0. But as the positive charges continue to move, now the other pole will be more positive than the first one. And the sort of the polarity, as we say, reverses itself. The voltage now reads negative compared to the first event. And then, of course, you can imagine what's going to happen as this signal continues to pass. Now there's no voltage difference, and our signal returns to the 0-volt baseline. So you can see that bipolar recordings tend to be a little bit more complicated because now you're dealing with signals that may hit one pole and then the other first. Okay, now let's change things a little bit. Let's take our charges and imagine that they are traveling in a different direction. What do you think would happen if the charges are now traveling towards the two poles at the same time? As these charges reach the two poles at the same time, there's going to be no electrical difference between the two poles. So what do you think it's going to show? Well, maybe very little deflection, if any. And then as these charges continue to move, as long as both poles remain at the same voltage, then there's going to be very little signal that's recorded. And so in some ways, bipolar recording systems are more complicated because they are dependent on the direction of the electrical signal that's traveling. If it's traveling along the same direction as the poles are, you'll record a very large signal. But on the other hand, if it's traveling in this direction, which would be considered perpendicular or at a 90-degree angle to the recording bipole, since this is a bipolar recording system, we refer to these two electrodes as a bipole, then the signal will barely show up on the recording. And that allows us to, in some ways, determine the direction of the electrical signal as it's traveling. Okay, so ECGs, for the most part, are using bipolar recording systems. Each bipole that the ECG uses is known as a lead. And we're going to talk more about this because when you have a full-blown electrocardiogram, it's known as a 12-lead ECG. But you have to understand the idea behind a unipolar recording system with one pole. It's very sensitive to pick up electrical activity that comes in any direction. Bipolar recording systems are able to pick up electrical signals very well as long as the signals are traveling along the direction of the two poles. But if signals are traveling perpendicular to that recording pair or that bipole, it may have a hard time picking that up. All right, so that's the two different recording systems. And now that we've gone over this sort of basic electrical theory, we can start talking about the heart and about electrical events that occur within the heart and how we record them and how we interpret them from the ECG. Well, thanks for listening. This is Dr. Nick with the Ecg Academy. And please subscribe to my YouTube channel and check out ecgacademy.com. It's going to have a whole host of videos that will teach you how to become an ECG expert. And thanks for watching. Hi, this is Dr. Nick from the Ecg Academy with Section 3, Chapter 1. The next lesson here is called Cardiac Tissues and Electricity. We're going to talk about how the heart muscle cells generate electrical activity that we can pick up as the electrocardiogram. So you're looking at these numbers and thinking, what has he got up his sleeve? Well, if you've ever worked in a hospital and had to chart on a patient, you'll know that this is a shorthand that we use to record different concentrations of different electrolytes. And I'm going to come back to this because what I want to do first is talk about the human body. So here's the body, and the key here is that the human body is made up of organs, the heart, the lungs, the kidneys, and so forth. But each organ is made up of tissues, different kinds of tissues. And if you think about tissues in the body, there are, you've got bone, and you've got muscle, and you've got vascular or connective tissue, and you've got nerve cells and so forth. So different tissues kind of have different characteristics. And if we talk about the heart is an organ, but it's made up of different tissues, the valves and the coronary arteries, which are blood vessels, but the muscle is what we're going to deal with because it's the muscle that generates the electrical activity. Just like brain cells can generate electrical signals, all muscle cells generate electrical signals, and we're going to find out how. Now, we'll get rid of this, and we'll talk about the heart muscle. This is the heart muscle is unique. It's different from from the muscles in our arms and legs, and it's different from the muscle in the walls of our intestine. It's very characteristic. It has these branching cells that under the microscope have some very characteristic parts to them. So let's bring up some labels. A heart muscle cell is referred to as a myocyte, myo meaning muscle and cyte meaning cell. And the parts of this heart muscle cell or myocyte include this dark region here, which is the nucleus. The nucleus contains the DNA and basically runs the cell through little chemical messengers that come out the nucleus. The rest of this cell is known as the cytoplasm, and that's where other organelles are in there. And in particular, you've got these very thin lines that run through the cytoplasm. These are known as striations, and these are the special proteins that actually allow the heart muscle cell to contract. After all, muscles have to contract in order to do work. Now, what separates one heart muscle cell from another is this heavy line here, which is referred to as an intercalated disc. And the intercalated discs are like the thick junctions between cells. Think of the cell as not flat, but it's more like a tube. And you've got one heart muscle cell joins the other by this disc-like structure, which we'll talk about in later lessons. But the idea is that the signal that the heart uses to contract is passed from one cell to another, to another, to another, like a bucket brigade. All right, so well, let's get back to these numbers. I mean, what are these numbers referring to? The numbers actually, this is, get rid of the labels. This is known as an SMA-7 in the hospital jargon. It's a sort of a shorthand way of writing the electrolytes in the body. What are electrolytes? The concentrations of the ions that we find in the blood. If you take a sample of blood and you spin it down with a centrifuge, the cells of the blood settle at the bottom, and then you've got the clear portion of the blood, which we talk about is called plasma, or if you allow the blood to clot to take out the plasma proteins, is called serum. So the serum, if you throw it into a machine to measure the different ions in the serum, you come up with sodium, which is in the upper left-hand corner of the boxes. Potassium is written down here. This is chloride, and this is bicarb or CO2, or actually HCO2 minus, okay, if you want to be accurate. This is the blood sugar or glucose. And then you have kidney function here, which is blood urea, nitrogen, and creatinine. Okay, none of those are really important, except the point here is that in the serum, you have normally a very high concentration of sodium, which is why blood tastes a little salty. I know that sounds gross, but it's true. But look, the concentration of potassium is very, very low relative to the sodium, that is. There's very little potassium in the serum, but lots of concentration of sodium in the serum. Now, when you take a cell in the body, any cell, get rid of these numbers, and just draw a little cell here. A cell, of course, has a cell membrane around it. You remember this from basic biology. And inside is the cytoplasm. Well, if you sample the cytoplasm in here, you find very large concentrations of potassium and only little concentrations of sodium. It's like reversed, with lots of sodium on the outside of the cell and just a little bit of potassium on the inside. And so this difference in concentration is what allows the heart muscle cell to generate electrical activity, because what happens is these ions rush in and out of the cell, and the movement of these charged particles generates little tiny electrical signals. And we'll talk about the movement of these ions in and out of the cell in the next chapter when we talk about the cardiac action potential. Oh, that sounds exciting, like an action-adventure movie, huh? Stay tuned. Hi, this is Dr. Nick with the Ecg Academy, on to Section 3, Chapter 2, talking about cardiac action potentials. And okay, so this was a dirty trick to get your attention. But we're going to talk about membranes and permeability and diffusion. And you have to think about membranes as having little tiny holes in them that lets things pass across. Well, all right, let's get rid of that and get more serious. The whole idea of diffusion, just to get this in the open, is if you have a material, whether it be a gas or something like that, and it's in the air, it'll eventually kind of move in different directions until this gas or whatever it happens to be, the concentration of it is equal through the whole room. Just imagine if you open a can of paint on one side of the room, eventually you can smell it all through the room. And that's because the molecules of paint are diffusing through the air. Well, what if we put something in the way, okay? Not a wall, but something that lets some things through. And the best idea of an example is something called a membrane, which is a sheet of material that allows certain things to pass through. Think of cheesecloth, lets water through, but catches little pieces of the curds of cheese. But we're talking on the order of like molecules or even atoms that can pass through. So imagine a sort of a beaker, and dividing this beaker in half, you have this sheet of material, whether it be plastic or whatever, and this sheet of material is permeable, meaning that it allows things to pass through it, okay? And now you sort of pour water on both sides of this beaker so that the water is in contact with this. Now, if you put a substance on one side, let's say, for example, salt, sodium chloride, you put salt on one side, it dissolves, and then the sodium breaks apart from the chloride because, they tend to do that in solution when they mix it with water. Now, the sodium, and if this is just a plain old membrane, there's lots of different examples, but I'm not going to get too complex. What happens is you've got all this sodium on one side, and what happens is that the force of the concentration here actually pushes sodium through this membrane, and eventually the sodium winds up on this side. And the force is kind of proportional to the concentration. So the higher the concentration, the more force to push these sodium ions through the little tiny pores in this membrane. Eventually what happens is the sodium on both sides is equal, and then sort of there is still movement back and forth, but the net movement or the total movement doesn't change, but the sodium concentration stays the same on both sides. Okay, so that's the easiest idea of the simplest concept of diffusion across a membrane. But the thing is, when you talk about cells have a membrane around them. We call it the cell membrane. The cell membrane, however, is a very complex organ. It's not just a thin sheet of plastic. It's very got a lot of things going on in it. And in a later lesson in the advanced course, I'll talk about what actually makes up this membrane. But think of it as far as it's not really permeable, or it does not allow sodium and potassium ions and stuff to pass through very easily, except that there are special proteins floating in this membrane that act like pores or gates that can open and close and let substances through from outside to inside. Now, remember I told you that there's lots and lots of sodium outside, but just a little bit of sodium inside. Now, you would think that all this high concentration of sodium would apply this tremendous force and would push the sodium through the membrane until the concentration is equalized. And there's some of that going on, but the cell has special proteins that actually pump sodium against this concentration gradient, we call it, with the high concentration outside and the low on the inside. It actually uses energy to pump sodium out to maintain this high sodium on the outside and low sodium on the inside. And at the same time, potassium gets pumped into the cell so that it maintains this high concentration of potassium inside the cell. And the cell uses energy to do that. That's why you need energy to run and to jump, because all your muscles use energy to carry on their normal cellular activity. But think of this high concentration of sodium as being this potential for energy that could be delivered as the sodium rushes through. It's almost like setting the spring on a mousetrap and getting it ready to snap. Because what happens under the right circumstances is that these gates on the surface, there's a couple of other different kinds. There's a what's called a voltage dependent sodium gate that has a sort of two doors. And then there are potassium channels that are time dependent and also voltage dependent to some degree. And without getting too complicated, what happens under the right circumstances is that the sodium gate opens up, and sodium is able to rush into the cell down the concentration gradient. So it's easy for the sodium to rush in because there's very little inside and there's lots outside. So sodium rushes in, and what happens is all these positive ions make the inside of the cell more positive for a split second. But then just a moment later, these potassium channels open and the potassium rushes back out of the cell and sort of restores the normal voltage across this membrane. Well, how do we know this, and what does it look like? Well, experiments were done using a special kind of a thin tube, a glass tube, that was inserted through the cell membrane without killing the cell. And this tube was open, and it had some, material that allowed it to conduct electrical impulses. It had it was like a wire, but had liquid in here, like a salt bath. And then the end of this tube was connected to a voltmeter, and then the other end was on the outside of the cell. And so you could measure what the inside of the cell, what kind of voltage was in the inside compared with the outside. And it turned out that the inside of the normal heart muscle cells have a negative charge on the inside, that the inside is like got more electrons than protons. It's got more negative than it has positive. In fact, the voltage across this membrane is somewhere about 90 millivolts or 90 thousandths of a volt. And if we display that sort of on a screen, if this is sort of 0 volts, it lives down here around minus 90. That's sort of the resting membrane voltage gradient. We call it the potential, or transmembrane potential, about minus 90 millivolts. Okay, so now what happens when the cell is ready to fire? Okay, what usually tips the cell to firing is that the cell on the inside becomes a little bit more positive. It reaches a certain threshold voltage, we call it, which may be minus 80, something like that for certain cells. Once it reaches that threshold, suddenly these sodium gates open, and sodium is able to rush into the cell, making the inside of the cell much more positive than it was before. So this membrane gradient, this voltage across the membrane that we're measuring here with the voltmeter, it suddenly becomes positive. It goes up above 0, and it stays there for a split second until finally what happens is the potassium gates open up, and potassium rushes out of the cell, bringing all these positive ions out and restoring the normal resting gradient of about minus 90 millivolts. Okay, so this sequence of becoming more positive, sort of reversing the negative polarity across this membrane, we call it depolarization. Depolarization is the changing from negative to positive on the inside of the cell, and then a split second later, when potassium rushes out of the cell membrane becomes repolarized. So you have this. So repolarization is the sequence, is the part where the potassium rushes out and the normal resting membrane potential is restored. Now imagine what happens to the next cell over. So the next cell here is, remember, the cells are connected by this intercalated disc, and that disc is able to pass ions across. So now when this cell depolarizes and you have all these positive charges on the inside, the sodium rushes in, the positivity can pass from one cell to the other. And then what did I say? If the inside of the cell becomes more positive, this cell will reach its threshold, okay? If this is 0 millivolts, this cell reaches its threshold of minus 80 millivolts or whatever, and this cell fires. And then you get an action potential of the next cell, and the next cell, and the next cell. So that's how cells are able to pass the signal from one to another through this very complicated movement of ions in and out of the cell membrane. Now, it's this positivity that moving in space, this electrical positivity moving from one cell to another through the heart, that is what we're able to pick up and amplify and put on paper as the electrocardiogram. So on the next video, what we're going to do is talk about the heart muscle itself, and when those cells depolarize and repolarize, what does the signal look like when we pick it up from the surface? So thanks for watching. This is Dr. Nick from the Ecg Academy. Stay tuned for the next recording. Hi, this is Dr. Nick from the Ecg Academy, and we're going to be talking about the three-dimensional anatomy of the heart, because the ECG gives us a lot of information about different regions of the heart, and in order to understand these regions, one needs to have an appreciation of the three-dimensional anatomy. So the bottom chambers of the heart, which are the pumping chambers, we call the ventricles. There's a right ventricle and there's a left ventricle. And it turns out that the right ventricle is really more in the front of the heart because the heart's kind of twisted in the chest. So the right ventricle is on the front, the left ventricle is on the side and kind of behind the heart. The top chambers are known as the atria. There's an atrium on the right side, and there's a left atrium, but you can see part of it on the left side, but most of the left atrium is actually behind the heart. So now how does the blood flow through the heart? Well, the veins from the body, including the superior vena cava here and the inferior vena cava coming from the bottom part of the body, empty into the right atrium. The right atrium is a thin-walled sac on the top of the heart. The muscle here is very thin. And then the blood from the right atrium goes across a valve into the right ventricle. Now this is a tricuspid valve. It has 3 leaflets. And the valves in the heart keep the blood flowing in the proper direction. So when the ventricle contracts, the valve closes and keeps the blood from going backwards. Once the blood is in the right ventricle, it needs to get out somehow. And this is the pulmonic valve that actually leads to the pulmonary artery and then off to the lungs. The venous blood that returns to the right side of the heart needs to be reoxygenated. The blood goes up to the lungs and gets a fresh supply of oxygen, and then it returns to the left atrium through 4 pulmonary veins. There's 2 on the left side and 2 on the right side. These pulmonary veins empty into the left atrium, and the left atrium, like the right atrium, serves as a storage sac. It's connected to the left ventricle, which is the main pumping chamber of the heart, through the mitral valve, which has 2 leaflets. The left ventricle pumps to the whole rest of the body, and once the blood enters the left ventricle contracts and the blood has to get out to the body, and it does so through this valve in here, known as the aortic valve. The aortic valve has 3 leaflets and leads to the aorta, which is the main artery in the body. On this model is right here. So in terms of anatomical regions, let's get some orientation here. The heart hangs from the great vessels with the apex of the heart pointing off to the patient's left side. The right ventricle is in the front. We can see some right ventricular events, but we're mostly concerned with the left ventricle because that's where most heart attacks occur. The front part of the left ventricle is known as the anterior wall, and you can actually see an area of fat here, which is the anterior interventricular groove. It's the groove that separates the right ventricle from the left ventricle. And deep down inside that groove, you'll find the septum, which is the thick muscular wall that divides the 2 ventricles. So you have the septum, you have the anterior wall of the left ventricle, you have the apex, as I mentioned. The lateral wall of the left ventricle is off on the side here. The inferior wall of the left ventricle is on the bottom end, sort of against the diaphragm of the body. And the posterior wall, which is the back side of the heart, you have to twist the heart around to see the posterior wall of the left ventricle right here. Different coronary arteries supply blood to different regions of the heart. And when we look at the ECG for ideas of what coronary may be affected, we need to know what these anatomical regions are. So that's the discussion of the three-dimensional anatomy of the heart. I hope you enjoyed it. And stay tuned for the next video where I'll talk about the internal anatomy of the heart in more detail. And then I'll talk about the cardiac conduction system and where the ECG comes from and how we start to analyze it. Thanks for watching. Hey, this is Dr. Nick with the next chapter, which is on the cardiac conduction system. This is Section 3, Chapter 4 of the Ecg Academy. And I put these wires up here because, after all, there is an electrical system in the heart that controls the rhythm. Most people think in terms of plumbing when they talk about heart disease. Yeah, Uncle Joey had a clogged pipe, but the doctor had to do roto-rooter. Yeah, that's it. But in fact, the electrical system is what controls the rhythm. And since the tough part about reading an ECG is looking for arrhythmias, that's what we're going to talk about. Well, how do we get from the wires there to this thing with an ECG and the electrical circuits and whatnot? So that's what we're going to talk about in this chapter. So let's get rid of the wires and look at our this is a diagram of the heart. Let me just sort of fill things in a little bit for you. Remember, there's our right atrium on the top and an atrial septum that separates the two sides, and a left atrium, very thin-walled sacs on the top of the heart. The left ventricle is much thicker. The septum is the dividing wall between the two chambers of the heart, the two bottom chambers, and the right ventricle is much thinner because it only has to pump to the low-pressure circuit in the lungs. The muscle of the heart is connected to the fibrous skeleton of the heart, and people, sort of look twice and they say, what do you mean fibrous skeleton? What are you talking about? There are no bones in the heart. Well, if we think about the muscular system, and let's say here's a diagram of the bone in the leg, the upper leg and the lower leg, and you've got this muscle connected by tendons to the lower leg bone. Well, when the muscle contracts like this, the muscle shortens, and that pulls this tendon, which is attached to the bone, and that, by leverage, uses force to pull the bone up. So in order for the muscle to do some work, it has to be attached to something. It has to be attached to the bone. Well, of course, there are no bones in the heart, but there is a fibrous skeleton. And the fibrous skeleton actually is surrounds the heart and separates the top and bottom chambers. This fibrous skeleton is what the heart valves are connected to. There's the tricuspid valve on the right side of the heart, which separates the right atrium from the right ventricle, and then there's a mitral valve on the left side of the heart. Remember, the valves open and close to keep the blood flowing in the proper direction, and they're supposed to keep the blood from flowing backwards. So you've got the right atrium, you've got the left atrium, the right ventricle, and the left ventricle. So where's this electrical system that we've been talking about? Well, it all starts in the top of the right atrium. There's a clump of special heart muscle cells that generate electrical signals. These cells generate action potentials on a regular basis. They fire. They generate a little tiny electrical signal that is what initiates each normal heartbeat. This structure is known as the sinoatrial node, or some people just call it the sinus node. And the sinus node sets the pace of the heartbeat. So we refer to it as the natural pacemaker of the heart. The sinus node sends out electrical signals, and these signals spread rapidly across the top chambers of the heart. And that's what gets the top chambers to contract, this electrical signal that spreads from cell to cell across the top chambers, and that gets the atria to contract. Now, the signal has to get to the bottom chamber somehow, and there turns out to be an electrical connection in the middle part of the septum, the atrial septum, and we refer to this clump of cells, a special structure in the heart, as the atrioventricular node, or AV node. Now, the AV node is, again, a collection of specialized cells that can generate electrical signals, but these cells sort of receive this signal from the atria and they delay it for a split second. And then the AV nodal cells are connected to a network of very long heart muscle cells. They're branching cells, like branches of a tree. And these long cells are known as Purkinje fibers. That's Purkinje. Purkinje fibers, and they're bundled together in the septum with a thin bundle that kind of goes off to the right side, and we call this a bundle branch. Since it's on the right side, it's the right bundle branch. And there's a much thicker bundle of Purkinje fibers that then splits into several different major branches and then minor branches. And these very long branching specialized electrical cells basically conduct the electrical signal all through the bottom chamber. Now, this very large branch of Purkinje fibers that are bundled together is known as the left bundle branch. And this is the right bundle branch. And in the center of the heart, way up here where those two bundle branches come together, this is known as the main bundle of His. Now, women do not have a bundle of hers. It's just the bundle of His, named after the doctor who described it. So here you have the electrical system of the heart with the sinoatrial node, or otherwise known as the sinus node, and it has nothing to do with the sinuses in your head. It has to do with the embryology of the heart and how this whole part of the heart formed in the uterus. So you've got the sinus node that generates electrical signals. These signals travel across the atria to the AV node, where the signal gets delayed for a second and then passes down to the main bundle of His, the bundle branches, and then finally the Purkinje fibers out to the ventricular myocardium, or heart muscles. In the next video, we're going to see how this all works together to generate the electrocardiogram. Hi, this is Dr. Nick from the Ecg Academy with the final chapter in Section 3, talking about the electrical activity of the heart, and we're talking about the electrical events and where the ECG comes from. It's a review of the cardiac conduction system, but we're going to finally get to look at a real ECG signal and what it looks like and how to name some of the parts of the signal. So this animation was something I put together showing the electrical activity of the conduction system and how it relates to the heart function. But let's get rid of that because we want to take it one step at a time. So I'm going to shorten up, I'm going to close this up so that we can see this animation. It's an illustration of the heart with the right atrium and the left atrium, the two ventricles on the bottom, right side and left side. And the cardiac conduction system is drawn in dark blue. Remember that the sinus node is located in the top of the right atrium, and it borders right where the superior vena cava attaches to the right atrium. The sinus node here, as you can see, is drawn with little blue-like projections, little finger-like projections. In fact, the sinus node is a clump of cells, a large clump of cells, but it's a complex structure, and there are extensions of the sinus node that stretch out into the atrial muscle to sort of connect the sinus node with the atrium, and it helps conduct the very low-level signal that the sinus node generates. The sinus node, in fact, generates a signal that's so tiny that we really can't pick it up from the outside. If you do a cardiogram, you cannot see the sinus node function on a cardiogram. You can only indirectly get a sense of what it's doing. But if we put a wire into a vein and thread it up to do a recording of the inside of the heart, we actually can manage to record the sinus node, so we kind of know how it works. Well, the sinus node, as I said, is connected by these finger-like projections to the atrial myocardium, and if everything is working properly, what will happen is the atrial muscle will pick up that signal, and it will conduct the signal across both atria. Now, the atrial muscle is, as I talked about in the heart muscle cells, they're connected, and so you get this bucket brigade action that connects cell to cell to cell, and you get this rapid conduction or propagation of the electrical signal across both chambers. Are the two chambers connected? Well, behind the aorta, there is a bundle of muscle that is known as Bachmann's bundle. And it takes the electrical signal from the right side and kind of easily conducts it over to the left. So there is a connection behind there. Now, when we're doing a cardiogram, we can see the atrial activity because what shows up on the cardiogram is a bump. Now, it's a thin-walled structure, so it doesn't generate a lot of electricity. But we see a little bump, and that atrial activity is known as the P wave. Now, the signal gets into the AV node, which, as you recall, is the electrical connection between the two chambers. The AV node is another specialized structure that delays the signal for a split second, but then conducts it down into the Purkinje system, down the main bundle of His, the bundle branches, and the Purkinje fibers. Let me show you what that looks like. So those Purkinje fibers are designed to very rapidly conduct the signal down into the ventricles. Now, can we see this on the surface ECG? The answer is no. We don't really see AV node conduction, and we don't see Purkinje system conduction. We can record it from the inside. And if anyone's ever heard of a His bundle electrogram, that is a technique where we can put a wire into the heart and record the electrical activity of the AV node in the bundle of His directly. That's what electrophysiologists do when we're interested in studying the electrical system of the heart. But in the cardiogram, you don't see much of anything except the AV node delaying the signal for a split second. You do get kind of a flat section here that goes on for a split second. Now, when the Purkinje fibers fire, the ventricular myocardium gets the signal. And then the ventricular myocardium fires, you get action potentials, just millions and millions of them. And that's what generates the ECG signal from the ventricles. Now, when the ventricles fire, there's a very characteristic appearance to it. It looks like that. And most people would recognize that as the signal that the heart gives off when it beats. We refer to this as the QRS complex. And I'm going to get into more detail about how we name the QRS complex. But notice that these ventricular cells, they fire when that turns bright white, but then they reset themselves. There's depolarization, which is what the QRS complex represents. But then the heart muscle cells have to electrically reset themselves, and that's what repolarization is all about. If you remember the cardiac action potential, I know you don't want to think about it because it was kind of confusing, but the cardiac action potential, you have this sodium rushing into the cells, and that causes depolarization of the heart muscle cells. Remember, this in blue is just one single heart muscle cell, whereas the ECG here is the whole entire heart. But after a while, those cells repolarize. They go back to that negative on the inside kind of, you see, if we draw this as 0 millivolts and this is minus 90, I know I don't want to bring this up because it was a bad memory, but when they repolarize, you can pick that up, and it results in a bump that's referred to as the T wave. Okay, so let's get rid of this action potential. We don't need to spend too much time with that right now. We're really talking more about the QRS complex and the P and the T wave. Okay, so now what part of the QRS is the Q and the R and the S? It's very simple. The first downward deflection of the signal, the first downward deflection that occurs during ventricular depolarization is known as the Q wave. Following the Q wave, the next upward deflection is known as the R wave. Okay, and then if there happens to be another downward deflection following the R wave, then that is known as the S wave. Now, why is that so important that we name it that way? It turns out that not every QRS complex looks like that. When you start getting involved with reading 12-lead ECGs, you'll find that some QRS complexes look completely different. In fact, in some certain circumstances, the QRS complex, you may get a normal P wave, but the QRS complex may look like this. Now, wait a minute. Isn't that something? There's something wrong with that because it's upside down, isn't there? Well, no, it turns out it's not upside down, really, because sometimes the QRS is up and sometimes it's down. But how do we name this part of this QRS complex with this very strange kind of appearance? Well, what is the first upward deflection called? Remember, the first upward deflection is the R wave. So this is the R wave. There is no Q in this ECG recording. That's the R wave. And then you have an S wave here. Now, what if you had something that looks like this? Well, would this be any different? Actually not. In this case, what you have is there's no Q, okay, because there's no downward deflection that starts the QRS. Remember, the Q is the first downward deflection. You have an R wave, big tall one, and then you have an S wave. Well, what's the difference between this RS and this RS? It's only the ratio, the size difference between the R and the S wave. And some people use a kind of a shorthand to describe how the QRS appears. And in this QRS complex, you have a tall R and a little s. And some people will write it this way, as big R and little s. Whereas this QRS complex would be written as a lowercase r and a tall s. That's how we name these signals coming from the ventricle. So it can look all different. It can look crazy. These two signals have no Q wave. All right, let me draw another one. This one's going to look completely different. It has a P wave. But wait a minute. There's no upward deflection at all. So in this case, there's no R wave at all. But if there's no R wave, then what do you call the downward deflection? Is this a Q? It's the first downward deflection. Or is it an S wave? Well, it's not really an S wave because there's no R. And remember, S always follows R. So there's a special name for this kind of ECG signal, and it's actually known as a QS pattern. What else can we see? Well, it's not uncommon to see an EKG where there's no S wave. So this would be the Q wave, and there would be an R wave here, but no S. So it's a little Q, big R, and you would classify that to look like a lowercase q and a big R. You could also have a different kind of QR pattern. You can have a deep Q and a little r. And this would still be in keeping with our naming convention, but in this case, we'd use a capital Q and a small r. So you can see that the QRS can look different under different circumstances, but I want you to just learn the naming convention because it's important when we start to identify abnormal waves in the EKG. Well, there are a couple of other parts that I didn't talk about. First of all, this flat part that follows the P wave, that's sometimes known as the PR segment. And we can actually measure the PR interval, which is a time interval from the beginning of the P wave to the beginning of the QRS complex. So we'll measure this in subsequent lessons as the PR interval. Okay? Now there's a Q wave, there's an R and an S. We can measure the duration of the QRS complex. This point right here, where the QRS ends, is known as the J point. And the flat segment that follows the J point before the T wave starts is known as the ST segment. Okay? And ST segments are very important when we start to try to diagnose ischemia or infarction, because then what you'll sometimes see, for example, in ischemia, the ST segment will become depressed compared with the rest of the signal. So this is where the ST segment becomes important in diagnosing underlying heart muscle conditions. Finally, the last interval that I didn't mention is known as the QT interval, which is from the beginning of the Q wave to the end of the T wave. And I'm just mentioning this, but when we get into the chapter on the actual measuring these intervals, we'll be able to make certain diagnoses based on the measurements of these intervals that we'll do with a real ECG. So that's an overview of the electrical events of the heart and how these events relate to the cardiac conduction system, how we name the squiggles that come out of the heart when we record them on an electrocardiogram, and the different shapes and configurations that we may see when we start to analyze these ECGs. So that's it. Thanks for watching, and remember to log in to the ecgacademy.com for more videos from beginning to end, basic to advanced, so that I can help you become an ECG expert too. Hey, this is Dr. Nick for the Ecg Academy, and we're working on Section 4, and this is Chapter 1 having to do with ECG recording systems. How do we get that ECG on paper, and how do we get it to look its best? Electrodes have to be hooked up properly, and we're going to talk about the basics of electrode placement in this video. And what I did here is put together a little collage of different kinds of ECG machines. Well, some of the ECG machines you'll find in rolling carts that you'll see in a hospital. Here's another example of a rolling cart type of ECG machine. Some of them are smaller, little desktop models that you might find in a doctor's office. The desktop units come really small with a nice narrow strip that you can mount in a chart, or this kind of fancy one that'll give you a large thermal printout of the 12-lead ECG. And you got really tiny ones here with just a liquid crystal display. These others are ones you'll find in a hospital, like, for example, in a coronary care unit. Most of them have pressure waveforms on the screen as well. And here's an old-fashioned one with an old CRT-type display. But no matter what ECG machine you use, they basically are all doing the same thing, recording the electrical signals from the patient's skin. These are the electrical signals that the heart produces, and getting into interpreting them, first we want to see how they get on paper. So this is a kind of an ECG cable. Now what I'll do is show you some other cables that these are different ways of acquiring the ECG. You can see they are applied to the chest. Now this is the old-fashioned kind. These are like little suction cups. We used to use paste, which is a kind of a white cream that had a very low electrical resistance, so that we'd be able to pick up the electrical signal easily. These were a kind of clamp that went on the patient's wrists and ankles, and these suction cups would go on the chest for the precordial leads. Now, nowadays we have these stick-on electrodes, which are very simple and easy to use in a coronary care unit where the patient is going to be hooked up for a while. But if you're doing just a 12-lead ECG on paper, these disposable electrodes are really handy because you just stick them on the skin, and then you use a sort of a clip-on wire to attach each one. And we're going to show you in the next video exactly where these precordial leads go. But just to show you that different ECG systems, here's one that you might find in a coronary care unit or an emergency room with just 3 electrodes. That only gives you a limited number of electrical views. Here's one with 5 electrodes, a little bit better, and then here's a full-blown 10 electrode system, which would be used to acquire a 12-lead electrocardiogram. How do they get attached? Well, you have to think about the person that you're recording. And let's just say you're facing this person here, and that person has, kind of smile on his face because you're going to help him out by doing his ECG. So this is a good discussion for not only the ECG technicians, but nurses. How do we know where to put the ECG electrodes and which color goes where? Well, it's really important to remember this. White, black, green, red. Okay, well, how do you remember it? I always like to think of it this way. Imagine the person is sitting behind the wheel of a car, okay? Now, when he's sitting behind the wheel of a car, his right foot is going to be over the accelerator pedal. And think green, go, right? That's accelerator goes on the right leg. Now, his left foot will be over the brake pedal. So red makes sense, doesn't it? You'd want to put the red electrode on the left leg. Now, if he's driving a car in the United States, at least, the steering wheel is on this side of the car, and so his left arm is going to be sticking out the window, and it's going to get suntanned. Aha! That's how you remember that the black goes on the left arm, and then, of course, the white one goes on the right arm because this arm will not be suntanned. So that's a real quick, easy way to remember what leads go on what limb. And of course, this is useful in the coronary care unit, but also on the ECG machines. They'll generally be color-coded, white, black, green, and red. Some of the old-fashioned systems may use yellow for the right arm. But anyway, in the next video, we're going to talk about the chest leads and where do those electrodes go exactly, because that's really important. If you don't put them on in the right spot, the ECG won't look right. So see you in the next video, and thanks for watching the Ecg Academy. Hey, this is Dr. Nick from the Ecg Academy, and we're going to go over the anatomy of the chest, because in order to put the ECG electrodes in the proper place, you have to be familiar with the anatomy. I've seen a lot of people put the ECG leads in the wrong place, the electrodes go in the wrong spot, and then it makes the ECG look abnormal when it isn't. So let's go over the anatomy of the chest. On the front of the chest wall, of course, we have the breastbone, which is called the sternum, and it connects with the clavicles, which are the collarbones. Now, the sternum has three parts to it. The top flat part, which is a little bit wider, is called the manubrium. The middle part of the sternum is called the body. And at the very tip, there's a small part that juts downwards called the xiphoid process. Now, between the body of the sternum and the manubrium, there forms an angle. It's called the sternal angle. It's a ridge. If you run your finger along the sternum, you can feel this ridge. Now, this ridge, if you follow it to the left and the right, it actually connects with the second rib. And that's important because below the second rib is the second intercostal space. Now, where do the ECG electrodes have to go in? The fourth intercostal space. So find the sternal angle, find the second rib, move down slightly, and you feel that little hole there. That's the second intercostal space. And then run over the third rib, the third intercostal space, the fourth rib, and then the fourth intercostal space. So if you find the fourth intercostal space, that's where V1 and V2 go. Now V1 should go on the right side of the sternum, where the sternum meets the rib, right in that fourth intercostal space, right about here. And V2 needs to go on the left sternal border at that fourth intercostal space. Okay? So that's very important. The next place to look for is V4, because V3 is going to be midway between V2 and V4. V4 is supposed to be in the mid-clavicular line. So find the clavicle, find the middle of the clavicle, and run down. And it's supposed to be not in the fourth intercostal space, but the fifth intercostal space. So V4 goes right here. Now V3 will wind up going halfway between V2 and V4. And then V5, if you follow this space out, go more or less horizontally, the anterior axillary line, which is the furthest to the front of the side of the chest wall, that's where V5 should go, the anterior axillary line. And then V6 goes in the mid-axillary line, which is all the way on the side. Don't be afraid to go just underneath the armpit there, because that's where it belongs. And if you put your electrodes in this position, your V leads, your precordial leads, will come out looking properly. Now what about the arms? Well, the arms are easy. You want one on each arm. And you'll see some people in the ICU, they'll put their leads on the chest wall, but that's usually not the best place to put it. You should, if you're doing a formal 12 lead, you should put it on the arm. And then the leg electrode should go on the legs, somewhere down on the calves or the thighs. Depends on what kind of access you have to the patient. And so that's where they belong. And I'm going to show you some pictures of where not to put them in just a moment. Hey, this is Dr. Nick with the Ecg Academy with a quick Chapter 3 in Section 4, Lead Misplacement. So what happens if your leads aren't in the right spot? This is a photograph I found in my files. And it's a fellow who's undergoing a stress test. You can see he's got a blood pressure cuff over here, and he has an intravenous in his arm. They're going to be injecting a nuclear material so they can get some images of his heart after he exercises. And he looks like he's all ready to go. But you notice a couple of things wrong with the picture. First of all, his limb leads are on the chest. This is right arm and left arm. Normally they should go on the arms, but of course when someone's running, you may wind up with a lot of artifacts. So that's why I mentioned that some people will put the limb leads on the arms, and here the leg leads are over here on the chest wall. But look at the precordial leads. Now remember what we talked about. You'd have V1 here and V2 here. They're a little far from the midline. I would say the sternal edge is a little bit closer to the midline. But then look where they put V3. That's a crazy position. In fact, the V3 is closer to the midline than V2 is. What they should have done was find the midclavicular line and put V4 in the fifth intercostal space and put V3 over here. And then V5 would be here, and V6 would be in the mid-axillary line. So whatever EKG they get is not going to be accurate. Now, of course, when you're doing stress tests, you're looking more for changes from the baseline. You kind of look at your ST segments, and if they're isoelectric at baseline, and then when you have a stress test, you get ST depression. Well, that tells you that ischemia is present. And we're going to go over that in future lessons. But the point is they're looking for a change. And so they'll get away with this. They'll get away with not putting the precordial leads in the proper position. But for the sake of your education, just keep in mind where those leads are supposed to go. And don't make this mistake of putting them where someone else may have told you to put them, or wherever you feel like it. Okay, and in the next chapter, we're going to show, well, what can go wrong with ECG systems, and how do you make sure what you're looking at is real? Well, this is Dr. Nick, and thanks for watching the Ecg Academy. Hey, this is Dr. Nick with the Ecg Academy. Going to finish up Section 4 with Chapter 4, Limitations of ECG Systems. Now, what does that mean? Well, we're going to talk about what can go wrong when you're recording an ECG and how to make sure that what you're looking at is real. And so here's the first 12 lead that I'm going to show you in this course. Hot off the presses from a brand new ECG machine, and it looks really pretty, doesn't it? There are nice clean signals, and what you're seeing is black ink printed on paper that has this printed pink grid. And just to get you oriented, you've got your limb leads, 1, 2, and 3, AVR, AVL, AVF, and then your chest leads or your precordial leads, V1 through V6. Now, what you have to understand is that these lines are all running simultaneously. So this beat is the same as this beat, as the same as this beat. And so sometimes what happens is you see when this line changes from V3 over to V6, you can sometimes get some squiggles or weird signals that you're not sure what to make of. But that's why the last line, the fourth line, is known as a rhythm strip. It's just one lead that runs all through the entire strip, and we call it a rhythm strip, so you can see very clearly what the rhythm is. Now, this looks great. It's easy to interpret and very straightforward. We're going to get into actually how to interpret it in future chapters, but I want to show you a different kind of tracing. Now, this is a rhythm strip that I got from my files, and you can see written on here, urgent broadcast called, because what happened is it says the patient had about 7 seconds of asystole, and that means flatline, no rhythm. And you can actually see that here. There's a QRS complex and then a T wave, and then nothing until way over here where there's a QRS complex. And it looks like the heart stopped for all this while, and you think, oh my goodness. Well, here's what you need to know. This size of this ECG is on the order of 1,000th of a volt. It's tiny, tiny, tiny. And what the ECG machine is trying to do is pick up these little tiny electrical signals from the skin. But it can pick up other electrical signals as well, from the skin or from the muscle or from just the patient moving around or breathing. And what you can see, for example, from here to here, is this sort of very fine undulation, this kind of like little random noisy signal, which we call the baseline. The baseline should have those little tiny fluctuations. But here you see that baseline is not present. And if you glance to the left here, it almost seems like someone took a ruler and a pen and just drew a straight line from here to here. It doesn't move. You don't have those little tiny fluctuations. And so what happened is that the wire got disconnected. So this patient was on the monitor. Somehow the leads got disconnected. The electrodes came loose. And that's what made it appear that the heart stopped, but it really didn't. So whenever you see this kind of flat line appearance where it looked like somebody drew that line with a ruler, you should really think that perhaps it's not real. The space in between beats really should look like this. Now I'll show you another example of that. Now this was a patient who was on the monitor, and they were. I was asked to see the patient because it seemed like their heartbeat was really slow. But one thing you notice, this kind of looks like a T wave, and maybe there's a QRS complex in here somewhere, but it sure looks really bizarre. And then there's a little signal, and then from here to here, again, it looks like someone took a ruler and just drew a straight line. And so, and then suddenly you've got this drop. See that how it suddenly drops? That's almost like where the wire makes a connection, and the real electrical signal suddenly appears to the circuits of the ECG machine. So you'll see this sudden drop. It could go up or it could go down. When you'll suddenly make the connection, the circuit will be closed, and then you'll record this sort of usual normal baseline artifact, this little tiny squiggle here. And then, I don't know, there may be some noise in this, so this doesn't look like a good signal. But from here to here, again, you see someone took a ruler and drew it. And this is a kind of a make and break artifact. Artifact is the word I like to use when it's not real. The heart isn't really doing this. It's just that the electrical circuitry is showing you something that doesn't really exist. I'm going to give you another example here. This is the last one. This is from my files. And here you've got 3 leads. They're kind of in a funny order, 2 and then 1 and then 3. But they're all running simultaneously, as they usually will. And you can clearly see these QRS complexes marching through on all 3 lines. But I want you to first notice that in between these QRS complexes, there's a lot of artifact in the baseline, what I like to call high-frequency artifact. It's just junk. It's just electrical noise that's present throughout this lead. But the other thing I want you to notice that aside from high-frequency noise, there are also low-frequency signals. These undulations here, that's not really the patient. That's something else. There's something moving. Either the patient is moving, but as you notice, as time goes on, these low frequency undulations get larger and larger. And when you look at this, if you were to just look at this by itself, you'd say, oh my goodness, call the coronary care unit, call a code. The patient's having some horrible arrhythmia. It looks like ventricular tachycardia. But look what's happening in this lead. See, the QRSs are marching on through. So in fact, the heart is not in an arrhythmia. It's just beating normally. And what you're seeing here is a low-frequency artifact. It's just an electrical noise superimposed on the EKG. You can actually see the QRS complex is there and here. It's still present. But you've got a much larger electrical signal being generated by something outside of the body, something coming from in between the heart and the ECG system is messing this up. And you have to make sure that you look at every EKG with a grain of salt. Always in the back of your mind have the question, is it real or is it artifact? And if you do that, you won't make the mistake of misinterpreting electrical noise as something real. So I hope you enjoyed this video. Don't forget, you can log on to ecgacademy.com to watch all the videos from beginning to advanced, as well as subscribe to the weekly Chalk Talks that'll get you used to reading more complicated tracings. This is Dr. Nick from the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to be talking about the ECG leads in this first chapter of Section 5. What is a lead? And what does it mean when you change leads? We're going to talk about the basics because when you look at a 12-lead ECG, you see these lead 1 and lead 2, and on monitors there may be a switch that you can change which lead the monitor is looking at, and what lead you pick is going to have an effect on the way the ECG looks. In the intermediate section of the Ecg Academy, we're going to be talking about a more advanced concept of the ECG axis. And that involves some calculations, and the axis deviation is a term used to describe an abnormal ECG axis that we'll get into as far as the physiologic disturbances that can result in axis deviation. But again, that's an intermediate concept, and we're not going to be talking about axis, but I do want to introduce you to the concept of the lead. Now, what is a lead? Well, okay, let's just talk about the recording systems that we had discussed in the past. Remember, ECG basically amounts to a voltmeter, and there are electrodes that are monitoring voltage in a bipolar recording system, that is. And when you have an electrical signal that's traveling in space, what happens is if it reaches one pole first, the voltmeter will measure a signal that amounts to the fact that the one pole is more positive than the other. And then as the signals pass, as a signal passes to the other pole, you may see a change in the polarity. And then as the signal continues to move, the recording will go back to the baseline state. But remember, if the electrical signal is traveling in the perpendicular direction, so for example, if it starts up here, let's erase this, and if it reaches both poles at the same time, then there's no difference between the two poles, and the electrical signal that's drawn may be very small or even non-existent as this wave of depolarization travels perpendicular to the plane of the electrodes. Okay, we remember this concept from one of the early chapters. All right, so what are we talking about in a person when we're looking at the electrocardiogram coming off of an ECG system? Well, remember we have different color codes. The black is the left arm, white is the right arm, green is the right leg, and red is the left leg. Well, in the early days of electrocardiography, they used a bipolar recording system to look at the electrical signal that's traveling between the right arm and the left arm. Now, just as a review, I want to remind you of what direction the electrical signals in the heart travel. Remember that the atrial signal starts in the high right atrium, and it travels down and to the left, and likewise the signal that goes through the ventricle travels down the septum and towards the apex, down and to the left. The normal electrical signal travels down and to the left. Now, in physical terms, this kind of directional movement of an electrical signal is called a vector. A vector is any force that has an amplitude or size and a direction. So the fact that electrical signals during cardiac depolarization travel in a certain direction is going to become important. Now, the first lead we're going to talk about is lead 1, which happens to be between the right arm and the left arm. So imagine that voltmeter now is connected to the right arm and the left arm. The way the polarity is set up in the machine is that signals that are traveling in this direction from the right arm to the left arm will be inscribed on the paper as a positive deflection. Okay, so any signal that's traveling from right to left is going to look upright on the ECG. Now, since the P wave and the QRS complex are both traveling down and to the left, they'll both appear positive in this very simple bipolar recording. And so your ECG will look like this when you record it from the right arm to the left arm. Now, by convention, right arm to left arm is known as lead 1. Okay? That's the idea. Lead 1 is from right arm to left arm, and in a normal person, it will look kind of like this, with a P wave and a QRS complex that are both upright, because the P wave is traveling in this direction towards right to the left, and the QRS complex is traveling right to left, isn't it? So that's lead 1. Well, what about the rest of the leads? Well, it turns out in most ECG systems, the right leg is a ground. So it's kind of like helps the machine determine where 0 volts is, and in some ways it kind of avoids excessive noise in the recording. And so it's the left leg that becomes important in recording ECGs. Now, lead 2 is recorded from the right arm to the left leg. Okay, so the right arm to left leg is lead 2. And then the left arm to the left leg, and that is lead 3. Now, one of the pioneers in electrocardiography was a guy named Einthoven, and he described Einthoven's triangle, which had a lot to do with the early leads and the way he devised how lead systems are going to be created. And what he described as lead 1 being from the right arm to the left arm, lead 2 being from the right arm to the left leg, and lead 3 being in this direction from the left arm to the left leg. Now, this was Einthoven's triangle, and we're going to talk a lot more about this in the next lesson, but I want you guys to understand the concept behind each of these leads. There are 3 other limb leads that we can talk about, and these are known as augmented limb leads. It has to do with a unipolar versus bipolar recording, because what the machine will do is, for example, take the left arm and compare it to the right arm and the left leg. It'll kind of hook the right arm and the left leg together, and then measure the voltage in the left arm compared with the sum of the voltage here. And it gives you a direction that is kind of headed towards the left arm. We refer to that as an augmented lead. It's known as AVL. Likewise, there's an AVR, and there's actually an AVF, which again are kind of sort of semi-unipolar leads, AVF looking at the left leg compared with the sum of the 2 arms. This will make a lot more sense when I talk about the circle around the patient that relates all the frontal leads to each other. And so go ahead and watch Chapter 2 of this section, and I think it'll make a lot more sense. Well, this is Dr. Nick for the Ecg Academy. See you then. Hi, this is Dr. Nick with the Ecg Academy with the second chapter in Section 5, talking about the limb leads. Well, here we are going back to the idea that the heart in the chest is creating this electrical signal that's traveling in a direction, usually down into the left of the patient. Okay, that's the idea of a vector. A vector is an electrical signal that has a direction. And so how do we record these vectors, and how do these ECG leads make sense? Well, we talked about Einthoven's triangle, and Einthoven decided that he was going to use the right arm, the left arm, and the left leg to create this electrocardiographic view of the heart. Remember that lead 1 is moving, anything that moves from the right arm to the left arm will be in lead 1 will appear to be upright in the cardiogram. Lead 2 are signals traveling from the right arm to the left leg, because that's where the wires are connected, and those are the electrical signals that lead 2 is picking up. And then lead 3 would go from left arm to left leg. Those are the wires that are used to derive lead 3, and any signals going in this direction will be upright in the ECG lead. Of course, conversely, anything that's going in the opposite direction will show up as a negative deflection on the EKG. Okay, I just want to make that clear. So that gives us an idea. If we look at any one particular lead, we can tell what direction the signal is going in. Okay, well, a triangle is a little difficult to understand. So, because we have the augmented leads in there as well, AVR, AVL, and AVF. So, I like the idea of a circle. The circle representing the frontal leads, which are the leads that we see in the front of the patient when we're viewing the front of him. Okay, and this circle is divided into 360 degrees. By convention, we usually divide this into 4 quadrants. And we consider this angle to be 0 degrees, and the degrees go upwards from here, and negative degrees are this way. This will make a lot more sense when we talk about axis. But let's review what the ECG leads that we have in Einthoven's triangle are. We have lead 1, which is going from right arm to left arm, and that's going straight across, so we can draw it in this circle looking like this. So lead 1 is drawn straight across and is pointing to 0 degrees, and will record any activity that's going in a horizontal direction. Now lead 2, how do we remember that lead 2 is going from right arm to left leg? Well, I always remind people that in English, at least, we read from left to right and from top to bottom. And so when you're ready to draw the second ECG lead in, you want to draw it from left to right and top to bottom. But it has to divide the circle into 6 parts because there's 3 leads, and they'll all bisect the circle. So where do you draw it in this quadrant here? You draw it 60 degrees above the horizontal, so that divides it like 60 degrees. Remember, there's 60 degrees in every corner of an equilateral triangle for you guys who actually passed geometry. And so lead 2 is drawn just like this, which is 60 degrees up from the horizontal, going from the right arm to the left leg. But it's beginning to divide this circle into 6 equal parts. Now lead 3, which is from left arm to left leg, we would naturally draw just like this and label it lead 3. And thus we've divided the circle into 6 equal parts, and we've defined angles that correspond to these 3 basic ECG leads. Now, what about the augmented limb leads? Well, the augmented leads kind of split these 60-degree angles in half, because AVL, which is sort of the left arm compared with the sum of the right arm and left leg, is kind of pointing towards the arm itself. And so what you get is this kind of an angle with the head of the vector heading this way. So this is AVL. And likewise, AVR is drawn 30 degrees above the horizontal in this direction, pointing towards the right arm. So this is AVR. And then, of course, AVF would have to go right down the middle. So that's AVF. And so we've now split this circle into 12 equal parts, each one corresponding with one of the 6 limb leads that we see on a standard ECG. Remember what these look like. We have 1, 2, 3, AVR, AVL, and AVF. Those are the limb leads on the first part of a 12-lead ECG. All right, let me get rid of that for a second and go back to this drawing. Okay, now the idea behind the leads being important has to do with the direction of the electrical signal. So let's say that in this normal person, you have a vector that's traveling down and to the left. So now if you happen to be monitoring, let's say lead 2, which would be going from the right arm to the left leg, the signal is traveling along lead 2 in that direction. And so when you look at the EKG in lead 2, you're going to see a large positive deflection of both the P wave and the QRS complex. Well, let's say now you go over to that monitor and you switch the selector to AVL. Now, AVL is going to be in this direction. Now, we've already decided that the vector is traveling in this direction. So AVL is almost perpendicular to the direction that the vector is traveling in. And so when you look at AVL on your monitor, you may only see a little tiny deflection. And it wouldn't exactly be a good lead to monitor because the QRS complexes are so small. The monitor may actually double count the P and the QRS, or it might not pick up anything at all, and you'll get heart rates of 0, and that makes the patient's family really upset when they look up at the monitor and see heart rates of 0. Because the monitor is not picking up the QRS complex. So switching to a lead that will pick up a larger signal makes a lot of sense in those cases. Now, the proof of what I was saying is in this ECG, because here you have an example of where the signal is very large in lead 2, but it's much, much smaller in AVL. And so it's a similar situation to what I just described with the axis that's going in the direction of lead 2. Because of that, it's going in the perpendicular direction to AVL, and the signal that you record is much, much smaller. Doesn't it make sense now? Okay, so the basic concept of a lead is that you can, in fact, get a sense of what direction things are traveling. By switching leads, you can get a better view, an electrical view of the heart, because the signal is traveling along that lead rather than perpendicular to it. And in the intermediate course, we'll start to talk about axis, which is basically the exact angle that the QRS happens to be at, where you actually have a normal range between minus 30 and plus 120, where that vector or the axis of the electrical signal is normal, and anything above or to the right of that is going to be abnormal and define axis deviation and allow you to diagnose crazy things like left anterior hemiblock and other kinds of advanced electrocardiographic diagnoses. So with this discussion of the limb leads, we'll get ready for Chapter 3, which is going to be a review of the precordial or V leads and the kind of things we look at when we examine those. And then in the next section, we'll start to analyze the QRS complex itself using real tracings and start to talk about real electrocardiographic diagnoses. This is Dr. Nick with the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick, and we're going to be finishing up this section on ECG leads, and we'll talk about the chest leads or the precordial leads. And if you can imagine, this is actually somebody's chest. It's a diagram of a chest sort of like cut down the middle in a horizontal direction so that you actually have the spine back here and the breastbone or the sternum over here. So just to orient you, this is the outside of the chest wall, and inside the chest, of course, we'll find the heart. There it is. I've drawn this ahead of time. So remember, if this is the front of the chest, then the heart is kind of rotated with the right ventricle and the right atrium towards the front, and the left atrium and left ventricle sort of towards the back of the heart, sort of posterior, pointing towards the spine. We discussed this in the three-dimensional anatomy video in an earlier section. So anyway, where do we put the precordial leads on? Well, of course, I did show you a video where the precordial leads go here, with V1 being on the right sternal border, V2 being in the left sternal border, V4 being in the midclavicular line, and V3 somewhere in between, V5 on the anterior axillary line, and V6 being in the mid-axilla, sort of like I've drawn it so that you're just sort of like cutting the chest in half, so that would be in the mid-axillary line. So that's where the V leads go. And what do they record? Well, these are kind of like unipolar leads. Remember, unipolar leads are a single lead, and you're looking at voltage movement towards or away from that lead. Now, when the heart depolarizes, it's the electrical system that allows for proper synchronization and efficient depolarization. And I've drawn in the cardiac conduction system here, with the AV node in the septum. You've got the main bundle of His, a very thin right bundle coming to the right ventricle, and then a large left bundle that splits into hemifascicles and other branches. So the first part of the heart to depolarize is actually the septum, off of a branch of the left bundle branch. And so the initial activation of the heart in the septum traverses away from the left bundle branch, anteriorly towards the right ventricle, and away from the left side. So it's the first part of the electrical signal travels towards the front and away from the left side. Then, of course, the left ventricle, being the much larger of the two ventricles, depolarizes mainly down and to the left, and at the very end sort of finishes in a little bit of a posterior direction. So what does that look like on the ECGs in the various chest leads? Well, in V1, the first thing you'll see is a P wave. Remember, the sinus node initially stimulates the right atrium, but then Bachmann's bundle conducts the signal to the left side, and left atrial contraction occurs a little bit later. So the signal first goes towards V1 and then later goes away from V1. And the P wave often has a kind of a biphasic appearance to it because of that reason. Then you have the PR segment, and then the QRS complex will have a very characteristic appearance because the septal depolarization is going towards V1. So you have an initial positive deflection, but then the left ventricle being so large and depolarizing in a posterior direction will give you mostly a deep S wave before resolving back to the baseline, and then often you'll see a T wave. And so V1 should look like this in a normal person. Now let's take V6 on the other hand. V6, what happens is you get a P wave that's sort of upright because it's traveling towards V6 all the time. It's traveling sort of towards the left. So you'll get a fairly upright P wave. But then what happens is the first part of the QRS is going to be going away from V6 because it's the septum that's being activated. And so what you'll get is a negative deflection, a Q wave, which is known as the septal Q wave. And then what happens is the rest of the left ventricle depolarizes and it's all going towards V6. And so you get a very large R wave. And then sometimes you'll get an S wave at the end, sometimes not, depending upon exactly how the ventricle is shaped. And then, of course, the T wave comes after. So this is what V6 will look like. Everything in between will generally be a steady progression from one to the other. In other words, the R wave will gradually increase in size until you get this big R wave. And the S wave will gradually diminish in size until you get hardly any S wave, if any at all. Okay, so now V2 is kind of like a lot like V1, in that you get sometimes a little biphasic P wave there. And then, but the R wave should be a little bit taller, and the S wave should still be negative. Now, V3 and V4 are the two leads where the so-called transition point generally occurs. What's the transition point? Well, that's where the R wave grows bigger than the S wave. So, all right, so in this case, we'll have the transition point be at V4, which is more common, I think, than V3. You have a P wave, and then you have an R wave that's getting bigger, but the S wave is still there, and it's still a little bit bigger than the R wave. But in V4, now we've reached the transition point on the precordial leads where the R wave is bigger than the S wave. V5 will progress again towards V6. You may have a little residual S wave there, and then V6 will finally look as I've drawn it. So you can see that the R wave gets bigger and bigger and bigger across the precordium, and the S wave will gradually get smaller and smaller. And the reason that's so is because we're seeing different electrical views of the heart. As we get further around the back end of the heart, we see the ventricle growing larger and larger. Why? Because the left ventricle is indeed a posterior structure, and V6 is seeing the backside of the heart a lot better than V1 is. So when you look at a 12-lead ECG, you should see this kind of R-wave progression across the precordial leads, and that tells you that all the electrical signals are in their proper position. You can imagine that if the precordial leads are not in the right position, then the R-wave progression will not look normal. And people will be tempted to diagnose all sorts of problems like old infarctions and crazy conduction abnormalities. So putting those leads in the proper position is definitely important. So now that we've completed our discussion of all 12 leads and you have a sense of what they should look like, we'll go on to the next section where we begin to examine real-life tracings of the P waves, the QRS complexes, and the T waves, begin to make initial measurements in terms of intervals and rate, and begin to put together an organized approach to reading ECGs, because it's important that you don't miss anything. And in order to do that, you have to have an organized approach. You have to look at the forest and then examine the trees, and bit by bit, piece by piece, put the thing together and figure out what's happening physiologically so that you can make the correct diagnosis on paper. Remember, I'm here to make you an ECG expert. So keep on watching these videos and I'll get you there. This is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're starting Section 6, which is all about the normal ECG and how to start to pick apart what you're looking at. All right, I want to get out my soapbox a little bit. I created the Ecg Academy because I've been teaching ECGs to people for decades, nurses, doctors, technicians, and I know what's important and I know what's not important, but the most important thing about trying to learn something from a video like this is that you have to be able to see clearly. And I've created these videos all in high definition, and I just want you to see something. This is an ECG that I got off the internet, and it's something that you'd see typically on an ECG website. Now let's zoom in a little bit. I just want you to see what this actually looks like. I think you can tell that this is actually a very low resolution scan of an ECG, and a lot of the details are lost. I just want to show you what I've done is created ECGs in high resolution, done scans of ECGs that are in my own library, and I just want you to see the difference in the fidelity. I mean, you can see every little detail in these ECGs. In fact, look at the pattern of squares on the paper. Compare that with what I showed you before. I think even on a small viewing window on your desktop, you can see that there's quite a difference in resolution. So much for my little political statement. I hope you'll subscribe to Ecg Academy and let me help you become an ECG expert by watching all these videos from beginning to end, and then subscribe to the weekly Chalk Talks, which will help you get used to reading more difficult tracings, give you lots of practice, because these will be real tracings that I've gotten from my practice from the hospital and from real patients, and I'll go through them with you at levels varying all the way from the very basic up to extremely advanced. So having said all that, let's get back to looking at ECGs as one of the most important tests you can do on a patient with heart disease. And this applies, of course, to cardiac monitors that you'll find on an ambulance, in the emergency room, in the coronary care unit. And my purpose here is to make sure you know exactly what you're looking at and get the diagnosis right. Now, what I've shown you here is an ECG that was done on a typical rolling cart type of machine. This machine carries with it pre-printed paper. Now, the paper here has that pink box pattern printed on it, and either pens or another mechanism will imprint the ECG on there. This isn't the only type of ECG that you can see. There are other kinds of ECG machines that will use the color papers. You can see here you've got an imprinted green square checkerboard pattern with the ECG printed with black ink. And then if you work in a hospital, most of the telemetry units and intensive care units use paper that's printed on a thermal printer. And you get these strips that are created by a thermal printer, and all the little gray dots are actually printed by the printer itself. But keep in mind that thermal printer paper fades with time. And if you want it to be part of the permanent record, it needs to be either scanned into the medical records department or photocopied. Thermal printer paper is not a permanent record. Let's get rid of some of these and take a closer look at what's actually on this piece of paper. Most of the commercial ECG machines will print a bunch of information on the page, information that will be very valuable to you. For example, identification, the patient's name, sometimes the medical record number will be over here, the patient's age, and then you'll have basic measurements here. For example, this reports out the heart rate in beats per minute, that's 88. The intervals are measurements that the computer will come up with. We'll talk about those in the next video. The measured axes, P, Q, R, S, and T in degrees, which we'll talk about in the intermediate course, and some other measurements of size and so forth. Now, on the paper, you'll also see information printed in terms of the standardization, which I'll talk about in the next video. And there are also these standardization marks. And of course, each lead will have its own label, 1, 2, 3, AVR, AVL, AVF, and so forth. Okay, here's another example of an ECG that was done on a different manufacturer, but it's basically got the same information on it. You got patient ID over here. You have measurements of one kind or another over here. This happens to be ST segment measurements because this came off of a stress test machine. And then at the bottom, you have information about the standardization in terms of this paper speed and the calibration size. So we'll go into more of this in detail in subsequent talks. But the one thing I want you to understand is that regardless of what you actually read on the ECG in terms of what the computer prints out, you always have to remember one thing. Never believe anything you read on an ECG, whether it's written by a nurse or a technician, or whether it's actually printed on the cardiogram in terms of an interpretation. Here, sometimes the computer will write normal sinus rhythm and so on and so forth. Often the computer readout is incorrect and needs to be overread by a cardiologist. And between you and me, it's surprising how often the official reading of an electrocardiogram is not entirely accurate. So keep all that in mind as we go through these videos and I teach you how to become an ECG expert. Stay tuned for the next chapter when I talk about the size and duration of the calibration marks and how to actually begin to measure the intervals using a pair of calipers. For the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and this video talks about timing, amplitude, and rate measurements of the normal ECG. This is Chapter 2 in Section 6, and we're going to basically get into these little tiny boxes and what they mean. Well, this is an ECG, a normal one from an 18-year-old. It's about as normal as it gets, but let's look at a high-resolution scan of this cardiogram. All right, now on this scan, you can see that there is this grid here. There are these heavy lines moving across, heavy lines moving up and down, and they create this these squares, large squares. But within each large square, there are these small squares. The ECG is based on the metric system, so one small square is 1 millimeter high and 1 millimeter wide. Remember, there's about 25 millimeters in an inch, just so you guys have some reference here. And so you have these 1 millimeter boxes. Now, the ECG machine that's printing out a standard size ECG will use this measurement. That's 10 millimeters per millivolt. Remember that milli in the metric system means 1,000th. So one of these is a millimeter, which is 1,000th of a meter, and it says 10 millimeters per millivolt. So if you count up 10 of these, that's 2 large boxes, because each large box is 5. So you have 10 millimeters here, and that's equal to 1 millivolt. Remember, that's 1,000th of a volt. It's a very small number, isn't it? But of course, we're measuring the heart's electrical activity through the skin and the bones and the muscles, so we're only seeing a little tiny electrical signal. If we actually measure this, all right, so this is a QRS complex. Remember, this is a P wave, and here's the QRS complex, and this one lands on the baseline, so let's measure 1, 2, 3.5 little boxes. Well, what's a little box? If 10 little boxes is equal to 1 millivolt, then one little box is equal to 0.1 millivolts, or 1/10 of a millivolt. Multiply that times here, 3.5, and you get 0.35 millivolts. That's a really tiny QRS complex, isn't it? All right, so that's how high they are. Now, how do we know? Do we have to look for this number? Well, you can actually see this thing. It's called a standardization pulse or a calibration pulse. And it happens to be 10 small boxes high. That tells us that the ECG machine is putting out a standard size. If you needed to have a larger tracing, let's just say if the signals are really small and you wanted to see more detail, you could push a button or turn a knob on the ECG machine and increase it to 20 millimeters per millivolt. The standardization pulse will then look this big, and the ECG will be twice as large as it otherwise would look. So that's how you can tell what your standardization is. You can look at this calibration pulse here, or you can look at your standard here. The other thing you need to know about is timing. If it's running the paper at the standard speed, then this should be 2 small boxes wide. On the paper, if you look down at the bottom someplace, there'll be something that says this, 25 millimeters per second. Well, that tells us how fast the paper is running. So remember, 25 millimeters is 25 small boxes, so 5, 10, 15, 20, 25. So from here to here is 1 second. So we can split this up and we can say, okay, well, if that's 1 second, then one large box is 1/5 of a second, isn't it? Because there's 5 of them in a second. And if you drill down and look at one of these tiny little boxes, it's 1/25 of a second. Well, to tell you the truth, most people don't really like to use fractions. And I think decimals are much easier to understand. But what's even easier to understand are milliseconds. Well, especially electrophysiologists who deal with ECGs all the time, they deal in milliseconds because it tends to be a little bit easier. The numbers, they're whole numbers, they're not fractions or decimals. Well, what's a millisecond? Since 1 second is made up of 1,000 milliseconds, after all, milli means 1,000th, doesn't it? So that 1 millisecond is equal to 1,000th of a second. All right, that makes sense. So that means if there are 1,000 milliseconds in 25 boxes, if we divide 1,000 by 25, that gives you 40 milliseconds. So that means that one of these little boxes is 40 milliseconds wide. And a big box is 5 little boxes, so that's 200 milliseconds wide. That becomes very important in the next chapter because we're going to be making measurements of all these little waves and everything. But for the time being, let's stick with the big picture. Because in reality, the first concept you have to think about is rate. How fast is the heart rate? Well, that's precisely the topic of the next video. So go watch it, will ya? This is Dr. Nick from the Ecg Academy, signing off. Hi, this is Dr. Nick from the Ecg Academy, and we're going to continue this discussion of heart rate measurements. We're going to pick up where we left off with the last tracing. Now, we've already established that at a normal paper speed, the paper is running at 25 millimeters per second, and that's our time reference. Now, how do you translate the timing that we've already established as being 25 millimeters per second? How do we get beats per minute out of that? Well, again, we're going to get into mathematics. The conversion has to do with the fact that there are 60 seconds in 1 minute. And because we're dealing in beats per minute, we have to somehow put this into the equation. Now, we know that 1 second is equal to 1,000 milliseconds. So that means that 60 seconds is equal to 60,000 milliseconds in a minute. Now, that's the fudge factor, 60,000. What that means is that the rate relationship between the interval, or the time between beats from here to here, is related to rate in a calculation that rate is equal to 60,000 divided by the interval between beats. Okay? So how do you figure that out? Well, you simply count. If you know that each big box is equal to 200 milliseconds, So make it easy on yourself. Scan the ECG and look for a QRS complex that lands on a heavy line. Okay, right here. So now if you measure how many milliseconds it is from one beat to the next, and you know that a big box is 200, so let's count off 200 milliseconds, 400, 600, 800, 1,000. And now you have to kind of look a little bit carefully. This turns out to be 1,100. So now if you take 60,000 divided by 1,100, plug it into your calculator, you get about 55 beats per minute. And it's easy, right? You can do this in your head, can't you? Well, most people can't. So don't feel bad. There are other ways of figuring out heart rate, and most of it depends on how many milliseconds there are between beats. Let's kind of zoom in on one of these leads here and try to figure out what the rate is. Well, you can count backwards and you can count forwards as well. Well, here's a P wave that lands on a heavy line, and you can count backwards if you like and count milliseconds 200, 400, 600, 800, 1,000, 1,040, and you can plug that calculation in. But there is an easier way. If you sort of like figure out let's see, if it's 200 milliseconds, 60,000 divided by 200 is equal to 300. And then if you figure on, okay, what about 400 milliseconds? Well, 400, if you take 60,000 divided by 400, and that comes out to be 150. Well, now there's a sequence of numbers, and as long as you can memorize these numbers, then it becomes very easy to count the rate. Okay, and so here are the numbers. If you start on a heavy line, the first number, if the signals are just one box apart, then the rate is actually 300 beats per minute, as I showed you in this calculation here. If the signals are two boxes apart, then it's 150 beats per minute. If they're three boxes apart, it's 100. If they're four boxes apart, it's 75. 5 boxes gives you 60, and 6 boxes gives you 50. If you just remember this sequence of numbers, does it make sense? Well, sure, look at that. If the beats are 5 boxes apart, 1, 2, 3, 4, 5, then it's 60 beats per minute. Well, 5 boxes is equal to 1 second, isn't it? And there are 60 seconds in a minute. So it all makes sense. If you remember, 300, 150, 100, 75, 60, 50. So what you do is you start on a heavy line, if you can, like say, for example, here. And then you count in one direction or another looking for the next similar signal. So 300, 150, 100, 75, 60, and this would be 50. Well, now you're going to have to kind of fudge it a little bit. If this is 60 and this is 50, then your heart rate here must be something just below 60, and you'd probably be okay to call it 58 beats per minute. So that's a quick and easy way to figure out the heart rate. Okay, so we're going to go back to this tracing, this whole 12 lead on that 18-year-old person. And we're going to get a sense of how do you measure rate on a 12 lead. Well, as I said, you kind of have to scan around and look for a QRS complex that lands on a heavy line. And this was the one that we used before. So if you count off, we can say 300, 150, 100, 75, 60, 50. So if this is 60 and this is 50, you have to kind of call it 55 or so. And that's what we came up with when we did that mathematical calculation. Okay, so it kind of makes sense to do this. Well, let's try it again. Here's one that lands on a heavy line, so let's count it. 300, 150, 100, 75, 60. Wait a minute. Wait, that's not the same. If this is 75 and this is 60, then we're talking a rate of like maybe 68 beats per minute, but that's not the same as this one. So it turns out that there is such a thing known as sinus arrhythmia. Sinus arrhythmia is a normal finding, and we're going to discuss it when we talk about sinus node function. But sinus arrhythmia occurs in normal people, especially 18-year-olds, and it has a lot to do with the nervous system's effect on the heart rate. And even with just respiration, the heart rate will vary from one beat to the next. So it becomes a little bit difficult. But I want to introduce you to the electrocardiographer's best friend, and that is calipers. Yes, indeed. Calipers are a way of trying to get a sense of whether we have a regular rhythm or an irregular rhythm, and it also allows us to make measurements that we otherwise would have difficulty making. For example, when things don't land exactly on a heavy line. So you take your caliper, and I'm just putting it on this point here, and then what I'm going to have to do is electronically kind of like resize it so that the other point lands on this other QRS complex, okay? And so then when you move the calipers from one beat to the next, you can get a sense of whether the interval is the same. This is almost the same, but clearly this interval is a little bit shorter. The R to R interval from the one QRS to another QRS is shorter than what we saw in the first couple of beats. And this is much longer than we saw in the first couple of beats. So yes, indeed, there is a bit of a challenge in measuring rate. You have to kind of look for an average heartbeat and measure it. Now, I'm going to show you a way around that a little bit later in this video. But first, I want you to get used to using these calipers. Now, the cool thing about calipers is it lets you measure things that don't land exactly on a heavy line, and I'll show you how. Well, let's go back to this first interval here. And we're going to put the point of the caliper on the first beat. And the second one, I guess maybe I could probably resize that a little bit better so that it lands on this second beat. Okay? So now that's showing us exactly how long the interval is. Well, now, how do we measure that without having to count little tiny boxes and get into milliseconds and do crazy stuff like that? Well, once you've established the interval here, you simply pick up your caliper off the page and you lay it down on another part of the paper such that the left-hand point is right on a heavy line. You can see that I've placed it on this heavy line, and now you can see what the interval is. If you want to count off in milliseconds, it's 200, 400, 600, 800, 1,000, probably 1,040. Maybe 1,060 if you look carefully. We're going to zoom in on things in the next video, so you'll be able to make fine measurements of PR intervals and so forth. But for the time being, you can make gross measurements without having to count little tiny boxes. In terms of heart rate, we're talking start with this one and count off the numbers, as I said before, 300, 150, 100, 75, 60. And you see it's a little bit less than 60. But it's nowhere near 50. So again, we have about 58 beats per minute, abbreviated BPM. Okay, so this first beat is 58 beats per minute, but there's a normal degree of sinus arrhythmia such that sometimes it's at 68 and sometimes it's down to 55 and so on. So that is your basic approach to determining heart rate. The key here is that you really have to look at the whole entire tracing. I always tell people when you're first looking at an ECG, you really have to look at the whole forest. Don't concentrate on the trees. Don't zoom in and look, oh, look at that. That fifth beat over there has a little funny swiggle. I wonder what that is. Well, before you get into those tiny details, you kind of have to scan the whole ECG all the way across and get a sense. Is it regular? Is it irregular? Are all the beats kind of about the same distance apart? In which case you can sort of like use any one you like and you'll still kind of be in the ballpark. Or is it very irregular? And I'm going to show you an ECG that's very irregular next. Now here's an example of an ECG where the rhythm is irregular. In fact, this is an abnormal rhythm. It's known as atrial fibrillation. You may have heard about that. It's due to a rapid electrical disturbance in the top chambers of the heart. So the atria are beating 1,000,000 miles an hour, but the AV node winds up passing a rather random signal down to the ventricles, and so the heartbeat is irregular. And you can see some of these intervals are actually very short, and other intervals are very long. And determining heart rate is a little tricky because depending upon which interval you measure, you could get vastly different heart rates. So calipers aren't terribly useful under these circumstances, but I'm going to show you something that is useful. Well, one thing you can do is just run a strip that's a whole minute long and count the number of R to R intervals in a whole minute, and that would give you the number of beats per minute. Well, that kind of would be a bit of a waste of paper, and it would also mean you'd have to sit there with the patient for that long. So that's not a practical solution. But what if you ran the ECG for 30 seconds, counted the number of heartbeats, and then just multiplied by 2? Well, that would give you the number of beats in a minute, right? Well, take that idea a little bit further. What if you only ran it for 10 seconds? Then you'd have to just multiply by 6, and then you would get the beats per minute. Well, I got an even better idea. Look down at the bottom of this tracing, and you'll find pretty much on every single printed ECG these little doodads. These little marks here are known as 3-second marks, and they're spaced, surprisingly, 3 seconds apart. So if you measure the number of R-to-R intervals between two of these marks, that would give you 6 seconds. And then you can multiply that by 10, and that would give you the number of beats per minute. So let's figure this out. Try to find a QRS that's more or less close to one of these 3-second marks. So we'll pick this one. Now you're going to measure, this is 3 seconds, and this is 6 seconds. How many R-to-R intervals are there in 6 seconds? Well, this R-to-R is 1, and this one is 2, and this one is 3, 4, 5, and now you'd have to say like 5 and maybe a half, or maybe 4/10. So that gives you a rate of 54 beats per minute. Now, of course, if you measure something a bit different, so if you go from this one to this one, you may get a different number. So this would be 1, 2, 3, 4, a little bit more, you might get 42. But this is a challenging ECG because the rate is so tremendously variable. But it gives you a tool, it gives you a way of measuring grossly irregular heart rates using these 3-second marks. Well, this is one of those tips you'll only get here at the Ecg Academy. And that concludes my discussion of heart rate measurements. In the next video, we're going to be talking about measuring intervals like PR, QRS, QT, and so forth. This is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the last chapter in this section of the normal ECG. We're going to talk about measuring intervals because this is one of the first things that we do when we're trying to interpret an ECG. So as far as measuring is concerned, we've got this tape measure that I kind of remember. My grandmother was a seamstress, and she'd whip one of these things out and start measuring all different parts of my body. But we're going to talk more about the ECG and how do you measure different intervals, and you can start to make electrocardiographic diagnosis. Well, first, a quick review. Here's a typical grid that you see. You've got large boxes and you've got small boxes. Remember that small boxes are 1 millimeter apart. If you assume the standard measurements of a normal ECG machine, you have 0.1 millivolts high for each little box and 40 milliseconds wide for each little box, and the big boxes are 200 milliseconds wide. For those of you who are used to seconds, there's 25 millimeters in a second, so that's 5 big boxes. That means each box is 1/5 of a second. I frankly don't like using fractions, but some people do. Anyway, so much for the grid. Let's talk about the ECG. If you recall, the atrial depolarization gives you a small bump known as a P wave. Ventricular depolarization results in a QRS complex. And then there's always a relaxation wave known as the T wave. So that's the QRS, and here's the T wave. Other parts that we need to be concerned about, the PR segment, which is the part between the P and the QRS complex. The ST segment, between the S wave. Remember, the first negative deflection is a Q, then the first positive deflection is an R, And following the R, you can have an S wave. And then you have the ST segment, which is between the S wave and the T wave. Remember, the point where the QRS complex ends and the ST segment begins is known as the J point. Now, there are a couple of extra waves that can be seen under certain circumstances. Okay, let's draw another EKG over here. Here's a P wave. Now, in some people who have an abnormal electrical system, they may actually have a slurred upstroke of their QRS complex, and this is known as a delta wave. And we'll talk about that in the advanced course when dealing with the Wolff-Parkinson-White or WPW syndrome. But what this does is it causes the QRS complex to widen, start early, and the PR interval is almost non-existent in those patients. Okay, sometimes you'll have inverted T waves in these patients. And there's one last wave that I want to mention because it is considered part of the QRS complex, and that's known as an epsilon wave. And that's found at the tail end of the QRS complex. Sometimes it's high frequency like this, and sometimes it's just widening at the tail end of the QRS. These are seen in certain cardiac illnesses and conditions, and we'll talk about that also in the advanced course. Now, what measurements are important? Well, there's the R to R interval that gives us our heart rate, and we talked about that in the last chapter. The intervals that we measure on a QRS complex include the PR interval, which is from the beginning of the P wave to the beginning of the QRS complex. That PR interval tells us something about the AV conduction system. The duration of the QRS complex, how long does a QRS take to inscribe? That's from the beginning of the QRS to the end of the QRS. And then the other interval that needs to be measured is known as the QT interval, which is the beginning of the QRS complex to the very end of the T wave, where the T wave comes back to the baseline. If you consider this to be the baseline of the QRS complex, where the T wave comes back to baseline, that's considered the end of the T wave. Now, every now and then you will see something else that's unusual, and we're going to talk about this in the advanced course. Sometimes what you'll see is a T wave and then a second bump following it. So this is a T and this is a U. Some people think that this is sort of all part of the T wave, but usually the U wave is a discrete, separate signal and can also be seen in certain abnormal conditions that we'll talk about in the advanced course. All right, so now that we've kind of reviewed all these different parts of the QRS complex, let's start practicing because, after all, we need to measure some of these things. Okay, so here's our normal 18-year-old, and if you kind of glance at this ECG, it's lead 2. If you remember your vectors, lead 2 is in this direction, down and to the right, or down and to the patient's left. It's 60 degrees above the horizontal, right? So that's from right arm to left leg. That's just a quick review of electrocardiographic axes. Okay, but that's not important to this discussion. What I want to talk about is first measuring R to R interval. Okay, so find an R to R that's kind of close to a heavy line. Like take this one. Now it's off about 20 milliseconds, so you have to take that into consideration. And what I like to do is just kind of look for the same spot on this heavy box. So that's 200, 400, 600, 800, 1,000, another 40 milliseconds. So that's 1,040 milliseconds. If you needed to count rate, that would be 300, 150, 100, 75, 60, a little below that, so that's 58 beats per minute. That's a number that we've seen before, isn't it? So 58 beats per minute, the R to R interval is 1040. Okay, now what about the PR? Well, you're going to look for the beginning of the P wave as best as you can tell. Now here's a P wave that's right on the heavy line here. So you measure the P wave to the beginning of the QRS complex. Okay, You have to be precise with this, so sometimes it helps to take out a pair of calipers. And there they are, our trusty calipers. You can pick them up and you lay down one point at the very beginning of the P wave, and then the other point goes at the very beginning of the QRS complex, and that measures out the PR interval. And then you pick up the calipers without moving the points, of course, and you lay it on a heavy line, and then you count off how many milliseconds is this, okay? So that's 40, 80, 120, and just about 160 milliseconds. Now, if you're off by 10, it's no big deal. A lot of times it's really hard to put these calipers on precisely, but try to be within 10 to 20 milliseconds in your measurement. So we're going to call this PR interval 150 milliseconds because I can actually see it with my eyeballs. I think maybe the calipers, we should have made them a little smaller, but you have to use your eyes. Now, what about the QRS duration? Well, here's where the QRS starts, and here's where the QRS ends, and here calipers are important, but I would say that you have a little more than 2 small boxes here. So if it was 2 small boxes, it would be 80. This is probably about 90 milliseconds, and that's the QRS duration. Now, let's kind of look at another QRS complex. Let's look at this one just to kind of double check, because after all, there are a couple here. Now, you can see the QRS ends just before the heavy line, and it starts just before this light line. And so you have 2 boxes almost exactly. And here as well. I mean, I think perhaps on second thought, this is probably more like 80 or 85 milliseconds. I think the computer would probably read it somewhere between 80 and 90. All right, so that's the QRS duration. And that's important because when you have delay within the interventricular conduction system, you'll have something known as an interventricular conduction delay, and very specific types of those delays are called bundle branch blocks. We'll talk about that in the advanced course. Finally, the QT interval. Well, since this is landing on a light line, let's count off. We can do 40, 80, 120, 160, 200, 40, 80, 120. It comes right back down here at about 160. So 200 plus 160 is 360. And that's the QT interval. Now, the one measurement that we didn't talk about is the corrected QT interval. The corrected QT interval, which is abbreviated QTC, is derived from a formula, and the reason we need it is because the QT interval, because it represents the combination of depolarization and then repolarization, it actually changes depending upon the patient's rate. The QT interval gets shorter at faster rates, and this has to be considered because a QT interval at one rate may not be normal at a different rate. Just to make it easy, though, just remember that the QT interval should shorten at faster rates. I think a quick and easy way for people to get a sense of whether the QT is in the normal range is that the T wave should not really extend past the midpoint between 2 QRS complexes. So if you look at these 2 QRS complexes and you figure the midpoint is around here someplace, clearly this T wave ends on time and it's not prolonged. Certain medical conditions can cause the QT interval to become prolonged, and there's even a condition known as a congenital long QT syndrome that we'll talk about in the advanced course as well. And one of the ways to diagnose that is to just measure the corrected QT interval. So how do you correct the QT interval to account for the heart rate? Well, the corrected QT interval is equal to the QT interval that you measure times 1 over the square root of the R to R interval, and that's in seconds. Okay, so it's a bit of a calculation, but it's not that hard if you have a calculator and you can figure out square roots. Otherwise, there are tables that you can look up to see what a normal QTC is for any particular heart rate. So in this example, your R to R interval is 1040 milliseconds, but in seconds, that's 1 over the square root of 1.04. Get it? This is in seconds, so you have to shift the decimal point over 3 spaces, 1, 2, 3, because we're dealing with thousandths of a second here, which has 3 zeros, and here you're dealing with seconds. So I'll bring my calculator up and I'll put 1.04, that's the seconds. We'll take the square root of that and then press the 1 over button. And that gives you a conversion factor. Now multiply that times the QT interval that we measured, which is 360, and that equals 353. Because the heart rate is so close to 60, now with 60, the R to R interval is 1 second, and this whole calculation fudge factor basically becomes 1. So the QT at 60 beats per minute is equal to the QTC. So here you can see it's only just slightly lower at 353 milliseconds. What's the normal? In males, the normal is 420 or less, and the upper limit of normal in females is 440 milliseconds. So this one's fine. Okay, so those are all the intervals that you'd normally measure. Well, I think I'll end this video at this point because it's getting kind of long, but I'm going to add one more video to this section in order to give you some more practice in measuring intervals. So for the Ecg Academy, this is Dr. Nick. So go ahead and watch the next video for some more practice. Hi, this is Dr. Nick with the last section in Chapter 6. We're going to practice measuring intervals. Well, here's the next one. If you look at the forest, it looks pretty regular. And if you look at the R to R intervals, it looks like it's falling one small box behind the heavy line. But look at that. It's sort of consistent. Every beat is on the same relative location. So what would the rate be? Well, start with this one. We'll count off 300, 150, 100. So the rate here is 100 beats per minute. Okay, let's look at the PR interval. This PR happens to land on a heavy line. The QRS lands right over here. So that's 3 small boxes. That's a relatively short PR of 120 milliseconds. Now, what is the normal PR interval? That's what we'd like to know. So the normal PR interval is 120 to 200 milliseconds. The normal QRS should be anywhere from 80 to about 120 milliseconds. And the normal QT interval, well, there isn't one, but the QTC should be less than 420 in men and 440 in women. Okay, so 120 fits into the normal range, but keep in mind this is a young patient. The heart's going fast, so their AV conduction kind of gets enhanced that way. The QRS starts with this light line and ends right about here. So you'd call it 40, 80, and not quite a whole nother box, so that's another 20 milliseconds. That gives you 100. So 100 milliseconds for the QRS duration, that's in the normal range. And then for the QT, we're going to count from here, 40, 80, 120, 150, 200, 40, 80, 120, and it comes down to the baseline here, which is another 40, 160, about 180 milliseconds. Add that to the 200, and you get 380 milliseconds. Now, was that a normal QT? Well, it might be. If we look at the midpoint between the two R to R intervals, we're going to wind up being about here. And that's right about where the T wave ends, isn't it? So now let's plug it into our formula. It's actually called Bazet's formula. So the QTC is equal to the QT times 1 over the square root of the R to R in seconds. If you want to do it a different way, you can rewrite it as simply the QT over the square root of the R to R interval. So if the R to R interval is 600 here, because it's 3 heavy boxes, that's how many seconds? 0.6 seconds. That's 600 milliseconds. If this is 600, you bring the decimal point back to the left 3 spaces, 1, 2, 3, and you get 0.6. So let's bring our calculator in here. We'll say 0.6, the square root of that. 1 over the square root is 1.29, and multiply that times the QT that we measured, which was 380, and we get 490. So lo and behold, this QTC is a little bit on the long side. If this was a woman, you'd be a little bit concerned. If it was a man, you'd be especially concerned. So what we found here is a fairly short PR, a normal QRS duration, and a QT interval that, when corrected, looks to be a little bit long for this patient. Okay, one last example. This one's a little bit harder because the QRS and the P wave is sort of small and it's kind of hard to measure. But let's do it really quickly. Here's a QRS that's very close to the heavy line. So let's count off 300, 150, 100. This would be 75. It's closer to 175. It's probably something along about 85 beats per minute. If you want to measure an exact interval, we can count 200, 400, 600, and then another 60, because that's 1.5 small boxes. So that's 660 milliseconds. If somebody wants to take out a calculator and divide this into 60,000, you'll get exactly the rate. Let's leave that as a homework assignment, shall we? Okay, so there's the rate, there's your interval. The problem is it's hard to see exactly where the P wave starts. So you kind of have to look at a couple of beats and get a better sense. That's where calipers can become very helpful. So I've already taken this pair of calipers and set it for what I think is the beginning of the P wave and the beginning of the QRS complex. And lo and behold, if you move it along, you can see that it's fairly consistent. So now let's put the point on a heavy line, and we can see it's just a hair over 200 milliseconds. Maybe it's not even, maybe it's exactly 200 if you want to call it that. So here our PR interval is 200 milliseconds. So that's kind of at the upper limits of normal. Our QRS duration is from here to here, so that's about 80 milliseconds, and it looks pretty consistent. And the QT we'll have to measure. And here again, we don't have a QRS complex that lands on a heavy line, so that's again where calipers become important. Okay, so here they are, and we're going to drag them over so that the one point is in the beginning of the QRS complex, and then we will stretch them out to the end of the T wave, and then we can pick up our points and place the one point on a heavy line, and we can, lo and behold, measure about 350 milliseconds. Got that? Because it would be 400 if it was two big boxes, 400 minus 40, and then another 10, so 350. All right, so we'll get rid of our calipers and then calculate the QTC. So remember, the QTC is equal to the QT over the square root of the R to R in seconds. We have 660 milliseconds, so that comes out to 0.66 seconds. So we take the R to R in seconds, which is 0.66. Take the square root of that, 1 over that number, times the QTC that we measured, which we said was 350 milliseconds, and that gives you 430, which is pretty normal. All right, so now that was a kind of a long discussion, but I hope you get the idea. Measure the R to R interval so that you can calculate the rate, then look for the PR interval, the QRS duration, the QT, and then, of course, correct the QT for the rate by using Bazette's formula. And there you have it. Now, when we talk about AV node conduction, we'll be able to define things like first-degree AV block, which is present when you have a PR interval of greater than 200 milliseconds. But that's a topic for another video, isn't it? Anyway, for now, this is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick from the Ecg Academy, and we're going to talk about rhythm analysis. You know, in my years of practice reading ECGs, I find that diagnosing heart attacks and hypertrophy and all the common electrocardiographic diagnoses when you're looking at a 12 lead is pretty easy once you know what you're looking at. But you know what's challenging? The rhythm. I think figuring out the heart rhythm on a complex ECG is probably the hardest thing to do. And in the cardiograms that I see in the hospital that are misread, it's almost always the rhythm that's misread, not so much diagnosing an old inferior infarction or anything like that. The rhythm is really the hardest part. So we're going to start with rhythm analysis. And of course, the normal rhythm is known as normal sinus rhythm. And that's because the sinus node is what's responsible for initiating the normal heartbeat. So here's my little animation of a sinus rhythm. Recall that the sinus node fires. It activates the atrial myocardium, which spreads down and to the left. The impulse enters the AV node where it gets delayed for a split second, giving rise to the PR segment. And then the His-Purkinje system gets activated very rapidly, giving you the QRS complex. Again, the normal direction that the electrical signal takes is down and to the patient's left. And then, of course, you have repolarization, which gives rise to the T wave. So let's just get this out of the way. And the first thing you want to look at when you're reading an ECG is the rhythm. Now, I always tell people you really have to look at the forest first and then concentrate on the trees. So in this ECG, you have the advantage of a rhythm strip here with lead 2 that marches all the way across. And if you just kind of like scan it, you see that for the most part, it's fairly regular. It gets a little bit slower here, but we're going to talk about that in a later video. But most of the beats are fairly regular. And when you're analyzing rhythm analysis, especially when you're looking to confirm that it's a normal sinus rhythm, here are the things that you have to look for. You have to look at the P and the QRS and the T wave, make sure they're all related to each other properly. That involves measuring intervals like we did in the last section and making sure that everything falls within normal limits. You need to examine the P wave appearance because P waves have a certain look to them, and often if it doesn't look right, then it's not a sinus rhythm. The PR interval is very important, and we're going to get involved with that when we talk about AV block. But if you're going to call it a normal sinus rhythm, it should be a normal PR interval, which you should remember that the normal PR interval is 120 to 200 milliseconds, or 3 to 5 small boxes across. You want to confirm the proper rate and the electrical vector or the direction or the axis that the P wave is going, just to get a sense of where it's coming from. And I'll talk about that in a moment. And make sure that the P that you're calling the sinus P is the only one, because you'd be surprised how often you think that you see a P wave in front of every QRS, but there are other Ps hidden in other places. But we're going to get more into that when we do more complex arrhythmias. So anyway, with this tracing, you start to look at each individual beat, and you can kind of get a sense that there is a P wave that's fairly consistent in front of every QRS, but you say to yourself, well, what's the best lead to look at? I mean, if you look over here in AVL, you can barely see a P wave. Are we sure that that's a P wave even? Or remember, all these lines are going simultaneously. So if there's a P wave here in AVF, then you can say with certainty that this, of course, is the P wave as well. Remember, with ECG recording systems, the limb leads are somewhat directional. Let's review that whole idea of vectors for just a second. Okay, so if we have the heart there, and here are the atria, and here we have the ventricles. We're going to look for normal vectors that are going down and to the left for the P wave, and of course for the QRS down and to the left as well. So which lead should we be monitoring? Well, if you recall our discussion on axis, lead 1 is from right arm to left arm. And which one is lead 2? Well, remember in English we read down and to the left. And that's going to be at a 60-degree angle above the horizontal, because we do have to cut this into 6 equal parts. So lead 2 here, look at that. It's looking down and to the left. So this turns out to be the optimal lead to look for sinus P waves is lead 2. So now let's go back to that other ECG, but let's take a close look at lead 2. Okay, this was the same ECG that I showed you before. Let me just go back to that. So this is here lead 2. We're going to be looking at a close-up of that. Okay, so in lead 2, you can clearly see that the beats are fairly regular. You can see the QRS complex right away because that's obviously the biggest signal. So look in front of it, and that's where you should be finding P waves. And then look after it, and that's where you should be finding T waves. So if we measure the PR interval here, it's 1, 2, 3.5 small boxes. So it's about 140 milliseconds, and that's normal. The QRS complex, this is just practice for you guys, is maybe 80 milliseconds. But you see this little jiggle here? Is that part of the QRS or isn't it? Well, here's where you need to look at the trees, the individual trees. Because if you look at this QRS complex, there's a little jiggle, but it looks kind of different than this. And if you look at the first one, there's a little jiggle, but it looks, again, a little different. So you're better off examining several QRS complexes, maybe use your calipers. But I don't think this is really part of the signal here because it's obviously not there in these other two tracings. So I'd say the QRS complex probably ends here, and that would give it maybe 80 or 90 milliseconds there. And the QT interval, of course, we measure, and you can count the corrected QT as normal or abnormal. It looks normal because it's less than half the R to R interval, as we discussed in the previous section. But what about this P wave? Remember, if I had just looked at this P wave, I would say, well, what the heck is this little jiggle here? Is that the P wave? Well, you can see that that jiggle is absent in this beat and it's absent in this beat. So it's noise. It's high-frequency noise. The patient maybe moved around just for a fraction of a second. So you really kind of have to scan across and see what your favorite P wave is. Now, notice that this P wave is upright in lead 2. And so that means it is traveling down and to the left of the patient. And that's a good evidence that this is a sinus P. Then what's the rate? 300, 150, 100. And this would be 75, so it's kind of like 85 or so. So what do we have? We have a normal PQRST appearance. The PR interval is normal. The P wave appearance is normal. The rate is in the normal range. What is the normal range for normal sinus rhythm? It should be 60 to 100 beats per minute. Anything less than that, if it's less than 60, we'll call it sinus bradycardia. And if it's greater than 100, we'll call it sinus tachycardia. That's going to be in the chapter after this. We'll talk about those two specific arrhythmias. And it clearly looks like it's the only P wave. If you kind of look halfway in between, you see this T wave, but I don't think there's any suggestion that there's other P waves. So I think it's safe to say that this appears to be a normal sinus rhythm. If you go back to that original ECG, a lot of people will tell you, well, if you look at that circle of axis and you look at if this is lead 1 and this is lead AVF, anywhere in this quadrant should be where the normal P wave winds up. And so it should be positive in lead 1 because it's heading towards lead 1, and it should be positive in AVF. And lo and behold, if you look at lead 1, it's upright. And if you look at AVF, it's upright. So that confirms that this P wave is traveling down and to the left and is in this little quadrant here. Okay, that's just sort of like another way of establishing that the P wave is going in the normal direction. So therefore, it must be starting in the high right atrium and traveling down and to the left. We're at a normal rate. So pretty much this is a slam dunk. We can diagnose this rhythm as a normal sinus rhythm. Let's look at a couple of other examples. If you look at this ECG, you can see the P waves are upright in lead 1 and they're upright in AVF, even though the QRS complex is a little bit different. It's also upright in lead 2, which again confirms that the P wave is down and to the right. What's the rate? If we count off, it's easier to find the rate if you look for a QRS complex that's on a heavy line. So let's do 300, 150, 175. It's just a little bit faster than that, probably 76, because you see this one falls a little bit on this side of the heavy line, and this one is even a little bit more on the side of the heavy line. So the heart rate's 75. The P wave is going in the correct direction. There's only one, so I would say that this is a normal sinus rhythm. It may throw you off if the QRS axis is abnormal, because if you look at lead 2, in this particular patient, the P wave is upright, but the QRS is inverted. So the P and the QRS do not always have to go in the same direction. The other thing I want to point out is that if you think about axis, and you look at the normal P wave axis being down and to the left, which is heading towards lead 2, well, where is AVL? AVL is up and to the left arm exactly 90 degrees from lead 2. And so you'll often see that AVL to P wave would be really small. Well, what does that mean for those of you who work on telemetry units? The lead that you decide to monitor will affect how big the P wave appears. And if you happen to be monitoring AVL, you might not see any P waves at all. If you don't see P waves, don't assume that there aren't any, just change the lead. And sometimes you'll be surprised at how large the P wave appears in another lead. Okay, so let's get some more practice here. Now here's a patient. Now the first thing you see is, it looks a little bit funny. Of course, the biggest signal here is the QRS complex. Okay, so we can label QRS here, and we see that it looks pretty regular. But what's the rate? Now this QRS lands near a heavy line, so let's count backwards. 300, 150, 100. So it's closer to 150 than it is to 100. It's probably about 130 beats per minute. So this is at 130 beats per minute. It's a little fast. The other thing is, look, in lead 2, which we're monitoring, the PR interval is a little bit on the short side. Here it's 3 small boxes or 120 milliseconds. And it's also inverted. So the P wave is upside down. What does that tell us? It tells us that the P wave is traveling away from the feet, because if lead 2 is going down and to the left, this signal is going in the opposite direction. So this is clearly not a normal sinus rhythm. It's not even sinus tachycardia because the rate's 130, but the P waves are inverted. So this is actually an abnormal rhythm. It's a supraventricular tachycardia, specifically an atrial tachycardia, and we'll get into that in a later section. Okay, so you can clearly see this is not a normal sinus rhythm. Okay, one more time, we'll take a look at this. I'm only going to show you the limb leads because I want you to again recognize that if you're only looking at one lead like AVL, you might not actually notice much of a P wave. The QRSs are clearly very large, but the Ps are very small. And if you happen to be monitoring AVL, you may not even see the P waves, but clearly they're up right here in lead 2. Nice and large. The P waves are up in 1 in AVF, and that confirms that it's in the lower left-hand quadrant. And the rate here, we see this QRS lands on a heavy line. So we'll count 300, 150, 100, 75, 60. A little bit faster than that, I'd say 64 beats per minute. So this is a normal sinus rhythm as well. Okay, so now in the next chapter, we're going to talk about sinus bradycardia, sinus tachycardia, and how to recognize those. And we'll get some more practice in recognizing some of the different variations in the sinus rhythm. And so for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick from the Ecg Academy, and we're going to continue our discussion of sinus rhythms. This is an ECG that I came up with for my files. And before you approach it, let's just review what you're supposed to be looking for. You want to look at your P waves, your QRS complexes, and your T waves. Look at the P wave appearance. Make sure that it looks like a normal P wave. Measure the PR interval and make sure you're in the right ballpark between 120 and 200 milliseconds. Calculate the rate and examine the P wave vectors. Make sure that it's upright in 1 and AVF. And if you can't see a P wave, then lead 2 is probably the best place to look for one. And then make sure that it's the only P wave and make sure there aren't any other atrial events going on. So we'll look at this cardiogram right here. If you look at lead 2, you see a very generous P wave here, a QRS complex that looks pretty large, and we'll get into how to diagnose abnormally high voltage on the 12-lead course. And then the T wave looks appropriate. The QT interval seems reasonable. It's less than 1/2 the R to R interval. All right, so, and the P wave is up in 1 and it's up in AVF. That tells you that the P wave vector is down and to the left, so everything looks good. One last thing to look at is the rate. So if we look at this QRS, it's on a heavy line. And so we'll count off 300, 150, 100, 75, 60, 50. So if the heart rate is 50 beats per minute and the P waves appear to be coming from the sinus node, then we have a diagnosis of sinus bradycardia. So sinus bradycardia, by definition, is a heart rate less than 60 beats per minute originating from the sinus node. So the P wave looks normal. It's coming, rising from the normal spot, and it looks like it's traveling in the normal direction. So this is an example of sinus bradycardia. It's a fairly common arrhythmia, one of the most common that we see. It can be due to any number of abnormalities, and we'll talk about that in the section on sinus node dysfunction. But as an introduction to arrhythmias, this is how you diagnose sinus bradycardia. Okay, so now let's look at the next ECG. Now here we have an example of another ECG. Remember, look at the forest first. If you scan across that rhythm strip, you can see the R to R intervals look to be quite regular if you glance across. And now let's find the rate. It doesn't really matter what sequence you do this in, as long as you try to be consistent when you approach every ECG so that you don't miss anything. Don't jump around and figure out rhythm, then rate, then STs, then voltage. And it should be regimented in your own style, and you'll get more practice reading more difficult tracings if you subscribe to my Chalk Talks. This QRS complex lands on a heavy line, so it's 300, 150, 100. And somewhere between 100 and 150. Well, here's a clue. I'm going to give you a sort of a Dr. Nick Pearl. If your QRS complex is not clearly on a heavy line and you're having a little trouble interpolating it and figuring out exactly what it is, instead of measuring the number of milliseconds and dividing it into 60,000, examine two R-to-R intervals and see what the heart rate would be, and then just multiply it by 2. So here's what I'm talking about. Start with this one, ignore this QRS complex, and just what would the rate be if it's here? So we count off 300, 150, 100, 75, 60. So if these two QRS complexes were there, the rate would be 60. But since there's one in the middle, that gives you a rate of 120. Look at that, how easy. So the key is to just measure off two R-to-R intervals, calculate what the rate would be, and then double it. So that's a quick and easy way to get a more accurate measurement of heart rate when your QRS complex kind of lands in between two heavy lines. We've established as a heart rate of 120. There's clearly a nice, healthy, juicy-looking P wave in front of every QRS complex. The PR interval looks to be physiologic. It's probably about 160 milliseconds, just eyeballing it. Is it up in one? It's a little bit up. It's certainly up in AVF. So it would appear to be a sinus rhythm, but greater than 100 beats per minute. And so this is known as sinus tachycardia. So sinus tachycardia arises from the sinus node, but by definition, it's a heart rate of greater than 100 beats per minute. And so it's easy to diagnose sinus tachycardia, just like sinus bradycardia. So now let's take a look at the next example. Now this is a rhythm strip that came off of a telemetry unit. The first thing you should look at is what lead you're recording. And this says lead 2. You can't always trust it, but if the nurse puts the wires on using the correct colors on the right limbs, then it should be accurate. So scanning across, you see a regular QRS complex. If you look at the trees, you can see that the QRSs march through pretty nicely. You can use calipers, but I think eyeballing it is just as easy. The problem is that you do have a little bit of noise here. There's a bit of a high frequency jiggle all throughout this electrocardiogram in both leads. You have lead 1 and you have a V lead. We're not sure where this V lead is located. The R wave looks a little tall for it to be V1. It's more likely V4, V5, something like that. You never know in a telemetry unit where they're going to stick that V lead. But it's this high frequency noise that kind of makes it a little bit harder to recognize what's going on. But you have to kind of look past it. That's the key. Ignore the noise and look in front of each QRS complex for a signal that looks consistent. Because if you have a P wave, then you should be able to get a sense that it's there. It may look a little different from beat to beat because this noise is superimposed on top of the P wave. If you have a P wave like that and you superimpose a bunch of noise on it, then you're going to wind up with something that doesn't look as smooth and as normal as you like. But look at that, sort of towards the end of the tracing, the noise kind of goes away, and then you're left with a very smooth-looking P wave. So we can measure that PR interval from here to here, and it looks like it measures about 160 to 180 milliseconds, still in the normal range. The QRS complex is pretty narrow. The QT interval looks reasonable. You can probably measure it, and it'll likely be at the upper limits of normal. We won't go through those calculations for this video, but you should know how to do that already. And lastly, let's examine the rate. And it's 300, 150, 100, so it's faster than 100. So even not knowing exactly what the heart rate is, we can already call this sinus tachycardia. So this is sinus tachy, or sinus tach, some people call it. The heart rate, to be exact, is probably about 110 beats per minute. So you're doing great so far, huh? It's not that hard. So let's go on to the next one. And this one looks a little bit like the first ECG. I mean, if you'd rather look at the heart rate first, that's completely up to you. The first thing you should look at is regularity. Is it, look at the forest, and these beats seem to be fairly equally spaced, and the heart rate is slow. I mean, I think you start to eyeball it and say, wow, that's slow. It's more than 5 boxes, so it's less than 60 beats per minute, right? It's 300, 150, 100, 75, 60, and this is 50, so it's less than 50. And 40 would be way out to here, so it's about 48 beats per minute, just below 50. So are the P waves normal? Well, they're up in 1. They're up in AVF. It looks like that's the only P wave. Here's a little clue in identifying P waves. When you look at a QRS complex, the change in voltage, in other words, the sharpness or the frequency content is very high. In other words, the voltage changes very rapidly in a very short period of time. So the slope of this signal is very high. And it's almost like, if you look at sine waves, electronic waves of electrical energy, sine waves are measured in frequency. How often do these occur? And that's related to how far apart the waves are. T waves tend to be very low in frequency. In other words, they're very gradual changing in the voltage. The slope of the T wave is actually rather low. It's not a sharp, spiky looking signal. P waves tend to have an intermediate, a little bit sharper signals, a little bit higher frequency signals in a P wave. They tend to change a little bit faster, certainly faster than a T wave, but not as fast as a QRS. So the QRS has the highest frequency component, the quickest, most rapid voltage change. P waves have less higher frequency deflections, but they're certainly faster and sharper and spikier than T waves. So what I always tell people is when you're looking for a P wave, you have to look for a sharp deflection. So in other words, T waves tend to be nice and smooth. But if there was a P wave superimposed on that T wave, then you'd wind up having a signal that kind of looks like that. A little bump or a sharp spike, or sometimes the T wave will look like it has a bite taken out of it. That high frequency, sharp, spiky part of the signal very well may be a P wave buried in there. So I always kind of like say, when I see heart rates below 50, could there be another P wave hidden in there? And one way of looking at it is to look for the midpoint between two P waves and look right in the middle to see if you see something that looks just like that, something that looks like a sharp, spiky signal. And here in this tracing, you just don't see it. And so I think it's fair to say that this P wave in front of each beat is the only P wave, and therefore you're dealing with sinus bradycardia, or sinus brady, as we refer to it. So if this is sinus brady, it fits all the criteria. The P wave is by itself. It looks like a normal P wave, has the expected vector or down and to the left of the patient. The PR interval is normal and the rate is less than 60. All right, so we'll do one more example here. Now this is off of 12 leads, so we know it's definitely lead 2. So here again we have a situation where the QRS complexes are easy to see. They look to be fairly regular. They march on through. And where's the rate? Let's find a QRS that lands close to a heavy line, right about here. And we'll measure off 300, and it would be 150 if it's here, but it's faster than that, isn't it? It's less than 2 big boxes. It's probably about 152 beats per minute. So we're talking about 152 beats per minute. Now we're looking for P waves in front of the QRS complexes. And you'd see this positive deflection right there. And you'd think, well, is that the P wave? I wonder. Well, keep in mind that P waves usually have a flat segment in front of them. You have the P wave, and then there's a PR segment before the QRS complex. So you should see a fairly discrete P wave. Now, not always. You should be looking for a fairly discrete signal followed by sort of a flat segment before the QRS complex. And I would say that the flat part that follows this deflection kind of slopes down a little bit. And that has me bothered. It doesn't look flat to me. And the P wave really doesn't look like a P wave. It's very narrow. It's a very short upward deflection followed by sort of a slopey signal. And don't get fooled into thinking that this is sinus tachycardia, as I'll show you why. If I actually scroll this strip over and look at what happens to it after a little while, you start to see that there's actually a repeating pattern here that looks like a sawtooth. And this we'll learn in a subsequent lesson is atrial flutter. So in fact, you have an atrial rate that's actually faster than 300 beats per minute. And that's typical for atrial flutter. So don't get fooled into thinking that any upward deflection is a P wave. And this is a typical example of an ECG that might have been misread as sinus tachycardia, but in fact it's not. All right, so keep all this in mind as you continue to practice reading ECGs. And in the next lesson, I'll show you one interesting phenomenon that occurs during sinus rhythm, and that's known as sinus arrhythmia. So for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick from the Ecg Academy, and you're thinking, blech, what is that? It's a brain. And we're talking about the heart and ECGs and heart rhythms, and why is he showing us brains? Is that to show how smart he is? No, I'm just teasing. Well, we're going to have to talk about the brain a little bit because the heart and the brain do talk to each other, and it can affect the ECG. And that's what this lesson is all about. It's called sinus arrhythmia. What we're going to do is start with a guy and a brain, and we're going to add part of the nervous system that controls all the bodily functions. This part of the nervous system is called the autonomic nervous system. Now, the autonomic nervous system is kind of like the body's autopilot. The autonomic nervous system controls all the bodily functions, the so-called involuntary nervous system, because it sends signals to all the organs and controls kind of everything on the inside. The sympathetic nervous system is kind of like the fight or flight reflex. It gets activated when you get scared or you get angry or you're in a fight with your boyfriend or girlfriend. And these signals go down the spinal cord and they create connections in the thoracic ganglia and send signals out to all the organs, your liver and your spleen and your intestines and everything. But look at that. The heart is in there someplace, and you need to know that the autonomic nervous system can control the heart. The heart is a team player, and it takes signals from the autonomic nervous system to speed up and slow down whenever the body needs it. This is the sympathetic nervous system, but I have here also the parasympathetic nervous system. Now, the parasympathetic nervous system is like the brakes. It slows things down. The signals go out the 10th cranial nerve, which is the vagus nerve, and those signals spread to the lungs and to the internal organs and the skin, but especially the heart. The heart has a lot of vagal receptors. By the way, the other name for this part of the autonomic nervous system is the parasympathetic nervous system, as opposed to the adrenaline-mediated sympathetic nervous system, which is the fight or flight reflex. Okay, so the idea here is that the heart responds to signals from the nervous system, and the nervous system is constantly changing. The sympathetic nervous system, which kind of speeds things up, and the parasympathetic nervous system that kind of slows things down, are always in a kind of a balance, a yin and a yang. So depending upon your body's needs, your organs will respond accordingly. Now, how does this all tie in with the heart rhythm? If you look at an ECG, what you'll often see in someone here, let's just kind of go over this ECG, okay? We have here a heart rate, if we measure it from this beat, of 300, 150, 175, about 70 to 72 beats per minute. Right here, the P waves are up in 1, and they're up in AVF, and I don't see any other P waves. It's the only one. The PR interval is normal, about 150 milliseconds. QRS looks fine. The QT looks good. So this is a normal sinus rhythm. The thing is, though, that if you take out your trusty pair of calipers and you decide to map around and see what the heart rate is doing, that if you look at the very next beat, it's changed. That's right. If you measure the next beat over, if we take our calipers and we stretch them out so that it encompasses those two beats, and then what you do is you pick up the point and you put it down here on this heavy line, and then you count off 300, 150, 175, 60. It looks like 64. So how did the heart rate go from 72 beats per minute to 64 beats per minute? And then if you look carefully, it kind of speeds up again, and then it slows down again, and then it kind of speeds up. And look, over here, it's even faster. 300, 150, 175. It's like 85 beats a minute here. So the heart rate seems to be changing constantly, and this is known as sinus arrhythmia. It's a normal finding. It happens in normal people, especially young people whose parasympathetic nervous systems are kind of like very active. The vagus nerve has this very acute, very rapid effect on the heart rate, on the sinus rate. So it's able to affect the sinus node even on a beat-to-beat basis. And the most common thing that influences the vagal tone is actually respirations. And you can often see a pattern that varies with respirations. You can see right here it kind of slows down, and then it kind of speeds up again. And here it's faster, so it's faster, and then slower, and then faster again. And so you see the heart rate is varying with the patient's respirations, with their breathing. Okay, so this is a very common finding, and you need to be able to recognize it because there are other things that can almost kind of look like this. Now, let me show you some more examples of this. Okay, this is another patient. Okay, so what you see here are upright P waves, N1 and AVF. The PR interval looks physiologic. It looks like it's within the normal limits. You can go measure it if you are really that interested. The heart rate here in this tracing, you can see it varies. So here's a short interval. Remember, look at the forest, and you can see that it's varying. You have to kind of train your eye to look at the big picture. It almost seems like it slows down right in here, and then it gets faster again over here. Again, with respiratory variation, you have rates between about 78 beats per minute at the fastest, and at the slowest here, it's about 300, 150, 175, about 70. So it varies between 70 and 78. You can usually see anywhere from a 10 to 20 beat per minute increase and decrease, fluctuations in heart rate. And it's cyclical. So this is all normal, and you have to be able to recognize it. But it is an electrocardiographic diagnosis, sinus arrhythmia. We see it quite often. Now, here's a little quiz. Now that we're kind of at the end of the introduction to rhythm analysis and the sinus rhythm, I want you to take a look at this ECG strip, okay? And tell me what the rhythm is. Come on, I'm waiting. Well, you should first realize that there's a mistake here. The first mistake, obviously, is that you are trying to read the rhythm in AVL. And if you have a normal sinus rhythm that's traveling down into the patient's left, then AVL is usually the worst lead to look for P waves. Okay, so is there a P wave or isn't there? Is this Memorex or not? I don't know. But now I'm going to show you the whole 12-lead EKG. Okay, now here's the rhythm strip that we were just looking at in AVL, and you see there's nothing there. You can't see a darn P wave anywhere. But if you kind of glance down to AVF, now it looks like there is a little bit of a bump there. But remember that P waves are not always really huge and juicy. You have to understand that they don't always look like the textbook. That's why I'm trying to introduce you to the idea that not all ECGs look alike. And in this case, the biggest P wave is probably here in lead 2, but it's still tiny. You can barely see it. The other thing is that there's a marked sinus arrhythmia here. look at how it's kind of fast, and then it really slows down in here, and then it really speeds up again. But again, these are gradual changes in heart rate. This is typical of sinus arrhythmia. Since the vagus nerve slows things down, what you have is a very low vagal tone right here where the heart is fast, and then the vagal tone increases, and that makes the heart rate slow down. And then the vagus tone is relieved by changes in respiration, and then you get this subsequent increase in heart rate and so forth. So with the changes in vagus nerve activity, you get abrupt changes in heart rate, but not too abrupt. Okay, you have to remember that if you have the heart rate going along, and then suddenly it goes really fast, that sudden change in heart rate is more indicative of some kind of arrhythmia, whereas the sinus node has gradual changes in heart rate, usually no more than about 20% of the cycle length change in any one beat. Now, I would consider this a marked sinus arrhythmia. This is pretty obvious. It's exaggerated. It's more than you'd see under normal circumstances. So keep that in mind when you're looking at some of these strips. But the point of this EKG is that P waves can be very small, and sometimes you don't even see them. You really have to look at multiple leads to be able to pick them up. And that's why it's important to, if you don't see P waves on a monitor, change the lead. And when you're examining a 12-lead ECG, look at the whole picture, look at everything, and look for P waves in multiple leads. You can see here they're pretty nicely in V1. That's another thing. V1 is a pretty good lead to look for P waves if you don't see anything. And we're going to go into this in a lot more detail when we get into some of the atrial arrhythmias that you can see. So that concludes our discussion of sinus rhythm and its variants. And in later sections, we're going to talk about arrhythmia mechanisms and then get into more detail about what can go wrong with the sinus node and how do you recognize abnormal sinus rhythms. So for the ECG Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick from the Ecg Academy, and we're going to be talking about the sinus node in this section because sinus node dysfunction is a very common problem leading to slow heartbeats and symptoms, and we'll talk about a lot of the physiology here. Well, this is my cardiac conduction animation, and on the left-hand side, you've got some of the action potentials that you'll see in different tissues within the heart. Remember, every cardiac muscle cell is able to generate a little tiny electrical signal because of movement of sodium into the cell, which makes the inside of the cell more positive, and then potassium usually rushing out of the cell in order to restore the normal resting membrane potential. Well, we'll get into the advanced physiology in one of the talks in the advanced level, but for now, let's just talk about the sinus node. Okay, so here's the sinus node in the top of the right atrium. It fires on a regular basis and it sends out electrical signals that generate the atrial depolarization. Those are the P waves. Now, the sinus nodal cells have a pretty unique looking action potential that has a relatively slow upstroke. And in between action potentials, you have what's known as a phase 4 diastolic depolarization. And as I said, I'll get more into that in the physiology talks. But for now, let's just call this slow depolarization in between beats, otherwise known as diastolic depolarization. There are actually ion currents known as pacemaker currents, and these allow the cell to reach the threshold potential, which in this case is minus 50 millivolts. So as soon as that cell crosses that threshold potential, the movement of ions into the cell occurs, giving rise to this action potential. And as that action potential is conducted to the neighboring atrial muscle cells, that's what generates the P wave, which is the atrial depolarization. As you see, this is drawn with little tiny extensions, these little fibers that kind of connect the sinus node with the neighboring atrial myocardium. So this is important because certain types of sinus node dysfunction are actually due to failure of the conduction of that electrical signal out into the atrial myocardium. We'll talk about that later in this section. Most sinus node dysfunction, however, occurs because the rate of firing of this structure within the heart is inadequate to meet the body's needs. In other words, the heart rate isn't fast enough to push enough blood to meet the oxygen needs of all your organs, and so you start to have symptoms. What are the symptoms of sinus node dysfunction? Well, the symptoms include things like fatigue, lightheadedness, shortness of breath, difficulty exercising, and all those are signs and symptoms of an inadequate blood flow. But for the sake of our discussion of sinus node dysfunction, we're going to talk about electrocardiographic diagnoses. And this is a list of the kind of diagnoses you can make on a cardiogram. Sinus bradycardia we talked about a little bit in our initial talk of the sinus rhythm. Chronotropic incompetence refers to the fact that when a normal person exercises, his heart rate should go up. What's the normal heart rate in most people is about 60 to 80 beats per minute at rest. And so this is sort of the normal heart rate. If you're going to call normal sinus rhythm, remember that includes 60 to 100 beats per minute. But for the sake of this discussion, think of 60 to 80 beats per minute as a normal resting heart rate. But when people go to exercise, what happens? Their sinus node should speed up to increase their heart rate and allow someone to run up a flight of stairs or do some heavy work. When the sinus node is incapable of speeding up appropriately, we refer to that as a very specific clinical diagnosis known as chronotropic incompetence. Chrono meaning time. And so what that sort of refers to is the fact that the sinus rate does not speed up appropriately. Like if you had energy level, like this is like exercise on a treadmill, and this is heart rate. You would expect that when the exercise begins, the heart rate should go up. And then when you rest, the heart rate sort of gradually goes back to normal again. Well, in people with chronotropic incompetence, what happens is their resting heart rate may be normal, but they can never really get their heart rate where it should go. And they get exercise intolerance, they get fatigue, they get out of breath with any kind of exertion. So that's one form of sinus node dysfunction, chronotropic incompetence. We're going to talk about sinus pauses, sinus arrest, and even post-tachycardia pauses in the second chapter of this section. And the third chapter is going to be on a diagnosis that you can make known as SA exit block. To start with, let's look at a typical example of a patient with sinus node dysfunction. So here's the electrocardiogram. And if you look at the whole thing, scan it across, you can see that it's fairly regular. If you look for a QRS complex that lands on a heavy line, you see the first one does. So we can count off 300, 150, 100, 75, 60, 50. It's a little less than 50 beats per minute, like 48 perhaps. The next step, of course, is looking at the P waves themselves. Here's a P wave, and it's up in 1, it's up in AVF, and so the quadrant is appropriate. The axis is down in the lower left-hand quadrant, which goes along with the tall P wave in lead 2. So we know this is a sinus rhythm, and it's below 60 beats per minute, so we call it sinus bradycardia. Now, the PR interval looks at the upper limits of normal. I would have to call it about 180 to 200 milliseconds if you take calipers. Now, there is a little bit of noise in this EKG, but, this course is designed to help you look past that noise and read real cardiograms, not just the ones drawn in a textbook. If you look at the precordial leads, you can see easily that the PR interval is clearly in the normal range, here about 180 milliseconds. But the other interesting thing is that you can see an ST segment and a T wave, but this large bump right there, and in fact you can see it nicely in V4, is a wave that follows the T wave, and it's known as a U wave. The U, of course, comes after T in the alphabet. It's an interesting finding that this patient has visible U waves, although they're not so prominent that you would consider them abnormal. So this is just a typical example of sinus node dysfunction taking the form of sinus bradycardia. Now, if this was a 40-year-old long-distance runner, a rate of 48 beats per minute would not necessarily be abnormal. So you have to take the clinical circumstances into account if you're treating the patient. But as far as making an electrocardiographic diagnosis, this would be abnormal. It's sinus bradycardia. Let's look at the next one. Here we have another example of sinus bradycardia, but I picked this one in particular because when you scan across the cardiogram, you should notice that the heart rate suddenly slows down over here in the second half. So the heart rate's a bit faster on the left-hand side than it is in the right-hand side. All the P waves look alike, however, and the P being up in 1 in AVF, tells you that this is a sinus rhythm, and there's a gradual change in heart rate. So we know that this is called sinus arrhythmia, but it's pretty remarkable how you have a heart rate here of 300, 150, 175, 60, just under 60, maybe 58 beats per minute. But then over here, it slows down dramatically to a rate that's actually below 50 beats per minute. 300, 150, 175, 60, 50. It's about 46 beats per minute. If you felt like counting up milliseconds and dividing it to 60,000, I get 1,360 milliseconds. If you divide that into 60,000, and you get 44 beats per minute. So that's a little bit more precise. So you have this sinus arrhythmia going on, but overall the heart rate is indeed less than 60, so we would call this sinus bradycardia as well. Now, sinus bradycardia can get to be pretty severe. Actually, here's an example from a Holter monitor in a patient who was being monitored because of lightheadedness. He was kneeling down in his garden, and he became very lightheaded, almost passed out. And you can see here a fairly steady rate, but when it's this slow, you kind of sort of have to count up milliseconds. So you got 1, 2, 3, 4, 5 is 1 second, 2, 4, 6, 7. So it's about 1,750 milliseconds, which if you plug into your calculator comes out to about 34 beats per minute. Very slow indeed. It's no wonder that this person got lightheaded because their brain just isn't getting enough oxygen given the fact that their heart is going so slowly. Now, in people who have symptoms from sinus node dysfunction, there's a specific clinical diagnosis called sick sinus syndrome. Sick sinus syndrome is one of the more common reasons for a permanent pacemaker to be implanted. Permanent pacemakers are electrical gadgets that are inserted under the skin and stimulate the heart to beat faster. And that's really the best way to treat sick sinus syndrome, assuming that the patient's not on some kind of medication that's making their heart slow. So sick sinus syndrome results in permanent pacemaker implant, and of course that will correct the slow heartbeat and thereby improve their symptoms. The last example I want to give is this from a telemetry unit. You guys and gals may see this if you're working in the CCU or on a cardiac unit. This is someone who clearly has sinus node dysfunction. The heart rate, even when it's going fast over here, is very slow. 300, 150, 175, 60, 50, and then 2 more boxes is 40. So it's about 36 or 38 beats per minute here. You can see down here it slows down to about 20 beats per minute. Well, how did I get that? Well, let's count out the number of seconds in between beats and divide it into 60. Okay, so we start here, we'll count off 1, 2, 3, 4, that's 1 second. 1, 2, 3, 4, that's 2 seconds. 1, 2, 3, 4. So it's about 3 seconds in between beats. And 3 into 60 equals 20 beats per minute. So that's dreadfully slow, and this is a person who would likely have severe symptoms and would need to even have a temporary pacemaker inserted, provided that there wasn't a medication that could be immediately discontinued. So these are some examples of sinus bradycardia that you see in someone with sick sinus syndrome, otherwise known as sinus node dysfunction. And in the next video, I'm going to talk about sinus pauses, sinus arrest, and other examples of sudden failure of the sinus node to fire. For the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick from the Ecg Academy, and we're going to go on with sinus node dysfunction, talking about sinus pauses and sinus arrest. Well, we talked about sinus bradycardia already, and we talked about chronotropic incompetence. Now we're going on to the next section here. Now, here's the strip that I showed you before with that periods of severe sinus bradycardia. Well, what would you call severe, by the way? Sinus bradycardia is a rate below 60, but generally if I see rates below 50, I start to call it severe sinus bradycardia. Rates of 45, 48, that's pretty low. And when you're coming up with an electrocardiographic diagnosis, I would say that's kind of the cutoff, although I think it's a little bit more arbitrary than some of the other definitions that we have. Anyway, here's the strip that was showing very slow heart rates. Let's count this off. That's 300, 150, 175, 60, 50. It's quite a bit lower than 50. It's below 40, probably like 38 beats per minute or so. But you notice that these two beats are fairly even. just like about the same rate as this. But if this is a continuous strip, then you suddenly have this long part where the two P waves are very far apart. And I just want to point this out because this is often referred to as a sinus pause. What is a sinus pause? It refers to a situation where the sinus node sort of takes a nap and you don't get a P wave for quite a period of time, usually more than a second and a half or so. Some people will talk about 1.2 seconds, a sinus pause, and you'll see that written on certain rhythm strips that you'll see on a CCU. Well, a sinus pause basically just means that there's a sudden deceleration in the heart rate, that the sinus rate suddenly drops. Now, a pause can be anywhere up to 3 seconds. And if you count this up, it's in milliseconds, it's 2, 4, 6, 8. That's 1 second, 2, 4, 6, 8. That's 2 seconds, 2, 4, and another half. So it's about 2.5. So people will label this as a 2.5 second sinus pause, and that's fine. These are almost 3 seconds. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. And look at that. So it's not quite 3 seconds. It's 2.9 seconds. That's a 2.9 second pause right there. Okay, but pauses basically we see up to 3 seconds. If it's over 3 seconds, then that's what we refer to as sinus arrest. Now, it's really semantics. It's really just a different definition, but I'll show you what a sinus arrest looks like. In this rhythm strip, it's a different patient. We have a pretty slow sinus bradycardia here. If we count it up, 300, 150, 100, 75, 60, 50. It's above 40. It's somewhere maybe 42 beats per minute or thereabouts. And it's fairly regular, very slow. So you'd call this a marked sinus bradycardia. And then it starts to decelerate even further. You've got a long interval here. It's 1, 2, 3, 4. 1 second, 1, 2, 3, 4. Just about 2 seconds. So that equals 30 beats per minute. Right? Remember that if you take the number of seconds, divide into 60, you get the rate. So 2 second interval is 30 beats per minute. And then look at this long pause. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Holy schmoly. It's more than 4 seconds. So we would call this sinus arrest. Some people won't use that terminology. They'll be very vague about it. They'll talk about a 4.1 second pause. Either one would be correct in the normal vernacular, but strictly speaking, it could be referred to as sinus arrest. But I want you to notice something, that following this pause, the beat that interrupts the pause does not have a P wave in front of it. Well, what does that mean? Did the P wave disappear? Why did the P wave disappear? If there's no P wave in front of it, where did this beat come from? Okay, well, think of it this way. You have your sinus mechanism, which is, of course, arising from the top of the right atrium. But all the cells in the heart are capable of depolarizing spontaneously, aren't they? Your AV node here in the central part of the heart is connected to the His bundle Purkinje fibers, and the AV nodal fibers, those cells are similar to sinus nodal cells in that they're able to spontaneously come to threshold, and they're spontaneously able to fire. And there is a pacemaker current that's going on in AV nodal cells, except the rate is much slower. All right, in a normal sinus nodal cell, the heart rate at rest, as I mentioned, would be somewhere on the order of 60 to 80, but AV nodal cells depolarize at a much slower rate. Generally, AV nodal cells depolarize somewhere in the range of 40, maybe 45 beats per minute. If you cut out the AV node and let those cells fire on their own, under normal circumstances, this is the kind of rates that you would get if the AV nodal cell, or the junction between the atrium and the ventricle, would start to fire at. So what happens if the sinus node doesn't fire? What happens if there's no P wave? What happens if you remove the stimulation from the atrium, from the AV node. Well, the AV node basically will say, hey, what's going on? I haven't seen a beat in such a long time. And so the absence of sinus P waves will result in the AV node firing. That kind of a situation will give rise to something called an escape beat or an escape rhythm. An escape rhythm refers to a lower pacemaker center, such as the AV node or the AV junction, same thing, firing at a much slower rate because of the loss of stimulation from above. And we will talk about this in more detail in the physiology chapter, which you'll find in the advanced course. But basically what this amounts to is a junctional escape beat. Okay? It has the same shape and size as the normal sinus beat. So basically this beat took the same normal conduction pathways. It went down the His bundle and it resulted in a QRS complex that looks exactly the same as the normally conducted QRS complex here. But there's no P in front of it. So it tells you that it started somewhere in the AV conduction system, somewhere in the AV node. This beat arose, and in fact, if you look down here, you'll see that there's a series of beats with no P waves in front of them at a rate somewhere that's in the range of about 35 to 40 beats per minute. And that's where you can basically diagnose a junctional escape rhythm. Okay, a junctional escape rhythm happens when someone develops a problem with the conduction system. This can happen in severe sinus bradycardia, or it can happen in patients who develop complete AV block, which we'll talk about in the next section. So basically, these are beats that came from the AV node, firing at a slow rate. So these beats are about 2 seconds apart. This is a rate of about 30 beats per minute, which is a little bit slow for a junctional escape, but not unusual when you have underlying conduction system disease. Here this patient was going at a very slow sinus rate, and just basically the whole entire conduction system is likely to be diseased here. So even though the normal AV nodal rate may be 40 to 45, it's not unusual to see rates of 30 or so. So this is a junctional escape, and what you have here is a patient with severe sinus node dysfunction, a sinus arrest, and a junctional escape rhythm at a rate of 30 beats per minute. You got that? Okay, kind of a fun strip there. Just recognize the terminology that we use. Severe sinus bradycardia, sinus arrest would be greater than 3 seconds. Now here's another example of a sinus pause. But this is a very unique situation. And it's written down here. It's called a post-tachycardia pause. I want you to notice that there's this pause in the rhythm. If you look along this ECG, look at the forest, you'll find that the heart rate on the left-hand side is a bit faster, a wee bit faster. It's actually looking about 150 beats per minute at parts. These are 2 boxes apart. And then it kind of slows down on this side. And what you have here is a pause with a very flat segment. Now, you might even think that, maybe this is one of those make or break artifacts. Maybe the patient came off the electrodes, one of the wires fell off. But it turns out that this is a particular rhythm disturbance known as atrial fibrillation. And we'll get into this in a later section. But atrial fibrillation occurs when the top chamber of the heart is got an electrical disturbance that results in very rapid, irregular, chaotic activity all going around in different directions. And so instead of seeing discrete P waves, what you see is almost a continuous, irregular, chaotic electrical signal that's going on. And you can see some of that here and here. You can see some of these rapid, irregular signals are here. And so what this patient has is atrial fibrillation, and the AV node is conducting these signals down pretty quickly. So you have this rapid heart rate somewhere in the range of about 150 beats per minute here. It's a little bit slower in this region, maybe 100, 120, but you've got this rapid arrhythmia, right? So this atrial fibrillation is going on, and then suddenly, right at this moment, it stops. The atrial fibrillation comes to a stop, And this rapid electrical chaotic craziness just kind of like goes away. And now what happens is the sinus node is left to pick up the pieces. The sinus node here has to now fire and start a normal sinus rhythm over again. And what you see here is a very nice sinus P wave. You can see it in all three leads, a nice sinus P wave with a normal PR interval and a normal QRS complex. But it took a while, didn't it? It took quite a while. If we count up this time interval, it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's about 2.2, maybe 2.3 seconds. So you have about 2.3 seconds of a sinus pause following termination of this atrial arrhythmia, this atrial fibrillation. So we refer to this as a post-tachycardia pause. Post meaning after. So post-tachycardia pause is, well, it's a sort of a normal physiology, except this is a rather long pause. I've certainly seen longer, but this suggests that the sinus node is a little lazy in coming to the rescue after this atrial fibrillation stops. So this is kind of an exaggerated pause. We usually shouldn't see more than maybe a second and a half or so after atrial fibrillation terminates. So this may be a reflection of a particular diagnosis known as tachycardia-bradycardia syndrome. So tachybrady syndrome is a situation where you have sinus node problems and you also have atrial tachyarrhythmias like fibrillation and flutter. We'll talk about those in the subsequent chapter. But you can have very rapid arrhythmias in the top chamber, but the sinus node also has problems as well. So often the heart rate is either too fast or it's too slow. Well, of course, in this case, what follows are a series of atrial premature beats, which we'll talk about. Here's a sinus beat and then a premature beat again, and then you're back to a sinus beat. So you kind of got a lot of atrial ectopy or premature beats that are going on. This is all stuff that we'll cover in subsequent sections, but I wanted you to know exactly what this is, so that when you see it again in the future, you'll begin to recognize it. Because after all, what I'm trying to do here is teach you to recognize abnormalities that you will see over and over again. So here, evidence of tachycardia-bradycardia syndrome with post-tachycardia pause here of 2.3 seconds. You need to be able to recognize that if you want to make the right electrocardiographic diagnosis. Now, in the next video, we're going to talk about a very special type of pause due to a physiologic abnormality in the conduction of the sinus impulse to the atrium, and that's known as sinoatrial exit block. So I'll see you then. Until then, this is Dr. Nick with the Ecg Academy. Thanks for watching. Hi there, this is Dr. Nick with the Ecg Academy, and this will be the last video that we do talking about sinus node dysfunction. We've gone through the list here of different electrocardiographic manifestations of sinus node dysfunction, and we've covered pretty much everything except this last one called SA exit block or sinoatrial exit block or sinus nodal exit block. Let me explain to you what that is. Now here we have those action potentials of the sinus nodal cells. So imagine those cells are basically firing at a regular rate, right? Which is what sinus nodal cells generally tend to do. Well, one manifestation of sick sinus syndrome is problems with this diastolic depolarization. The pacemaker currents are not what they should be, and what happens is the cell takes a much longer time to fire, and what you have is a heart rate that's much slower. Well, this would be considered a disorder of impulse generation because the signals are being generated too slowly. And that's one of the mechanisms of arrhythmia that we talk about in the advanced chapter on mechanisms. So if the sinus nodal cells are firing too slowly, that will give you sinus bradycardia. But there's another situation that can cause bradycardia and sudden pauses. So here's my animation of the cardiac conduction system. And remember I talked about how the sinus node has these little extensions into the surrounding atrial myocardium. These extensions basically connect the sinus node with the surrounding atrial myocardium. These are little tracts, if you will, that extend into the myocardium. And these tracts behave kind of like sinus nodal cells in that they can fail to fire, and they may not generate enough electrical energy to penetrate the surrounding atrial muscle and initiate a depolarization through the atrium. So what does that mean? It means that the sinus node can fire, but the signal never gets to the atrium. And what happens is the P wave that should be there isn't. In other words, there's a block that occurs as the signal tries to exit the sinus node. And that's why we call it SA exit block. So here's our natural conduction system. And if I show you an animation that I did for SA exit block, you can see there's a sinus beat, there's a sinus beat, and then look, right there, the sinus node fired, but the signal never got to the atrium. So every third beat here, what I've shown you is what happens in sinoatrial exit block is that the sinus node gives off a signal, but it never penetrates into the atrium. Now, what does that look like on an electrocardiogram? Well, what you'll generally see is a sinus pause. Right? There is usually a marked sinus arrhythmia. Here, if you examine this electrocardiogram, you'll see that looking at the forest, there's a tremendous variation in the heart rate. You've got very slow heart rates on this side, then it seems to regulate itself, and then you have a pause here. If you look at the P waves, you can see they're upright in 1 and AVF, and that's fine. So they are sinus P waves. Here you've got very slow beats on the left-hand side, rates in the 30s, basically. And then it looks like the sinus nodal rate picks up a bit. And here you have 300, 150, 100, 75, 60, maybe about 58 beats per minute. So you have this regular rhythm, 58 beats per minute, looks like a perfectly normal sinus rhythm, and then suddenly you have this pause. Now this is the important part. If you take a pair of calipers, and you can move these around here, right? Okay, let's just sort of like take the P waves and measure the P wave intervals. Remember, try to do the beginning of the P wave because sometimes the top part may be arbitrary. So you have a pretty regular rhythm that's going on here. And as I said, if you pick up the calipers and put it on a heavy line, you can count off a little bit less than 60 beats per minute. But the important part is when you put your caliper on this P wave here and you look to see what happened, there is no P wave in this segment of the ECG. It's gone. A P wave did not get generated. But the cool part is that if you make a mark over here and then pick up your calipers and bring it on over, you'll see that the next P wave pretty much occurs right on time. So even though there was no P wave here, the next P wave occurs on time. So what that tells you is that the sinus node did indeed fire right at this location, but the signal never got out to the atrium, so the P wave is missing. But then the next time the sinus node fires, that signal gets out to the atrial myocardium, and you do have a P wave that occurs on time. So this is an indication that you have SA exit block going on. There's another way of looking for this, and that's if you take your caliper and you measure out 2 P waves. So let me resize this thing. Okay, we'll measure out 2 P waves here. So spread your calipers apart and measure out 2 P waves. And then it's very useful to see first are the P's regular? Yeah, they are pretty regular in this location. You can see that this interval is the same as the one that I measured. And then when you put your calipers on, you can see, yes, indeed, there's nothing there. But when you put your caliper on this P wave, look at that. That double P wave interval maps out precisely. Now, this doesn't always hold because there's actually more than one type of sinoatrial exit block. But this is pretty recognizable on a lot of cardiograms in patients with sinus node dysfunction. And you can especially diagnose this when you see marked sinus arrhythmia. That's a clue. When you see sudden dramatic changes in heart rate, most people will consider sinoatrial exit block as the cause. Now, this is known as a disorder of impulse conduction, because here the sinus node may be firing perfectly fine, but the signal is not being conducted out to the atrial myocardium. And that's why you get these pauses because of failure of conduction. As I said, there's a whole section of videos on arrhythmia mechanisms, and you can watch those if you've subscribed to the advanced course. It just gives you a better physiologic understanding of what's going on inside the heart so that you can understand these arrhythmias better and be better equipped to make the proper diagnosis. After all, I want to make you an ECG expert, and that's why you're watching these videos. And so that's my discussion of sinoatrial exit block. I thank you for watching. This is Dr. Nick from the Ecg Academy. Hi, this is Dr. Nick from the Ecg Academy, and this section is about the AV node and the kinds of things that can go wrong with it, otherwise known as AV node dysfunction. We're going to be talking about the different kinds of AV block that we can encounter, and I have to tell you, there's a lot to this, and it's kind of interesting because a lot of the books don't really get into the nuances of AV block, the different types. There's a lot of misunderstanding out there, and my plan here is to try to get you guys to understand this thoroughly. Let's just start with the idea that you have muscle cells, of course, and if you remember, cardiac muscle cells are capable of depolarizing, and for the most part, sodium rushes into the cell, which causes the cell to go from a negative voltage on the inside, depolarizes the cell, so now the inside of the cell is more positive because you've got all these positive charges that have just gone into the cell. And then potassium, which is the predominant ion inside the cell, sometime later rushes out, basically restoring the normal resting membrane potential by making the inside less positive, going back to the resting membrane potential. Well, when depolarization occurs mainly through sodium rushing into the cell, we call it sodium dependent. Sodium dependent cells, characteristically the atrial muscle, the ventricular muscle, and the Purkinje system, and they're recognized by this rapid upstroke. This is known as phase 0, and then we have 1, 2, and phase 3. Phase 4 would be diastole, when certain pacemaker currents will allow certain cells to depolarize spontaneously. You know, all the cells in the heart can depolarize spontaneously to some degree. So those are sodium-dependent cells. But if you notice that the SA nodal cells and the AV nodal cells, the action potential looks a little bit different. They don't have a very rapid upstroke of phase 0 during depolarization. The slope or the rate of change of the voltage is a little bit decreased, and you can see that in AV nodal cells as well. And that's because there are less rapid sodium channels in those cells. And instead, what you have is calcium channels that allow calcium to move into the cell during depolarization. Calcium currents tend to be a little bit slower. And so sinoatrial nodal cells and AV nodal cells are known as calcium dependent. This becomes important because they behave differently. We will talk more about this in the advanced physiology video, discussing the differences between calcium-dependent and sodium-dependent cells. But let's just say, for the sake of understanding the AV nodal physiology, is that the signal takes a little longer to get down the AV node than in other parts of the conduction system. If we bring up our video animation here, you can see that the atrial depolarization spreads rapidly, but the AV node there hangs the signal up for a split second. So there's a little bit of delay in the conduction through the AV node, and this becomes important in understanding what happens when the AV node is incapable of conducting every impulse. Okay, so let's just get rid of this for now, and we're going to talk a little bit about the structure of the AV node. Okay, even though we draw the AV node as sort of a compact structure, it's very complex, and if you look at it under the microscope, you can see there's quite a crazy architecture going on, but it's basically located in the septum of the atrium. So here's the left atrium on this side, the right atrium on this side, and the ventricular septum is here. And the AV node, as you know, is connected to the bundle of His fibers that plunge through the central fibrous body and then split up into the left and right bundle branches. There are specific AV nodal cells known as N cells. This isn't too terribly important, but I want you to understand that there are also transitional fibers. These are long cells that extend out into the atrial myocardium, and they kind of funnel the atrial signal into the AV node. So as the atrium depolarizes, the signal is led into these transitional fibers and enters the AV node, where it then gets delayed. Just so you know, there are other fibers that can enter the AV node at other locations. In fact, when we start to talk about certain kinds of rapid heartbeats, we'll touch more on the role of this slow AV nodal pathway. But for now, let's just ignore the fact that there may be multiple fibers going into the node. The AV node, as I said, delays the signal for a split second, and then the signal rapidly emerges out the other end and goes down the His-Purkinje system into the ventricles. So how do we assess the state of the health of the AV node? From the outside, there's not much you can tell other than simply measuring how long does it take for the signal to go from the atrium to the ventricles. And that gives you a rough idea of the health of this AV nodal conduction system. How do we measure that? We measure it on the surface ECG as the PR interval. Remember, the P wave represents atrial depolarization. The PR segment is usually a flat area that you can see after the P wave and before the QRS complex. The Q wave, this is a nice Q wave here, which is a downward deflection. The R is the upright, and the S is a negative deflection after the R wave. And then, of course, you can see the T wave. There's an ST segment here that we'll talk about in future lessons. But let's just talk about the P and the PR interval. Where does the P wave start? It starts where the P wave just leaves the baseline. Where's the baseline? Well, that's the segment that's in between the previous T wave and this P. Now you can see in this ECG the baseline does drift a little bit, but you can get a sense that right about here is where the P wave begins. And right about here is where the QRS complex starts. Now with some practice you can eyeball these PR intervals, but the best way to do it now at this stage of the game is to use a pair of calipers. So let's bring our calipers over and we'll put the first point right where the P wave leaves the baseline. And the second point we place right where the Q wave starts, where the QRS complex leaves the PR segment. Then we'll take our calipers and put the one point on a heavy line, and we can measure number of milliseconds. Remember, each 1 millimeter small box is 40 milliseconds, so you have 40, 80, 120. This would be 160, but it's like 3/4 of a box here, so you have to call this 150 milliseconds. So the PR interval is 150 milliseconds. That's normal. The normal PR interval should be 120 to 200 milliseconds. That's the normal PR interval. When that interval is outside those rates, then you consider this an abnormality and you can make the diagnosis accordingly. Now, what you have to understand is that under normal circumstances, every P wave is followed by a QRS complex, and that you have what we call one-to-one AV conduction. That means the AV node transmits each atrial signal that it receives down to the ventricles, and you have this kind of normal QRS morphology with a P wave followed by a QRS complex. Okay, but when there are problems with the AV node, one-to-one conduction may not exist anymore, and some of the impulses may not be able to reach the ventricles. This is a condition known as AV block, or atrioventricular block. Now, there are different degrees of AV block, which I'll review right now, and we'll cover each and every one of these in a separate video. Now, the way you have to sort of first approach this classification system is to understand that there are 3 different degrees of AV block. There's first, second, and third degree. The easiest way to kind of get your brain wrapped around these is to first understand that in first degree AV block, all the P waves conduct to the ventricles. It just takes a little bit longer. Now, down at third degree AV block, that means that none of the P waves are conducting to the ventricles, and the ventricular rhythm has to be some kind of escape rhythm, which we touched on in our discussion of sinus node dysfunction. Second degree AV block simply means that some of the P waves are conducting. And we're going to have a long discussion about the different types here, but since some of the P waves conduct, obviously that means that some do not conduct. And that's how you can diagnose second-degree AV block, which indicates a partial failure of AV conduction. Now that I've introduced the classification system of AV node dysfunction, go ahead and watch the rest of the videos in this section. You'll be able to understand all the nuances of this very common electrocardiographic diagnosis. So for the Ecg Academy, this is Dr. Nick. Thanks for watching. And this is Dr. Nick from the Ecg Academy. We're going to be continuing our discussion of the AV node and the electrocardiographic diagnosis of AV block. Just to review, the categories of AV block include first degree, where all the P waves conduct, it just takes a little bit longer. What's the normal PR interval? The normal PR interval should be 120 to 200 milliseconds. So anything longer than 200 milliseconds means that first degree AV block is present. Third degree AV block means that none of the P waves conduct, and we'll be talking about that in the last lesson of this series. Second degree AV block is a condition where some of the P waves fail to conduct, but some get through. Now, this chapter has to do with first degree AV block, and we have a cardiogram up here on the screen, and you can see that it is fairly regular. The QRSs look to be pretty wide apart if you count the rate. Here's one that lands on a heavy line: 300, 150, 100, 75, 60, 50. So we're talking about 50 beats per minute. And when we look for P waves, we do see that there is a P wave in front of every QRS complex. Now, what's the PR interval? Well, it depends on where the P wave starts. Look for the point where it leaves the baseline. And then the end of the PR interval is where the QRS begins. Well, I just want to show you that this ECG happens to have a fair amount of low-level noise. And these little jiggles here are the noise artifacts that I'm talking about. And so the question is, where does the QRS start? Does it start with this little bump, or does it not? And if you look at this QRS complex, it seems to have a little bump, but there is almost like a double bump. And if you look at this first QRS complex, there's no bump. So when you're trying to decide exactly where the QRS starts, if you only have one lead to look at multiple QRS complexes. And I dare say that the QRS really does start with the first upward deflection, that this first bump doesn't count. So if we say the QRS starts with the upward deflection, that would be about here. There are 4 small boxes on this side of the heavy line. There are 4 small boxes on that side of the heavy line. So if there are 8 small boxes times 40 milliseconds each, gives you 320 milliseconds. And that's the PR interval. It's clearly greater than 200, and so we can diagnose first degree AV block. If it's hard for you to count small boxes at this point, it's certainly a bit easier to take calipers to this tracing, and you can place the one tip of the caliper on the beginning of the P wave, the other end on the end of the QRS complex, and when you pick up the caliper and place it on a heavy line, you can sure enough count 8 small boxes, and that gives you 320 milliseconds. So indeed, first degree AV block means the PR interval is greater than 200, but you see, you still have 1-to-1 conduction of each of these QRS complexes. That's 1-to-1 with a little colon there. That's how you write it. Well, let's look at a couple of other examples. Now, here's a 12 lead, but I want you to concentrate on the rhythm strip down here on lead 2. If you kind of scan across, look at the forest first, you can see that the QRS complexes are quite regular, and they're at a rate of, I'd say a little above 75, maybe 76 or 77 beats per minute. You can train yourself to look at where the QRS complex lands on a heavy line, and look at how this one lands just a little bit to the left of the heavy line, and this one again marches a little bit more to the left, and this one a little bit more to the left. So you can see there's a progressive movement of the QRS complexes away from this heavy line. First of all, since it moves away from the heavy line gradually over the course of several beats, it means that the beats are regular. And it also lets you measure the rate in your head a little bit more accurately, because you know it's not 75, it's a little bit faster than that. So we're talking 76 beats per minute. We'll look at the P wave in 1 and AVF, and they're both upright. You can see those P waves right there. I think they stand out pretty nicely. You can see they're very tall and they're very sort of spiky, but look at that PR interval. If we take the QRS complex starting here, and we look at where does the P wave begin, it's almost 2 big small boxes. I think if you look really carefully, you can call us about 340 milliseconds of a PR interval. But notice that the PR interval is constant. If you scan across and look at every QRS complex, the PR interval is fixed. And so we can now make the diagnosis of normal sinus rhythm with a first degree AV block. That little degree sign, like the number of degrees in the temperature, that's how we sometimes abbreviate it. Some people will write out the words first degree, however you prefer. Let's look at a couple of other examples. Now, here's a little bit more of a complicated electrocardiogram, and we're not going to get involved too much with the QRS complexes and what it shows just for you newbies. This is an example of a right bundle branch block, but we're going to cover that in the intermediate course going over 12 lead ECGs. But for now, let's concentrate on the rhythm. If you scan across, you see that the QRS complexes are quite regular at a rate of about 300, 150, 175. It's somewhere between 175, closer to 75. I'd call it at about 85 beats per minute. And where is the P wave? If you look in front of the QRS complex, you really don't see a good P wave there. But keep looking, because here it is. You see the P wave occurs in this ECG just after the previous T wave. So here's the T, and then the P is sort of superimposed on top of it. And this sometimes will fool people into thinking that there's no P wave. But remember that T waves have a very gradual change in voltage, whereas P waves have a little bit more spiky appearance because they have higher frequency components to it. And so what you have to look for is a bump. And that's what you're seeing here, is a bump in the T wave. But you do have to look for it. It's not as obvious as you think. And if you look for the beginning of the P wave, it may be hard to find because it is landing on top of the T wave. But you can sort of extend it down a little bit and call the beginning of the P wave maybe here. And this QRS starts here. So again, we're talking about around 340 milliseconds of a PR interval. So here we have sinus rhythm, upright Ps in 1 and AVF, a sinus rhythm with a first degree AV block. It brings up a good point. If someone asks you what the rhythm is, and you just say normal sinus rhythm, that implies that AV conduction is normal, that you have one-to-one conduction, that the PR is within the normal limits. When you have AV conduction disturbances like this, the rhythm should be normal sinus rhythm with first degree AV block. That's more of a complete label of the rhythm because, after all, you're trying to make a comment of what the entire heart is doing, both the top chamber and the bottom chamber. And this will become much more important when you have degrees of second and third degree AV block, of course. But just get in the habit of mentioning AV conduction when it's not normal. Well, the last cardiogram I want to show you has a very interesting physiologic finding. Well, we talked about the AV node and how the AV node delays the signal slightly. But what you have to appreciate is the degree of delay down the AV node has a lot to do with the atrial rate and has a lot to do with how quickly beats reach the AV node. And here's an example of what I'm talking about. If you look over this cardiogram, you can see there's a slight irregularity in that the QRSs do seem to march through, but then this beat comes somewhat early. You can see that this beat, if you had mapped it out, the normal beat would have occurred here. Instead, this beat comes a little bit early. We're going to talk about ectopic beats in a later section, but this happens to be an atrial premature beat because you can see a P wave that conducts to the ventricles. The P waves in front of all these beats are quite obvious. Following this premature beat, there's a little bit of a pause, and this interval is a little bit longer than the underlying heart rate. And so we refer to this as a compensatory pause. Now, this is going to affect how the AV node conducts, because the AV node will delay signals that are very rapid or signals that are early or premature. It's almost like the AV node isn't finished with the last beat, and if a beat comes in too early, the AV node takes its time to conduct it. These are upright P waves in 1 and AVF, so we're talking about a sinus rhythm. And this underlying rate is 300, 150, 175, 60. So it's about 66 or 68 beats per minute. And when we look at the PR interval, it's clearly long. The PR interval looks to be about 240 or maybe 260 milliseconds and looks fairly constant in each of these beats until you get to that premature beat. When you look at the PR interval of the premature beat, it comes out to be more like 320 milliseconds. So you have about 240 here, but with the premature beat, you get a PR interval of 320 milliseconds. So it's quite a bit longer because the AV node wasn't ready for this beat. Now what happens is you get this compensatory pause. Compare the R to R interval here is 2, 4, 6, 8, about 960 milliseconds here. This interval is more like 2, 4, 6, 8, 10, about 1100. So the AV node had a little bit more time to recover. And look at the PR here. It's actually normal. The PR is about 200 milliseconds with this beat that conducted following a pause in the rhythm. But then with this next beat, the PR gets a little bit longer again and then becomes stable again at about 240 milliseconds, which is where it started. So the reason I show you this is so that you understand that the AV node conduction time will vary depending upon how quickly the rhythm is, and that the AV node at a certain rate will fail to conduct every impulse down. That means you'll get AV block. But in normal people, AV block normally does not occur spontaneously. Although it's true that normal people, and especially people with healthy hearts, can sometimes exhibit brief periods of AV block when they're fast asleep. We can see that on Holter monitors, but that's considered somewhat normal in those patients. But in the next chapter, I'm going to show you how AV node dysfunction can lead to failure of one-to-one conduction, and the AV node will get into a situation where it has to drop a beat every now and then just in order to keep up. And that's what we refer to as second-degree AV block, which is the subject of the next chapter in this section. So this is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy. We're going to go on with our discussion of AV node dysfunction, talking about second-degree AV block. So we covered first degree already. Now we're going to do second degree, and you can see that the classification is a little bit complicated and that there are different types of second-degree AV block. There's type 1, type 2, and there's actually high grade, which a lot of people don't think about. Okay, well, a quick review of the physiology of the AV node. Remember that the AV nodal cells fire because of calcium currents that go into the cells. And so the upstroke of the action potential is a little slurred compared with the His-Purkinje system, like the His bundle and the bundle branches, where the action potential is much sharper and there's a little bit more of a plateau phase. So these two types of cells behave differently. We'll talk more about this in the physiology section, but in the AV node, the cells basically will delay the signal as it passes that signal down towards the His bundle. And if the atrial rate is too fast, what will happen is the AV node will fail to pass the signals down. You'll get delaying of conduction and eventually failure of conduction. And this delay or failure of conduction results in prolongation of the time it takes for the signal to get through. So the PR gets longer. If the PR gets longer, it usually means there's delayed conduction within the AV node. On the other hand, the His-Purkinje system, being sodium dependent and having a very sharp upstroke, behaves more in an all or none fashion. In other words, those cells either conduct it or they don't. So what happens if you have failure of conduction below the AV node is that you'll have AV block without any prolongation in the PR. So the PR is constant in conditions that result in AV block below the AV node. And this physiological distinction between these two cells is responsible for different behaviors labeled as type 1 and type 2. And clinically, the level of the AV block makes a difference. This is something that we'll cover in more detail in one of the advanced talks on physiology. But for now, let me just clarify what type 1 and type 2 second-degree AV block look like. Let's start with this example of an ECG. At first glance, when you look at the forest, you see the QRS complexes appear to be fairly regular. And if you've learned how to count up boxes, you'll find that it's going at about 50 beats per minute. In front of each QRS complex, there does appear to be a pretty clear P wave. And it's up in 1, it's up in AVF. So the rhythm is sinus bradycardia. And now let's take a look at the PR interval. The PR interval starts just before this heavy line, and the QRS complex starts right at this heavy line. So the PR interval here is a whopping 400 milliseconds, twice the upper limits of normal for a PR interval. And when you look across, you can see that the PR interval looks pretty fixed. Or does it? I don't know. I'm starting to get the sense that this is on this side of the center part, this is getting a little bit longer. And if you look at this one, it's even longer still. So somehow the AV node is starting to delay the signal. It's taking longer and longer to get down the AV node. And then what happens? Look at that. A P wave, but there's no QRS complex following that P wave. So this is an example of AV block. The atrium fired, but there's no conduction to the ventricles. So you have AV block now. Is it first, second, or third degree? Well, clearly it's not just first degree because one of the P waves failed to conduct. It's obviously not third degree or complete heart block because most of the P waves do seem to get through. So this is second degree AV block. Now, the fact that the PR is getting longer tells you that delay is most likely occurring in the AV node. And with prolongation of the PR interval, that allows you to make the diagnosis of type 1. With type 1, what happens is the PR gets longer and longer before the beat finally blocks. Let me give you a more typical example of type 1 second degree AV block. Okay, here's an example of type 1 second degree AV block. Remember, in type 1, the PR interval gets longer before a P wave fails to conduct. Now, where do you even start with this ECG? Well, I think it's important to first look at the forest, and what you see here are 2 beats, and then there's a little bit of a longer interval, and then you see 1, 2, 3 beats, and then a longer interval, and another 1, 2, 3 beats, and then a longer interval, and you're starting to wonder if there's a pattern here, a pattern of irregularity. Yes, it's irregular, but what you have is a group of QRS complexes, and then a pause, and then here's another group, and a pause, and here's another group, and a pause, and then it keeps on going. So this is actually known as group beating, and group beating is pretty characteristic of AV block. Now, if we just concentrate on one of these groups, let's start to pick this apart. We'll start to look at the trees. In front of this first QRS complex, you do see a P wave, and the PR interval looks to be a little bit on the long side, like maybe 210 or 220 milliseconds. So if you put a 220 there, and now let's see, are these P to P intervals regular? In other words, do we have just a sinus rhythm? Well, let's take the next P wave, and if you want to make it easier, you can take your calipers, bring them on down, and put them on top of the beginning of the P wave, resize them, and then if you march these calipers out, you can see that the P to P interval is really quite regular. Okay, so the P's are marching on through. The sinus node is firing at a regular rate, and if we try to figure out what rate that is, we put it on a heavy line, and then count off 300, 150, 100, 75, so it's about 78 beats per minute. So we have a sinus rhythm at 78 beats per minute, but what's happening is the PR of the second beat is longer than the first beat. You can see it visually. And I think the best place to look at PR prolongation is at that PR segment. See that segment after the P wave finishes and before the QRS? Look, that segment is getting longer. And if you measure this PR interval, it comes out to be about 280 milliseconds. And now this PR segment is very long, and this PR interval is close to 400. It's like 360. Now what happens is this P wave occurs on time, because we've already mapped these out, and there's no QRS complex following it. So to kind of like shorthand it, we draw a little signal that looks like that, and that means that this P wave blocked. It did not get through the AV node, and it leaves you with a pause. Lo and behold, following that pause, the pause that refreshes, that is, the PR interval gets shorter again, and then it gets longer, and then you block again. And so we have a pattern here. There's a pattern of 4 P waves to every 3 QRS complexes. And this was first described by a guy named Wenckebach. And this Wenckebach periodicity would be expressed as 4:3. That's the ratio of the P waves compared to the QRS complexes. Now, in type 1 second degree AV block, there's always one more P wave than there are QRS complexes. So you can have 4:3, you can have 5:4, you can even have 3:2. There's always one more P wave than there are QRS complexes. Otherwise, it makes it a different type of second degree AV block. Okay, so now how do you make this diagnosis? You see group beating. You see P to P intervals that have to be regular. Remember, the sinus node is just beating at a regular rhythm. It's not that you have premature beats that encounter an AV node that's not quite ready to conduct. Remember, we saw a premature atrial beat that conducted with the first degree AV block in the last lesson. We'll see in the video on premature beats that you can get non-conducted premature beats because it basically catches the AV node with its pants down. But what we have here is a regular atrial rhythm, which is sinus rhythm, marching along at a regular rate. And what happens is the AV node delays the signal progressively, the PR gets longer, and then fails to conduct. Now, there's kind of a way that you can check to see if indeed you have classic Wenckebach, and that is the rule of the pause. The pause should always be less than 2 times the previous R to R interval. So if we take our calipers and move them on over and check this R to R interval, well, let's adjust those so that we get the R to R interval exactly. And then if we move those calipers over and see what's the size of this pause, we can note where the tip of the caliper falls here and then move it on over, and you can see, look at that. That if you take the previous R to R interval, that the size of the pause is always less than 2 times the previous R to R interval. So if you measure that over, it comes out to there. The pause is less than 2 times. And that's a rule that you should be able to prove if you want to make the diagnosis of type 1 second degree AV block. We used to refer to this as Mobitz 1, but I think that type 1 is a more generic term, and we should use type 1 and type 2 instead of Mobitz. In terms of AV node classification, we've now covered type 1 second degree AV block, and you've recognized what it looks like. Let me show you another example. Okay, here's a rhythm strip that came off of a CCU, and when you first kind of glance at it, you're trying to figure out, well, what's going on? And what you should be able to see is a slight irregularity if you look at the whole forest. If you map out the QRS complexes, you see that this interval is a little bit longer than this one. And then it gets shorter again, and then it gets longer. So it's almost like you're alternating short, then long, then short, then long. So there is a bit of a pattern to it. It's a regular irregularity. When you see this, think group beating, because what you're talking about really is a group of 2 and a pause and then another group of 2. Well, if there are 2 QRSs in this group, how many P waves should there be? Well, there's always one more P wave than there are QRSs. So let's see if we can prove 3 to 2. Well, where are the P waves? Look around, and you should be able to see that this is a P wave here. Now let's look for a signal that looks just like that, and you see it right there. It's kind of at the tail end of the T wave, but remember, compare this T wave with that T wave, and you can see the two are distinctly different. And remember what I told you about P waves being sharp and spiky compared to T waves. So you have this one here, and then you have this sharp spiky guy right on top of the T wave. Do these map out? Well, let's see. If we resize our calipers and move them on down, they do indeed appear to map out. This one's a slight bit early and this one's a slight bit late. But my point is that when you look at the relationship between the P's and the QRS's, you see this PR starts out long at maybe 300 milliseconds, but it gets much longer here. And then this P wave fails to conduct. And then what happens is your PR gets short again, it gets longer, and then this one fails to conduct. So what you have here is 3 to 2 winky back or type 1 second degree AV block. Now what happens in type 2 second degree AV block is you don't get the PR prolongation. The P to P interval is still regular. And so if you map these P waves out, I won't bother with the calipers, but trust me, they're perfectly regular. And you have group beating here. You have a group of 2, and then there's a pause on either side. But when you examine the PR intervals carefully, especially look at the PR segment, the PR interval doesn't change, and then this beat blocks. And the PR following the pause is about the same, and then you have a fixed PR here, and then you block again. So the PR never really changes. If we get out our trusty calipers and look at the R to R interval, you should be able to see that the R to R interval from here is exactly 2 times the previous R to R interval. So when the pause is exactly 2 times the previous R to R, that tells you that the PR is not changing, and that what you have here is type 2 second degree AV block. Now type 2 second degree AV block suggests that the block is below the AV node in the His bundle and the bundle branches. And sure enough, the QRS complex is a bit wide. It's more than 120 milliseconds in duration. So this is a patient who has significant disease below the AV node, and his conduction system is failing in a very characteristic way. Okay, well, second degree AV block is a big subject, so we're going to go on to the next section because we talked about type 1 and type 2. Now, high-grade AV block is unique, and it's defined as second degree AV block, but worse than 3 to 2. In other words, 3 to 2 is the worst that you can get for type 1 or type 2. So that's not what this is. What you have is 2 to 1, 3 to 1, or anything higher than that. Here's an example. If you look at this ECG, you can see the QRSs look regular through the whole thing. Yes, indeed, they look fine, although they look kind of slow. The rate here is in the 40s. And when you look in front of each QRS complex, you do see that there's a P wave. But if you look very carefully, midway between these two P waves, there's another one. Okay, this is something that you can't miss. Those P waves here are not conducting. So you have this conducts and this blocks, this conducts, this blocks, and every other impulse is blocking. Now, you can see them actually very nicely here in lead V1. Now, a lot of people will immediately say, well, this is type 2 because it's 2 to 1. And they'd be wrong, because 2 to 1 is neither type 1 nor type 2. The reason is you really don't have two PR intervals in a row that you can tell whether the PR is getting longer or shorter. You only have isolated ones. In order to call type 1, you have to have two PR intervals in a row that you can tell that it's getting longer. Or in the case of type 2 second degree AV block, the PR interval doesn't change, and then you get a block beat. So it's either fixed or it's getting longer. Here, you don't have either of those situations because you only have single PR intervals to examine. So you cannot make the diagnosis of either type 1 or type 2. It is in its own category. That is high grade. Some people call it advanced AV block, or high grade is really my favorite expression. So high grade AV block is in its own category. And that's the way I wrote it, high grade. Okay? You can get very high grade periods of AV block. Okay, what you see is a sinus rhythm marching along. If you look at the PR interval, it is a bit long. It's about 280 milliseconds, but it's fixed. It doesn't really change. And then you have a P wave that fails to conduct, but it sets off a whole series of blocked P waves. So this is known as high-grade AV block. It's not really complete because you had conduction here, and then at the very end you have some more conduction, but you see this episode, otherwise known as a paroxysmal, so we call it paroxysmal high-grade AV block. It's a very specific diagnosis. You don't see it too often, but it is something that you should be able to recognize on an ECG. But the idea is anything of 2 to 1 or better, 3 to 1, 4 to 1, those kinds of situations are referred to as high grade and are neither type 1 nor type 2. I know that was a long lesson, but there is a lot of confusion when it comes to second degree AV block. In the last chapter of this section, I'm going to talk about complete AV block and how to distinguish it from other similar arrhythmias, so I'll see you in the next video. Meanwhile, this is Dr. Nick for the Ecg Academy. Hi, this is Dr. Nick with the Ecg Academy, and I'm going to be finishing my discussion of AV node dysfunction with, yeah, you guessed it, third degree AV block, also known as complete AV block or complete heart block. So what does complete heart block mean? Well, as I mentioned, first degree AV block means all the P waves conduct, it's just that the PR interval is longer than 200 milliseconds. With second degree AV block, some of the P waves fail to conduct, and depending upon if the PR is variable or if it's fixed, it gives you either type 1 or type 2. High grade AV block is either 2 to 1 or 3 to 1 or something along those lines, but some are still conducting because second degree AV block means only some of the P waves block. Well, third degree AV block means none of the P waves are able to get through the AV node, and so the ventricles are not getting the signal. Does that mean you have no heartbeat? Well, usually not. Otherwise, you wouldn't be doing an electrocardiogram, you'd be doing an autopsy. Okay, maybe that's morbid, but if you remember my discussion of sinus node dysfunction, if the ventricles don't see a heartbeat, then what happens is a lower pacemaker center will pick up the slack. So in the case of sinus node failure, severe sinus bradycardia, usually the AV node will start to fire and you'll have a junctional escape focus. As you know, junctional means the AV node It's the junction between the atrium and the ventricle. Those escape rhythms are usually for the AV junction in the range of 40 to maybe 45 beats per minute. But what happens with AV block is you'll get an escape rhythm, and it could be from the low junction. If you recall, the AV node is connected to the His bundle, but there may be an area down in the lower part of the AV node that would be able to take over. So you can sometimes see escape rhythms in the range of 30 to 35 beats per minute coming from the AV junction. If the AV junction is diseased also, then you can have escape rhythms that are arising from the Purkinje systems, from those fibers down in the ventricle. And those usually give rise to very slow escape beats with wide bizarre QRS complexes known as idioventricular escape rhythms. Idioventricular means it's coming from the ventricles, and usually you'll see rates of 25, maybe 30 beats per minute in idioventricular escape. Those are generally very wide-looking escape rhythms. It means the ventricular rhythm will generally be regular because it's coming from some escape focus. The P waves, of course, will be marching on through, and none of them will be getting through to the ventricle. All right, well, how does that look? Well, here's a good example of complete AV block. If you look at this electrocardiogram and scan across with your eyeballs, look at the forest and you'll see that the QRS complexes are there. And they look to be fairly regular, although rather slow, right? Let's find a QRS that lands on a heavy line. This one's pretty close. So 300, 150, 100, 75, 60, 50. And we're in the range of like 42 to 44 beats per minute. So the ventricular rate's about 44, and when you look around for P waves, you see P waves, but they seem to be just kind of hanging out here. There's one, and scan across, and oh, there's another one. And but wait a minute. Here's one too, but when you look at this QRS, it looks like there's a P in front of it. Well, does that mean it's a normal sinus rhythm? Well, there looks like there might be a P in front of this one, but if you look across, there's no P here. Well, actually, you can see a little piece of the P that's occurring simultaneously with the QRS complex. And so what you have here is an atrial rate that seems to be marching on through, and you have to look at the atrial rate. Well, how do we figure out the atrial rate? Here's a P wave. The beginning of it starts on a heavy line. So let's count it off. 300, 150, 100, 75. So it's about 70. So the atrial rate is 70 beats per minute. And if you look at the P waves, they're up in 1 and they're up in AVF. And so what you're seeing here is a sinus rhythm at a rate of 70 beats per minute, but none of these P waves are getting through to the ventricles. Every single one is blocking. So as a result, the ventricular rhythm is a very slow escape rhythm at 44 beats per minute. It's perfectly regular. And it's coming from where? From the ventricles? No, because it's narrow. Look at how narrow it is. It looks like a normal QRS complex. And so it must be taking the normal route of conduction down the bundle branches and to the ventricles. And so we would consider this a junctional escape because it's narrow, it's normal appearing, and it's at a rate of 44 beats per minute, which is about right for the AV junction. So to summarize, what do we need to say complete heart block is present? We like to see regular P to P intervals because, after all, we're usually dealing with a sinus rhythm of some sort at a rate anywhere between 60 and 100 and something beats per minute with upright P waves in 1 and AVF. So we have a sinus rhythm and the P to P interval is regular. The R to R interval should be regular as well because if you have complete heart block, then you should be dealing with an escape focus of some sort. And that is not influenced by what's going on in the atrium. The two chambers are not talking to each other. You have to make sure there's no relation between the A's and the V's. So even though there may be P's that don't conduct, make sure you don't have some kind of fixed relationship like 2 to 1 or 3 to 1. And finally, this is very important, the atrial rate should be faster than the ventricular rate. If there appears to be no relation between the A's and the V's, but the V rate is faster than the atrial rate, we call that AV dissociation. And that's something we'll discuss when we get into ventricular arrhythmias, like accelerated idioventricular rhythm and ventricular tachycardia. Okay, so for now, let's get some practice up here. So here's an ECG from my archives. Again, when you look across at the QRS complexes, you see that you can just eyeball them and see that they are regular. They march on through. You can take calipers to make sure that I'm not lying, but we have here a very slow rate. We'll count up milliseconds this time. 2, 4, 6, 8. 1 second, 2, 4, 6, 8. Almost 2 seconds. So the rates, if it was 2 seconds, it would be 30 beats per minute. So it's somewhere in the order of 32 or 34 beats per minute. The QRS is a little bit wide. This could be a junctional escape rhythm, or it may actually be a rising from a little further down in the conduction system. But this is clearly an escape rhythm. Where are the P waves? We're looking for P waves, and probably lead 2 is the best place to look for P waves because they generally will tend to be largest. Remember, from the sinus node, the vector is going down into the patient's left, so that would be lead 2. The other place you can look for P waves is V1. That's a nice lead to look for P waves because they generally tend to be kind of large there. So here are the P waves. Here's one. You can see another one peeking out from the QRS, and here's one, and here's one. And so they're marching on through. The atrial rate here is about 300, 150, 175, maybe 76 beats per minute. So you have a sinus rhythm at 76 beats per minute with complete heart block or third degree, you can say third degree AV block, and a slow junctional escape at about 32 beats per minute. And that would be the rhythm diagnosis here. Complete heart block is generally easy to diagnose, but you'd be surprised sometimes it's overdiagnosed. Let me show you one example. Here's an ECG that initially was thought to be complete heart block because look at how slow the ventricular rhythm is. Look at that. If we count off milliseconds, we have 1, 2, 3, 4. That's 1 second. 1, 2, 3, 4. That's 2 seconds. So it's less than 30 beats per minute. And it looks pretty narrow. So we got a very slow junctional escape at like maybe 26 or 28 beats per minute. And when you start looking for P waves, you say, oh, look at that. There's a P wave that's just hanging in the breeze. So then obviously blocked. And this one, look, the PR is really long, and then here's another one that blocks. So you'd say, well, the P to P interval seems to be regular, but then what you say, wait a minute, the R to R interval is not exactly regular. And so what do we have here? Well, look at the PR interval. It looks to be fairly fixed, and it looks the P is in the same relationship with the QRS complex in these 3 beats. And then you have these are blocked. So you'd say, aha, well, I know what this is. It's not complete heart block. Instead, it is, well, a lot of people would call this Mobitz 2 because it's 2 to 1. Right? Okay? But what did we say in the last video? That 2 to 1 AV block is not Mobitz 2. 2 to 1 AV block is in its own category. We call it high grade. High grade AV block includes 2 to 1, 3 to 1, 4 to 1. It's also called advanced AV block. So from here to here, at least, you have high grade AV block. It's neither type 1 nor type 2. Well, I want to show you something really cool. You see this area right here? Well, let me just blow this up here because you see there are 2 P waves in a row that conduct. And if we look at that carefully, let's blow that up. So this group of beats here is the same group of beats that I have down here. I just sort of blew it up. You can see with nice high resolution. There's a fair amount of noise, little tiny bit of electrical artifact in the baseline. But you can see the P waves, okay, which I've already marked here and here and here, and they march through precisely. Now let's look at the PR interval. Well, it kind of looks fixed, but let's get out our good buddies, the calipers. And what you want to do is you want to place those calipers right at the beginning of the P wave and open them up to get right at the beginning of the QRS complex where it just leaves the baseline. Okay, and you have a PR interval there that's about 7 small boxes. So that's 280 milliseconds, right? 7 times 40. Good. Now let's march on through and let's see what happens when we put the point on this P wave. Oh, look at that. It looks like the PR interval here is a little longer. Well, if the PR gets longer, like this, if you see the P is shorter, it's 7 boxes, and then here it's more like 8 boxes, and then it blocks. What do we call this? This is type 1 second degree AV block. Type 1, or a winky back in this case, is what occurs from here to here. Well, what does that tell you? It tells you that most likely the block is in the AV node and not below the AV node, because the AV node delays the signal as the signals get down, but block below the AV node would be expected to have a fixed PR interval because of the all or none behavior that you see with the His bundle and the bundle branches. So this is really winky back. So how do we get from type 2 to type 1? Well, you can't have both. And that's the point. This is not type 2. This is advanced 2-to-1 block, which is likely occurring in the AV node itself. And then what happens is the AV node conduction improves just a little bit in order to conduct 2 P waves in a row. And then you're able to demonstrate that the PRs are getting longer, so you know that this is type 1 right in this location. But it shows you that the degree of AV block can change from 1 second to the next. What you have to keep in mind is the physiology of it all. How does the AV node behave? It exhibits slowing of conduction with each progressive signal, whereas the His-Purkinje system is more of the all or none kind of behavior that you would characterize as type 2 second degree AV block with a fixed PR interval. All right, so we're getting into some major physiology here, but I just wanted you to understand the difference between type 1, type 2, and complete, and don't get confused when someone hands you a strip with 2-to-1 block and asks you, well, what is it, Mobitz 1 or Mobitz 2? It's neither. And complete heart block is obviously a whole different animal. Okay, the last ECG I'm going to show you in this section is pretty impressive. In fact, this is a patient who came to the emergency room with a heart rate of about 20. I was called to see him, and it appeared that he had this wide QRS complex going at an extremely slow rate. Here, if you figure it out and calculate it, it comes out to be 22 beats per minute. Wide QRS complex, but where are the P waves? Well, there were no P waves. This is an arrhythmia known as atrial fibrillation. There's a whole section about atrial fibrillation later in this course. But what's happening is the top chamber is kind of jiggling it around at a rapid rate, and what you see is the top chamber just kind of looks like there's continuous electrical activity going on. But with atrial fibrillation, the hallmark of that arrhythmia is that it's irregular. It's generally irregularly irregular. And not to open up a whole can of worms, we will talk about that in great detail in that section. But when you see a very slow, regular atrial fibrillation, this is often called regularization of atrial fibrillation. You have to, at that point, diagnose complete heart block, because normally you would see an irregularity, but what this is an idioventricular escape rhythm. So this is idioventricular escape rhythm, and it's going at a rate of about 22 beats per minute. And it's there because the AV node has failed in a big way, and this was a patient who wound up getting a temporary transvenous pacemaker inserted on Thanksgiving Day, in fact, and then he subsequently had a permanent pacemaker implanted. So what I wanted you to appreciate is the idioventricular escape. The QRS is wide. If you measure it, it comes out to be about 140 milliseconds. It's bizarre looking. There's these weird, bizarre T waves that you're seeing, and this is a patient with severe conduction system disease who wound up needing a permanent pacemaker. So with that, I'll end my discussion of AV node dysfunction. I think we've covered most of the bases, and I hope you have a good appreciation of how to diagnose AV block. We'll go on to the next section and start to talk about specific arrhythmias, including ectopic beats, in this basic section of the Ecg Academy. This is Dr. Nick. Let me help you become an ECG expert too. And thanks for subscribing to the Ecg Academy. Hi, this is Dr. Nick from the Ecg Academy, and this section is entitled Interventricular Conduction Disturbances. So we're going to be talking about things that slow down the electrical conduction through the ventricles. And what happens is your QRS gets wide. But before we start looking at tracings, let's review the cardiac conduction system. Remember, there's a sinus node that fires on a regular basis, and these electrical signals spread rapidly across the top chamber, giving rise to a P wave. That electrical signal then enters the AV node through transitional fibers. The AV node delays the signal slightly and then passes it down to the His-Purkinje system. So you have the main bundle of His here. You've got the bundle branches, including the right bundle branch that goes to the right side of the heart. Remember, this is the right ventricle. And you've got the left bundle branch that goes down the left side. Now, the left bundle branch splits up, and in many people, we can identify a kind of a functional half a bundle, what's known as a hemifascicle. There's an anterior one and there's a posterior one. And in the intermediate course, when we talk about hemiblocks, we'll get into more detail with that. Any disturbance in the electrical conduction through the ventricles is going to wind up making the QRS longer. Why is that? Remember that the P wave is the atrial depolarization and the QRS complex is ventricular depolarization, so the width of the QRS is a reflection of how long does it take for the electrical signal to get around to the ventricles. And when there are problems with the electrical system, branches of this bundle branch system or the Purkinje fibers that don't work, it takes a little longer. What you need to understand is that Purkinje fibers have a very rapid speed of conduction. These things conduct at literally meters per second. So that's why these fibers are well suited for interventricular conduction, because the signal zips around so rapidly that it allows a very organized synchronous contraction of the ventricle. So what happens when one of these bundles doesn't work? Well, let's say if this bundle doesn't work, then part of the ventricle here doesn't get this signal rapidly. So what happens is you get cell-to-cell connections, through those gap junctions that allow the signal to get into this area, but it takes a lot longer. So the signal, for example, would have to come down this fiber and then very slowly conduct, well, relatively slowly conduct, at least compared with the rapidity of the Purkinje system. And that just takes a little bit longer. And so what happens is you get widening of the QRS complex, and that's how you diagnose an interventricular conduction disturbance. Okay, let's take some examples. Here is an ECG that's fairly normal. I placed it so that the beginning of the QRS complex happens to be on this heavy line. So if you measure back, the PR interval is 3.5 boxes. That's 140 milliseconds. The QRS duration here is 2 boxes wide. So each box, remember, is 40 milliseconds, and that gives you 80. Well, the normal QRS duration should be somewhere around 80 to 120 milliseconds. So this being 80 milliseconds, that's fine, and that really means that the electrical signal is really zipping around the ventricles and that the conduction system appears to be fine. Okay, well, what happens when you look at the QRS complex and it just looks funny? It looks weird. It's got little notches, it's got little wide parts, but when you take the total duration of the QRS complex from this heavy line to here, it's just under 120 milliseconds, maybe 110. So the duration here is normal, but it just looks like it takes a funny turn somewhere. It could be that some of these little branches here aren't working right, and the signal may have to go down one branch and then turn around, like, backing up into a steep driveway. So this is known as a nonspecific interventricular conduction delay, or nonspecific IVCD. Now, some people call it interventricular conduction disturbance. Some people call it delay. It really kind of means the same thing, that something is happening in the conduction of the electrical signal through the ventricles that makes it look a little funny. But it's still less than 120 milliseconds. So this is a common electrocardiographic diagnosis, a nonspecific IVCD. But you can see it's a little bit widened. It just looks a little funny, but it's not classic for any other particular problem. Well, we're going to talk about a number of different IVCDs in this section to introduce the different kinds of IVCDs that you may encounter, and then in the last chapter introduce the concept of a functional IVCD. And so this is Dr. Nick from the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to continue our discussion of interventricular conduction disturbances. In this chapter, I'll cover the types of IVCDs we can diagnose on a rhythm strip. First, a quick review of what we covered in the first chapter. The Purkinje fibers have very rapid conduction, and anything that disturbs the normal Purkinje system activation is going to affect the QRS complex. Widening of the QRS indicates that there's a delay in interventricular conduction, and the generic term for that is an interventricular conduction delay or interventricular conduction disturbance. Now, I showed you what it looks like when you have just a minor problem in your Purkinje system. So what happens is the signal has to kind of slowly make its way through cell-to-cell conduction, which occurs much more slowly than it does through Purkinje fibers. And that delays the signal, and what you get is this kind of weird-looking widening. Now, this QRS complex wasn't over 120 milliseconds in duration. This is only about 110 milliseconds, and we consider this a nonspecific IVCD. We frequently see that as a diagnosis on 12-lead ECGs. In fact, there's going to be a whole section on IVCDs and bundle branch blocks in the intermediate section for those of you who want to be able to recognize this on a 12-lead. But let's see what happens if a larger branch gets affected. For example, when there's delay down the right bundle branch system, let's say the right bundle branch does not get the signal where it needs to go in time. What happens is the left side of the heart activates first, and then you wind up with very slow activation of the right ventricle. Now, the right ventricle is a pretty thin-walled structure, and it doesn't create a lot of voltage, but we can see it on the cardiogram. And often what we see is widening of the QRS complex, but the first part of the QRS complex looks fairly normal. You got a little Q here and a nice tall R, and it's this wide S wave, this negative deflection at the tail end of the QRS complex, that allows you to diagnose a bundle branch block, in this case a right bundle branch block. And we'll get into more detail in the intermediate section, but for the time being, if you notice that the QRS complex has become long, in fact, here it's about 180 milliseconds in duration, and you have this terminal S wave. The beginning looks fairly normal, and then you have this terminal S wave, which is pretty characteristic of a right bundle branch block, because the left ventricle is depolarizing normally, and it's the right ventricle that causes widening of the QRS complex. That's one type of IVCD, and when you see something this wide, it's greater than 120 milliseconds, then we can generally diagnose a bundle branch block this way. Another pretty characteristic bundle branch block pattern is what we refer to as rabbit ears. You can see this QRS goes up, and it's notched at the top. And this is pretty characteristic of a bundle branch block as well. Depending upon what lead we're seeing this in, it can allow us to make the diagnosis of either a left bundle branch block or a right bundle branch block. But I just want you to recognize this pretty characteristic rabbit ear pattern, along with the fact that the QRS here is about 150 to 160 milliseconds in duration. This is a classic example of a bundle branch block pattern with widening of the QRS and the rabbit ears. We can sometimes see this with the right bundle branch block and sometimes a left bundle branch block as well. Okay, so now let's take the example where the left bundle is diseased and that the signal has a hard time getting down the left bundle. With a left bundle branch block, most of the left ventricle doesn't get the signal rapidly, and it can cause very extreme disturbances in the QRS complex. So what usually happens is the signal will go down the right bundle branch and then have to very slowly make its way all around the left ventricle, and you get very bizarre disturbances in the QRS morphology. Often the QRS is extremely long and large, and it looks pretty bizarre. Here you can see the QRS duration is 170 milliseconds or so, and the slope of the electrical signal, often the downslope is very slurred, and that's just a reflection that it's taking a long time to get around the left ventricle. So this widening and this sort of characteristic deep S wave, or sometimes there's no R here, sometimes it's a QS pattern, is pretty characteristic of a left bundle branch block. Now there are a couple of other things that can disturb the electrical signal's ability to get around the heart in a rapid way. Let's say, for example, this patient has complete AV block and they required a permanent pacemaker. Well, what is a pacemaker anyway? A pacemaker is an electrical device that's inserted through a vein, and what happens is there's a wire that's inserted into the right ventricle, and this wire provides the electrical signal that keeps the heart beating. So the electrical signal arises from the tip of the pacing wire, which is generally located in the right ventricle. What happens is this disturbs the electrical activation of the left ventricle. Because the left ventricle has to depolarize very slowly, what you get is a very wide, bizarre electrical signal, a little reminiscent of a left bundle branch block pattern. But this is very wide, here 200 milliseconds in duration. But what you see in the beginning of the QRS complex is a very sharp, narrow signal, and that's known as a pacemaker spike. The spike is the electrical signal that's delivered to the right ventricle, and that's what starts the QRS complex going. So being able to recognize a paced rhythm has a lot to do with seeing the spike, but when the pacemaker is working, the QRS will be very, very wide and bizarre looking. And this is one type of interventricular conduction disturbance, but you wouldn't necessarily call it that. You would basically say this is a paced rhythm. We refer to the QRS complex as being captured by the pacemaker. That's the term that pacemaker specialists use. So this is a captured QRS complex with a pacing spike, and that's why the QRS is so wide. There's one last medical condition that can cause widening of the QRS complex that I'd like to cover in this chapter, and it occurs in patients who were born with a congenital abnormality. They were born with some kind of electrical short circuit that bridges the atrium and the ventricle somewhere on the side where the AV groove runs around and separates the top and bottom chambers. This is kind of like a short circuit that allows the signal to jump across from the atria directly to the ventricles without having to go through the AV node. This short circuit is known as an accessory AV pathway, and because this part of the heart winds up getting the signal earlier than the rest of the heart, the condition is known as pre-excitation, referring to the fact that part of the heart is being excited prematurely. The other name for this condition was named after the three people who first described it, and that's Wolff, Parkinson, White. Now, what you generally see on the cardiogram in Wolff, Parkinson, White is that the QRS complex starts early. Think of it this way. In a normal heartbeat, you have a PR segment, and then the QRS starts, and it's a very sharp upstroke in the QRS complex. In people with pre-excitation, the P wave occurs on time, but because part of the ventricle is excited early, the QRS complex starts early. And because you're not using the Purkinje system, and that conduction occurs very slowly through these cell-to-cell connections, the QRS complex is not sharp in its upstroke, but rather slurred. And so the QRS is generally wider than it should be, and then there are often T-wave abnormalities that go along with it. In essence, what happens is the QRS widens at the expense of the PR interval. So here, this EKG is a typical example of pre-excitation. If you measure back from here, you can see the PR interval is short. It's only maybe 100 milliseconds. The QRS complex is wide. It's just over 120, about 130 milliseconds here. And the upstroke is somewhat slurred. See, it's not a sharp rapid change in voltage over time. It's a very slurred upstroke. This is referred to as a delta wave, and in the advanced course I'll be talking about WPW in great detail. But this is something that you should be able to recognize even on just a rhythm strip, is a short PR, a widened QRS, some STT abnormalities are part of it as well. And the fact that the QRS complex starts very gradually with a sort of a slurring of the upstroke of the QRS complex, and referred to that as a delta wave. A triangle like that is the Greek symbol for the letter delta. By the way, another name for all of these interventricular conduction disturbances is called aberrancy, or aberrant conduction. And I'll talk more about that in the next video. Well, now that we've discussed all different types of IVCDs, in the next chapter I'm going to give you some examples on real ECGs and then discuss the notion of a functional IVCD or a functional bundle branch block, which means that it's not blocked all the time, only under certain circumstances. So for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we'll finish our discussion of interventricular conduction disturbances. I want you to understand a little bit about the action potential of the heart. Remember, if you take a heart muscle cell and you measure the inside of the cell using a little tiny tube, you can determine that the inside of the cell starts out being more negative. As you can see, the resting membrane potential is somewhere around minus 80 millivolts. And then with the action potential going through the different phases, the upstroke is known as phase 0. and then it comes down a little bit, which is phase 1. The plateau phase is 2, and the repolarization is phase 3. This is basically movement of sodium into the cell, which makes the inside of the cell more positive. And then repolarization is potassium that rushes out of the cell, and that happens during phase 3, which brings the cell back to its resting membrane potential, which is more negative on the inside. Okay, well, that's just a quick review, but there's something we haven't discussed, and that has to do with excitability of the cell. So if a neighboring cell is over here, and they're connected to each other with these gap junctions that allow movement of sodium and potassium across the cell from one cell to another. Now, at what point can a cell respond to an outside stimulation? At what point can this cell fire because of a neighboring cell's action potential? Well, certainly during the resting phase, when it's down here at minus 80 millivolts, it's very excitable, and that's what brings the action potential sequence about, is a neighboring cell. But you can't stimulate the cell again midway through the cycle. The sodium channels just aren't ready. And so at what point along the action potential is the cell able to receive another signal from a neighboring cell and fire again? And it has a lot to do with the membrane potential. That membrane potential has to come down almost down back to baseline. Under certain circumstances, it can fire a second time before it's gone all the way back down to its resting membrane potential, and it has to do with resetting of these sodium channels. But there's a certain period of time where the cell is not excitable, where the cell cannot fire a second time, and that period of time is known as the refractory period. All right, now this is getting into some advanced physiology, and I'm going to go over this in more detail in the videos that I'll do in the advanced course. But this refractory period is well defined under most circumstances, and it's the time where the cell is not excitable. It will not fire. Tissues can be refractory as well, including the bundle branches. So think of it this way. As the AV node sends a signal down the bundle branches, and this results in a QRS complex, there's a certain period of time after that beat where the bundle branches are incapable of accepting another signal. They are refractory. Well, it turns out that the bundle branches are not completely homogeneous, and that one bundle may in fact recover a split second before the other bundle. What that means is if you look at the action potential of the cells of the right bundle branch, and you compare the action potentials of the cells of the left bundle branch, the left bundle branch action potential duration may be a little shorter, and the refractory period is a little bit shorter. What that means is if the AV node lets a signal down at this point in time following the last beat, that the left bundle may be able to conduct it because its refractory period is over, but the right bundle is still refractory. So what will happen is that the beat will get to the ventricles, but the right bundle will be blocked for that one beat. And as a result, you'll get a widened QRS because of a bundle branch block type of IVCD, and this is known as functional aberrancy. Aberrant conduction simply means that the signal took an abnormal path. Aberrant sort of means abnormal. And if the signal takes an abnormal path because one of the bundles is blocked, then that gives rise to a widening of the QRS complex. But the fact is that the right bundle is still capable of conducting, that it's not really truly blocked, but it acted as if it was blocked because of the way it was functioning. Okay, so that's where we get the name functional bundle branch block, or functional aberrancy, or functional IVCD, okay? Now here's an example of a rhythm strip, and we look at the forest and we see these 3 beats here. The one thing that you should notice right off the bat is, well, first of all, the beats look to be fairly regular, and the QRS complex looks fairly wide. In fact, this starts about 20 milliseconds before the heavy line, and it finishes after 3 small boxes, so we're talking about 140 milliseconds worth of QRS complex, which is pretty consistent. We can see a very vague looking P wave in front of every beat, And the PR interval, if the QRS complex starts here and the P wave starts about here, we're talking about maybe 200 or 210 milliseconds of a PR interval. So we have a first degree AV block, and we also have this wide QRS complex, which could very well be a bundle branch block. Now, it's hard to diagnose a bundle branch block just based on a rhythm strip, but clearly there's some aberrant conduction going on. The QRS is wide, so there is some kind of interventricular conduction disturbance. When I show you the whole strip, you'll see that we were looking at AVF here, but the QRS complex is very wide and bizarre in all leads, with the rabbit ear appearance in one in AVL, and this very deep S wave and a widening of the QRS complex. So this is pretty typical for a left bundle branch block pattern. In the intermediate 12-lead class, we're going to go over exactly how you diagnose the different types of bundle branch blocks. But for this basic class, just understand that widening of the QRS indicates some kind of interventricular conduction delay or aberrant conduction. Well, the point I want to get across in this video is that aberrant conduction is not always consistent, and that you can have functional aberrancies, and when you're looking at a rhythm strip like this and you scan across, you can see there is some irregularity to this QRS complex. Each QRS complex seems to start with a P wave. There's one there and there's one there, and you can see it's very irregular because there's a pause over here. Okay, but what you also notice is that some of the QRS complexes look very narrow, like this one is narrow, and this one is narrow, and so is this one and this one. And by narrow, I'm talking about 80 milliseconds or so. But these two beats appear to be significantly wider, somewhere on the order of about 140 to 160 milliseconds. How does the PR interval compare? I've magnified this picture a little bit, and I put these little teeny tiny calipers on. But if you look at the P wave of the narrow beat and compare it with the P wave of the wide-looking beat, it doesn't seem to change. Let's go to the narrow beat following the pause, and in fact it looks a little bit shorter. So if you measure the PR very carefully, you'll find that the PR is certainly in the normal range, regardless of whether the QRS is narrow or wide. And so you're not dealing with an AV nodal problem, and these are not ventricular premature beats, which we're going to talk about in the next section. But these are conducted beats down the AV node, but they're wider than the normal beats, and so they are aberrantly conducted. Well, why are they aberrant? Well, let's bring up another pair of calipers and see. If you look at this aberrant beat compared with the prior QRS complex, okay, and let's look at the coupling interval, in other words, how far apart from the last QRS complex we see, we're talking 2, 4, 6, 8, about 900 milliseconds. So that's a little bit faster than 60 beats per minute. But so we have 900 millisecond coupling interval, and let's look at this beat over here. It's about the same, maybe 920. Then, of course, you have a much larger interval from here to here, and a much longer interval from here to here. And now let's look at this interval from one narrow beat to the next. See, it's a little bit longer than 900. It's more like 1100. And so what we can assume from this tracing is that there is a bundle branch aberrancy that occurs when the QRS complexes are 900 milliseconds apart, but not when it's greater. You see, this is the pause that refreshes. So with this time interval, both bundles have a chance to recover, and so this QRS complex conducts in a narrow fashion down both bundles. And so does this one, because you've got lots of time here for both bundles to recover, and this one, being 1100 milliseconds, conducts normally as well. But here, when you have 900 and here you have 900, that's not enough time for both bundles to recover. So one bundle gets blocked and the QRS becomes wide. And this concept of a rate-related bundle branch block is going to become very important when you start talking about distinguishing supraventricular tachycardia with aberrant conduction from ventricular tachycardia, which is a topic that we'll touch on at the end of the basic course, but we'll spend much more time in the intermediate and the advanced courses. But the idea that the bundle branches may not be blocked all the time, that they're only blocked under certain circumstances, is known as this functional IVCD, and that's the point of this video, is that aberrant conduction may come and go, depending upon the circumstances. Here's another example. This is the first time I'm going to teach you this thing, is that you should never ever pay attention to what's written on a rhythm strip, because chances are the person who interpreted the strip was not an ECG expert. But since you're watching this video, it seems that you want to be, okay? And that's my job, is to get you guys to be really good at looking at these tracings. So what do we see in this tracing? Well, we see a somewhat of an irregular heartbeat. Scanning across, you can see it's kind of slow over here, and then it sort of speeds up, and it gets very fast. Here the heart rate approaches about 120 or 130 beats per minute, and then it suddenly slows down again. Now, what exactly happens with the QRS complexes? The QRS complexes are a little bit wide to start with. They're just about 120 milliseconds here. And your PR interval is somewhat long as well. It's about 220. So you have a little first degree AV block in the beginning, and you have a slight IVCD here. But then what happens is QRS complex changes. It starts to look different. Where are the P waves, though? You see, if you scan across and looking for bumps, and here's a P that precedes this QRS complex. And then if you look across, here's the next P that seems to conduct to that. But why did this QRS change? Why did this QRS look a little bit different? And if you look at this run here of a rapid rhythm, you see that there's a P wave in front of every single beat. That tells you that basically the atrium is driving the ventricle, but yet the QRS is changing. This is another example of functional aberrancy. Even though the QRS starts out a little bit wide and stays kind of wide, it changes. It looks different. The idea that this QRS complex looks different than this QRS complex was misinterpreted as evidence that these were ventricular beats, and that's why they called them PVCs, or premature ventricular contractions. They even called it a run of V-tach, but clearly you can see there are P waves in front of every beat. So this is an atrial arrhythmia with aberrant conduction that caused the QRS complex to change in its shape and size. Okay, so aberrant conduction doesn't always mean that the QRS gets wide. Sometimes the QRS complex doesn't really seem to change its duration. It just looks different because what's happening is you're getting detours of signals going around the back door somehow. Some of the bundles are conducting, some perhaps not. Some of the Purkinje system is refractory and some of it's not. This clearly looks like a rate-related aberrancy, but in this case the QRS duration didn't really change much. Just understand that aberrant conduction means the QRS was inscribed different from normal. That doesn't always translate to wide. Here it was wide to start with, and then it just sort of like changed its shape. Sort of an advanced concept, just something that I want to mention at this point in time, but I'm definitely going to cover this again and again in future videos because it's a very important concept to understand. Now here's one last strip that I want to just throw at you. This could easily make a nice chalk talk. I want you to examine this strip carefully, and it's actually kind of a tough one, but I wanted you to see how the QRS in these three beats looks different than these three beats. This QRS is clearly wide. It goes from this box to a little over this heavy line. It's about 170 milliseconds, and that's pretty consistent here. You got a little more than 4 boxes wide in all these beats. So you have some kind of underlying bundle branch block pattern here, some sort of IVCD that's present, but then the QRS gets even wider on these beats. In fact, this is over 200 milliseconds in duration. But I wanted you to notice something. This little teeny tiny black mark right there before the QRS starts, right there, and then you see it again here. We know what that is? It's a pacemaker spike. And that's one of the things that I touched on in the last video. When a patient has a pacemaker, you'll see very wide QRS complexes because the electrical signal has to move very slowly through the left ventricle. This is not a paced beat because pacemakers are machines. They're electronic clocks. And if we take our calipers, we can see that this would be the interval from one pacing spike to the next. And so you'd expect the next pacing spike to land here. So this beat clearly came early. It's even more wide and bizarre than the underlying beat. And this is actually a premature beat, a premature ventricular contraction, which is wide and bizarre because it arose from the ventricles and did not take the normal conduction. If you think that's a little confusing, it'll all become clear in the next section when I'm going to start talking about premature beats, including atrial and ventricular premature contractions. And then I'll circle around and talk about atrial premature beats with aberrant conduction to, in essence, complete this discussion of functional aberrancy. And so, this is Dr. Nick for the Ecg Academy. Thanks for watching. Hey, this is Dr. Nick with the Ecg Academy, and we're going to start a new section about premature or ectopic beats. Now, premature obviously means early, but what does ectopic mean? Ectopic beats arise from places outside the normal conduction system. So anytime a heartbeat arises from somewhere in the atrium or in the ventricle outside of the normal circuitry, we call it an ectopic beat. And the spot where it comes from is often referred to as an ectopic focus. And so we're going to talk about where ectopic beats come from and how to recognize premature beats in the videos in this section. So you're thinking, oh no, not more action potentials. Yeah, we have to talk about the electrophysiology a little bit. And this is an action potential of a sinus nodal cell. As you know, sinus nodal cells are able to fire spontaneously because during diastole, during the part of the heart in between beats, there's this leakage of current into the cell. These positively charged ions leak into the cell, usually sodium, and that makes the inside of the cell less negative until it finally reaches this, where it's labeled negative 50 millivolts. That's known as the threshold potential. So when the cell reaches this threshold potential, that's when the action potential starts. That's when suddenly the floodgates open up and sodium, or in this case calcium, moves into the cell, making the cell positive, and then of course repolarization occurs after that. And if you label the action potential like you see in these sodium-dependent cells as phase 0, the downstroke is phase 1, the plateau is 2, and repolarization is phase 3. There's also a phase 4, and that occurs in between beats, the time known as diastole. So diastole, which is in between beats, remember, systole is the word that we use to describe when the heart is beating. So during diastole, you have this gradual increase in voltage, making it less negative, and when it reaches the threshold, it fires. Well, most cells in the heart are able to fire on their own, but it's the sinus node and the AV nodal cells that do it most rapidly. Remember, sinus nodal cells fire 60 to 80 beats per minute at rest. AV nodal cells, if you're looking at a junctional or nodal escape rhythm, we're talking 35 to 45 beats per minute. But pretty much any cell in the heart can reach its threshold and fire prematurely. And if a clump of cells in the atria or the ventricles reaches threshold and fires, what can happen is that wave of depolarization can propagate across the heart and result in a heartbeat. It would be an early heartbeat because you can't tell that it's happening unless it disturbs the timing. But in the next video, I'm going to show you how you can recognize a premature atrial beat, and subsequent videos will allow you to diagnose ventricular premature beats, and then we'll get into atrial premature beats with aberrant conduction and all sorts of other fun stuff. So fasten your seatbelts and start the next video, because this is Dr. Nick with the Ecg Academy. Thanks for watching. Hey, this is Dr. Nick with the Ecg Academy, and we're going to continue our discussion on premature beats. In this video, we'll talk about atrial premature beats. Now, we've talked about this action potential and the idea that most of the cells in the heart can reach a certain threshold potential that will trigger the floodgate and open up the ion pores in the membrane to allow depolarization to occur. Okay, in plain English, that means that if a spot down here in the right atrium reaches that threshold for whatever reason, that it can fire, and then an electrical signal will propagate across the atrium and cause a heartbeat to occur. So we characterize atrial premature beats as, one, they're early, and the other thing is that they come from someplace else other than the conduction system, and so they're known as ectopic. We can recognize the fact that it's coming from someplace different by the size and shape of the P wave. As you recall, in a normal sinus rhythm, the P wave travels down and to the patient's left. And so if you look at lead 1 and if you look at AVF, the P wave is upright in both of those because if it's going down into the patient's left, it's traveling towards lead 1 and it's also traveling towards AVF. Remember, lead 1 is at 0 degrees and AVF is at plus 90. Okay, well, what if the signal is arising from the low right atrium? What's going to happen is the signal is going to propagate in a different direction. It's going to travel up and to the left. Now, lead 1 may very well remain upright because it is kind of traveling towards the left. But if it is coming from the low right atrium, then the signal is going to be going away from the feet. And anytime something goes away from a lead, it will appear inverted on the cardiogram. So that's how we can tell that the P wave is coming from an ectopic focus, and that it will be inverted in certain leads where it shouldn't be. Well, let me show you how that's supposed to look. Let's imagine this patient's in a normal sinus rhythm, and what you expect to see is a fairly regular P wave and a QRS that follows with a fairly stable PR interval. And then you'll have a premature atrial beat followed by a compensatory pause. Let's take this apart step by step. The sinus rhythm, unless you have some degree of sinus arrhythmia, is going to be relatively regular. The PR intervals should be fairly constant. And the way I've drawn this beat is that the P wave clearly looks abnormal because it's coming from some ectopic focus. It's premature because it lands sooner than you'd expect if you were just going to map out the sinus nodal beats. And the next sinus nodal beat occurs fairly well on time, resulting in what's referred to as a compensatory pause. Now, it's interesting because many patients will complain about the pauses feeling like their heart stopped for a split second rather than actually feeling that extra heartbeat. So with a typical atrial premature beat, it's going to be early, the P wave's going to look funny. And one more thing, I took the liberty of drawing this with a PR interval that's a little bit longer than the underlying PR interval. And you'll often see that because if you recall, the AV node, which receives signals from the atrium and passes it down to the bundle branches, the AV node behaves in such a way that an early beat or rapid beats may not be able to pass down the AV node quite so easily. And you may get excessive AV delay with a premature atrial beat. You can even see first-degree AV block with some PACs, and if this beat occurs early enough, it may not even be able to get through the AV node at all. We'll cover that in the last video in this section. There's a little bit of vagary in terms of terminology because some people will call them atrial premature beats and some people will call them atrial premature contractions or atrial premature complexes. Some people like to put the P first. They call them premature atrial contractions. It all means the same thing. Well, there's some more terminology I just want to mention. Aside from premature beats, you can see something called a couplet, which means that there are 2 premature beats in a row. A triplet would be 3 premature beats in a row. Bigeminy means every other beat is premature. And trigeminy is a word we use to say every third beat. So this is every third is premature and every second is premature here. And I'll show you some examples of this later. Just to mention those terms before we get started looking at some tracings. Okay, well here's the first tracing I want to show you. This is a real tracing. You can actually see there's real noise on this tracing. Remember, here in the Ecg Academy, I'm making you ECG experts so you can look past the noise, can't you? These are tracings from real patients, not just drawings that you'll find in a textbook. All right, so let's look at the forest. And what you should notice is that the rhythm seems to be fairly regular. But if you notice, this interval right here is shorter, so this beat is something we'll come back to. And then look at that, there seems to be a longer interval following that beat, so it looks like we have a premature beat with a compensatory pause, and then we're back to being fairly regular again until the very end, when there again seems to be a premature beat. Now, what's the first thing you want to look at are P waves. Where are the P waves? How do they relate to the QRS complexes? Well, I do see a P wave in front of this beat. There's a little bit of a first-degree AV block. If you measure the PR interval, it's about 240, 280 milliseconds. And you have a P wave there as well, so it's fairly consistent. Remember, you can look at any lead here. You can see P waves up here and here as well. So there's a P wave in front of every beat. It's upright in 1 and it's upright in AVF, so we're in a normal sinus rhythm with a rate of just about 75 beats per minute, maybe a little slower. So here's the next normal beat, and here's the premature. Now, you want to look for P waves in front of the premature beat because that'll basically prove that it's an atrial premature beat. Can we see P waves? Well, we sure can. Now, here's a lesson I want to bring out, and I've mentioned this time and time again. When you look at a P wave, it tends to have fairly rapid changes in voltage. In other words, the slope of the P wave is pretty sharp. It's a kind of a spiky signal, at least compared with a T wave, which is more broad and slower in its rate of change of voltage. In electronic or physical terms, if you've taken physics, there are high-frequency components to this signal that relate to the rapid change in voltage, whereas T waves generally tend to be restricted to low-frequency signals. Okay, so you can usually see a P wave superimposed on a T wave because it looks sharp, it looks spiky, it looks like the voltage changes rapidly. Well, you can see that here very nicely. If you look at the T wave from this beat, it's very smooth. And if you look at the T wave from this beat, you've got this sharp deflection at the very end of it that's clearly negative. And in fact, you can see it here in this lead as well. It's almost like the T wave here is a very broad, slowly changing signal that only goes positive, but here it goes in 2 directions. It goes up, and then there's a sharp negative deflection, and that negative deflection there is the P wave of this premature beat. You can see it in this lead as well. Now, where did this P wave come from? Well, since it's negative in AVF, it has to be traveling towards the head from the feet. It has to be going up somehow. And you can see it's negative in lead 2, but it's positive in AVL. So if lead 2 is going this way and it's going away from lead 2, it has to be in this half of the circle. So it's got to be in this region here because it would be positive in AVL. In other words, this beat most likely arose from the low right atrium and is traveling almost straight up towards the head. The PR interval of this premature beat doesn't look much longer than the underlying PR interval because the beat wasn't all that premature, and that's kind of what you'd expect. There is a compensatory pause, and then the patient's back in sinus rhythm again, until we see this beat, which is premature also, but in these leads, unfortunately, the P waves are not quite as clear as they are here in the limb leads. So this is a beautiful example of an ectopic atrial beat, premature, complex, whatever you want to call it, arising from the low right atrium that resulted in a P wave that clearly looks different, it clearly came early, and was followed by a compensatory pause. Okay, pretty simple. Well, here's an ECG that's a little bit more complicated. And when you first look at this, you say, oh, I know what this is. I can see group beating. Here's a group of 2. And then there's a pause, and then a group of 2, and a pause. And I remember the whole group beating thing when we were talking about type 1 second-degree AV block. Yeah, this might be winky back, right? Well, when we look for P waves, we can see this big giant P wave here with a fairly long first-degree AV block. Looks to be almost 400 milliseconds. And then in front of this beat, we see another P wave, and the PR looks to be even longer. So it's looking like AV block, but wait. Let's get out our calipers and make sure. So if we drag our calipers down and place it on the P wave, so here's the P to P interval, and if you move the caliper over to the next beat, you should see a P wave here, because after all, when you have second-degree AV block, the P to P interval should be regular. And these P's are so huge, you really wouldn't be able to miss it. But it is not there. So this is not second-degree AV block. What's happening is that this is a sinus P wave. It's up in 1 and it's up in AVF. And then you have a premature beat that occurs and then a compensatory pause. And then another sinus P wave, a premature beat, and then a compensatory pause. And it keeps repeating with a sinus and then a premature beat, and a sinus and a premature beat. So what did we call it when every other beat is premature? That's right, this is atrial bigeminy. And it's something that you see fairly often. It's more common in ventricular bigeminy, but a lot of people can be confused by this because they think that there's another P wave here that doesn't conduct, and it's often misread as winky back. But this is just another example of what can happen when a focus in the atrium starts firing prematurely and disturbs the rhythm. In the next video, we'll start talking about ventricular premature beats and how they differ from atrial premature beats. And then, of course, I'll try to pull it all together in the second half of this section. So, for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to talk about ventricular premature beats in this chapter. We talked about atrial premature beats in the last chapter, so let's go on to the bottom chamber. So here's our electrical system with the atria and the ventricles. And of course, with a normal beat, you expect the electrical signals to arise from the sinus node, spread rapidly across the top chamber, giving rise to a P wave. You have a little PR segment as the electrical signal moves through the AV node, and then as the signal goes down the Purkinje system into the ventricles, you get a QRS that looks pretty narrow, and then of course a T wave for repolarization. Now, what does a ventricular premature beat look like? Now, keep in mind that ventricular action potentials look pretty characteristic, and during the part of the action potential in between beats, that's phase 4, there can be a diastolic depolarization that, if it reaches the threshold voltage, will cause another action potential to occur. And this action potential can propagate. It can start on the right side, and it can propagate towards the left, or on the other hand, it could start on the left side someplace and then propagate towards the right. So either way, what you have is a beat that arises from the ventricle, the bottom chambers. If it arises from the bottom chambers, it's not going to take the normal Purkinje system. And so it's going to take a while for that signal to make its way around the heart. And so PVCs, or ventricular premature beats, are usually wider than the normal conduction system. Since they're coming from the bottom chamber, you should not see a P wave in front of a PVC. And in fact, the ventricles should activate independently from the atrium. If the ventricles are acting independently from the atrium, we refer to a situation known as AV dissociation. Now remember, the terminology that applied to atrial premature beats also applies to ventricular premature beats. You can have couplets, which means there are 2 ventricular premature beats in a row. You can have a triplet, which means there are 3 premature beats in a row. You can have bigeminy, which means every other beat is a ventricular premature, and trigeminy, meaning every third beat is premature. There's actually quadrigeminy that some people talk about, and I'm sure you can imagine what that means. So let's look at some strips and let me show you what I'm talking about. Now here's a rhythm strip. And if you look at the forest, you can see it does clearly look a little irregular here. In fact, you can even sort of say, look at that, there's group beating here. There's groups of 2. And then at the end, it looks like there's 2 fairly normal beats with a P and a QRS that looks fairly consistent. Well, let's just for the sake of clarity, take out our calipers, and we can move those calipers up to where the P to P interval is. And what's the rate here? 300, 150, 175. It's about 82 beats a minute or so, 85 perhaps. And if you measure the QRS complexes, they seem to be pretty much on track, maybe about 40 milliseconds off. Okay, so with these 2 beats, you now have a sense of what the underlying rhythm is doing. So now let's go look at these groups of beats here. And the first thing you notice is that the 2 beats of the group look different. One is going down and one is going up. The ones that are going down, these look a lot like these normal beats, and we've already decided that these are normal sinus beats because of the shape of the P wave and the rate. So here are the normal beats, and lo and behold, in front of each normal beat you have a normal-looking P wave, and here's another P here. So if we've already decided that the sinus rate is going at 80 beats a minute, let's take our calipers and put it on the beginning of the P wave. And so the next P wave you'd expect to land right at the tip of this caliper, but what you see is this QRS complex, which is different from the underlying QRS. If you look at this QRS, it's maybe about 100 milliseconds in duration. And this one looks to be maybe a little bit longer, perhaps 120 milliseconds. Kind of hard to see where the end of the QRS is. So it looks to be a little bit wider. Now, is there a P wave in front of it? We do not see a P wave in front of this beat. Could there be a P buried on the T wave? You always have to ask yourself. Is there a premature atrial beat buried on the T wave? Well, this T wave looks pretty smooth. And if you compare it with these T waves here over on the right side, it looks to be the same. So I cannot honestly say that I can tell that there's a P wave in this T wave. So what's happening here is you probably have a normal sinus beat that's occurring, but before that P wave has a chance to even show itself, you've got this beat which is arising from the ventricle. So this is your ventricular premature beat. It has no P wave in front of it because it came from the ventricle. It's a little bit wider than the normal beat, and it clearly looks completely different because it's taking a different pathway within the ventricle. It's not following the normal conduction system. You do have some bizarre-looking STT wave abnormalities, which goes along with the fact that the normal Purkinje system is not being used. What follows a PVC is generally a pause until the next sinus beat kicks in. If we take our calipers and figure that the normal sinus beat landed here, let's bring our other point over, and we can see that there was a little bit of a delay here. In fact, there's more than just a compensatory pause, that this P wave occurred actually a little bit later. Now let's move on and see what happens here. Now if you compare this odd-looking beat to this one, it looks about the same, but it comes even earlier. How can you tell that? Well, look at the distance between the end of the T wave and the QRS complex that this PVC represents, and compare it with the end of this T wave and this QRS. And so you can see that this beat came even earlier than that one. It was even more premature. There's no relationship between the previous QRS complex and the PVC. So this occurred quite early, but the interesting thing is when you look after the QRS complex, something has changed. You can see that there's a smooth T wave here, but this T wave has a big bump going downward. Now what this is a retrograde P wave. Now what is a retrograde P wave? Well, let's go back to our conduction system. Remember that our AV node is capable of conducting impulses down from the atria to the ventricles, but in many patients, these cells are also able to conduct in a backwards direction. That means if a PVC arises from the ventricle and manages to get into the Purkinje system, it can travel up the AV node and wind up emerging on the atrial side of the AV node and result in an atrial depolarization, which will be traveling in the opposite direction than a normal sinus beat. That means that following a PVC, if we have a normal sinus beat here, you'll have a PVC that'll look bizarre looking, and there'll be a retrograde P wave following it. That just means that this ventricular beat managed to go up the AV node and wound up emerging right around here and caused a retrograde P wave, which means it's inverted compared with the normal P wave. Going back, we see that this P wave is in the opposite direction than the normal P wave. It's a sharp, spiky signal, so it has high frequency components, and that's a retrograde P wave. And in fact, it landed right around the same point where the normal sinus P wave would have occurred. Following that, there is a compensatory pause again. And then if you look at this beat, you see that you also have a retrograde P wave following this ventricular premature contraction or ventricular premature beat. So this is something that you're going to see again and again. An early beat with no P wave in front of it, but is followed by a retrograde P wave in many cases. Not always, though, because here you didn't see a retrograde P wave. Well, let's look at a couple of other examples so that you understand this a little bit better. Well, here's a 12 lead, and you can immediately see that there is this regular rhythm underneath here, but then there are all these FLBs. We call them funny-looking beats. They're wide, much wider than the underlying QRS complex. They're very bizarre-looking, and they occur prematurely, because if you were to take the R to R interval here and map it out again, you expect the QRS to land here someplace. And then the next one occurs here. All right, so you have this early beat. There's no P in front of it. It's wide and bizarre. It's got these really bizarre looking T waves following it. There's a compensatory pause following it. And this is a typical example of frequent ventricular ectopy. Now there's a little bit of a trigeminal pattern here. You got normal, normal, premature, normal, normal, premature. Here you have normal, normal, premature, normal, normal, premature. Now this is interesting though. If you look at this beat carefully, you'd say, wait a minute, hold on. There's a P wave in front of that beat, and the QRS looks wide, not as wide as the PVCs, but not as narrow as the underlying beat. And it kind of looks halfway in between the PVC and the normal beat, and plus there's a P wave in front of it. Well, what about the PR interval? That's really, really important to look at. The underlying PR interval here is about maybe 180 milliseconds. This PR is significantly shorter. This PR is only about 120 or 150 milliseconds. If you zoom in on that, you probably can make an accurate determination. But this is a very cool beat, and it's known as a fusion beat. A fusion beat implies that part of the QRS complex came from this P wave down the normal conduction system. But at the same exact moment, a ventricular premature beat arose somewhere in the ventricle, and they met halfway. So you've got this ventricular premature beat here, and that travels up, and you've got a normal sinus beat that goes down the AV node, and they kind of meet halfway. And that's what a fusion beat means, is that the signals meet halfway, and the QRS complex comes from both the P wave down the normal conduction system and the ventricular ectopic beat. That's a very good way to know that indeed you are dealing with premature beats, is that if you see fusion complexes, you know that these beats are coming from a different part of the conduction system. Okay, last example. I want to show you that if you look at the forest, you see that there's some irregularity in here. In fact, it's kind of interesting because if you look at the rhythm strip, you can see PQRST, PQRST. So you've got a couple of normal beats. It's a little bradycardic. The rate here is a little bit below 50 beats per minute. But look at how this P wave kind of changes. So it looks like there's a little bit of a variation in the P wave morphology, which basically means that the P wave is coming not just from the sinus node, but there may be some region out here, and you've got competition between the two beats. So this is almost like a fusion beat in the atrium, because it came almost on time. Maybe it's only a little bit faster, but the P wave looks different because it arose from someplace away from the sinus node. Then you have what looks like a sinus beat, then another odd-looking atrial beat that's a little bit more premature. Here the rate is 300, 150, 175, 60. So it went from a little below 50 to about 60. So this is a premature atrial beat, a PAB or PAC. And this is probably a fusion between those two foci, the normal sinus beat and the premature beat. And then you have a third P wave morphology, which is kind of interesting. And then you have these two wide beats. Well, the wide beats are very wide and very bizarre. If we look at the T wave here, it looks exactly the same as this T wave. So I don't believe that there's a P in front of this beat, but there certainly looks like there's a P behind it. Right there is a retrograde P, and following the second beat is another retrograde P. So these two beats came from the ventricle. This is a ventricular couplet, and that means two abnormal ventricular premature beats in a row. It's a couplet, but notice how narrow it looks in this one lead. So you kind of have to look at multiple leads in order to be able to determine how wide the QRS is. But this is just an example of how you have to take each beat at a time, look at these little subtle differences in P wave morphology, look for retrograde P waves in order to be able to diagnose ventricular ectopy. And this is a bit of an introduction to how to approach an ECG and pick it apart and find all the little details that allow you to precisely make the diagnosis, just like you should if you're an ECG expert. And so for the Ecg Academy, this is Dr. Nick. In our next video, we're going to talk about weird kinds of ectopic beats, other kinds of premature beats that you'll come across in order to finish this section on premature beats. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to finish up this section on premature beats, talking about my very favorite, and that's known as other premature beats. Well, I didn't know what else to call this chapter, but we're going to start talking about a few things that you see now and then, including aberrantly conducted APCs, non-conducted APCs, and junctional premature beats, and something else, a special secret guest that's going to be coming at the end of this discussion. So let's start right off the bat. We're going to look at this tracing right here. Let's look at this as a chalk talk, okay? You look at the forest first, and you can see that there's some irregularity going on. In fact, it kind of looks like group beating, but the two beats are different. So it makes you think of those PVCs. You have a narrow beat and a wide beat, narrow beat, wide beat. Then you've got a couple narrow beats in a row, another wide one, a narrow and wide. And you see that the wide ones are always premature. That's right. If you map out this normal-looking beat with a P and a QRS, your PR interval looks pretty normal. And if you take this one as the next normal beat and you look right in the middle, you can see that this beat right here occurred early. Now let's look at the QRS duration. In the normal beat, it's only about 80 milliseconds or so in duration. This QRS starts on the first row of boxes and finishes on the fourth row. So that's 3 small boxes, 120 milliseconds. So it's clearly wide, it's clearly premature, and you'd say, well, the QRS complex looks really quite different than the underlying rhythm, and this kind of looks like a PVC. So you'd look at this and say, well, it's every other beat, so it's ventricular bigeminy. Isn't that right? Well, if that's what you think it is, I'm going to show you why it's not. If you look at these 2 normal beats in a row, it gives you a chance to look at what the normal T wave looks like. And the normal T wave looks pretty smooth, as T waves should. And then you have this P wave that occurs before the normal QRS complex. So the P's look fine and the T looks pretty smooth. What you need to make sure about is that there isn't a P wave in front of these wide-looking beats. And if you look at this T wave right here, it looks distinctly different than this T wave here. Why? You guessed it. This is a P wave. And so is this. Well, you'd say, well, that looks like a normal T wave to me, but it looks different from this T wave. Okay? You have to compare from one T to the next. So now if you look at this T wave and you look at this T wave, you can see that this one's much more bumpy. There's a big giant lump on top of that. It looks like Mount Everest to me, and that's the P that results in this wide beat. And so what are these beats? These are known as aberrantly conducted APCs. They're aberrantly conducted because the premature beat, this P wave, got through the AV node and encountered partial refractoriness of the conduction system below the AV node. So if the AV node is here, and you've got your left bundle and your right bundle, and your hemifascicles going down here, so the premature beat gets down just at a point when one of these hemifascicles is blocked. It hasn't recovered from refractoriness. Remember, the right bundle can have a longer refractory period than the left bundle. And if this beat comes down right at this location, it may be able to conduct down the left bundle, but the right bundle is blocked. And that gives you aberrant conduction, or a functional bundle branch block. So timing is everything. This P wave happened to occur at a point when one of the bundles had not recovered from refractoriness, and you get aberrant conduction or a functional bundle branch block pattern. Okay, and you're going to see this again and again, and in fact, I'll bring it up again when we talk about supraventricular tachycardia, because frequently that'll occur with aberrant conduction, and then it's hard to tell it from ventricular tachycardia. It's one of those challenges that only ECG experts can solve, and that's why you're watching these videos, isn't it? Well, now that we've covered aberrantly conducted PACs, let's go on to the next topic. Here's an interesting rhythm strip that I found, and you can see that the rate's quite a bit faster than the last cardiogram. The fine lines are kind of difficult to see, but I think if you count off 300, 150, 100, it's just about 100 beats per minute. There's a nice P wave with a normal PR interval of about 140 milliseconds. And so you have sinus rhythm at 100 beats per minute. In fact, I think it's right on the border of 100. Each of these QRS complexes seems to land in the same position with respect to the heavy line. Okay, but then all of a sudden, you see slowing of the heartbeat. The R-to-R intervals suddenly become much longer. You still have P waves here in front of every beat, but there seemed to be a sudden slowing of the sinus rhythm. And you've got this period of slowing down here, and then suddenly the sinus rhythm seems to pick up again, and it goes back to where it was before. And so you have to kind of ask yourself, well, is this a sinus node problem? Do we have sinoatrial exit block? That would be a possibility, because here you have sudden slowing of the sinus node, so potentially these sinus impulses couldn't get out to the atrium. So that's a possibility, but that one's not right either. And again, the key is in the T waves. Look at these T waves. They look very smooth and very consistent, and then suddenly this is Mount Fuji over here. It's Jaigundo. And why is it Jaigundo? And why is it followed by slowing of the ventricular rate? Well, that's because right here is a P wave that did not get down the AV node. It's non-conducted or blocked. We call this a non-conducted PAC or a blocked PAC, and it left a pause in the rhythm, which is really just a compensatory pause. You remember atrial premature beats result in compensatory pauses, and they sometimes can conduct with a first-degree AV block, but in this case what's happened is this PAC landed at a point where the AV node didn't have a chance to recover from this beat. So this lands on the refractory period of the AV node and fails to get down the AV node, so you're left with a pause. Okay, so then here's the next sinus beat, but then it happens again. This T wave is again very tall because there's a blocked PAC, a non-conducted P wave that creates this pause in the rhythm, and then it happens again. You've got another P and then a non-conducted PAC here. Well, every other beat is premature, so it's definitely bigeminy, and it's atrial bigeminy, but these atrial bigeminal premature beats are non-conducted or blocked. And so it's a non-conducted atrial bigeminy, and it sets up this pattern of conduction and block and conduction and block. And then finally, this beat conducts, and look, the T wave goes back to normal because now there's no PAC here, and the next sinus beat comes on time. And so the sinus rhythm starts to conduct one-to-one, because this atrial bigeminy goes away, and then you're back to where you started. So the idea that you can have non-conducted or blocked PACs in a bigeminal pattern, that's a kind of a cool thing, and it fools a lot of people. So you've learned two things from this trip, that you can have non-conducted PACs. Now, I prefer the term non-conducted rather than blocked. A lot of people call them blocked PACs, but because these PACs are so early, look, if you just measure the rate between this PAC and this PAC, it's about 150 beats per minute. And a lot of patients will not be able to conduct that quickly after this one. So in reality, it's normal physiology for the AV node to act as like a safety valve, to not let rapid atrial rhythms down. We'll see that when we start to talk about atrial tachycardia and other atrial arrhythmias where the AV node actually protects the ventricle against rapid atrial arrhythmias. But in this case, it's kind of a normal physiology to have this premature P fail to get down the AV node. And so the word blocked implies there's something wrong with the AV node, and often that is not the case. So I prefer the term non-conducted. It just is more clear and less misleading, and doesn't make it sound like there's something wrong with the AV node. Okay? Let's go on to the next example of unusual premature beats. Now here's a 12 lead. It's kind of set up differently because you've got all the leads kind of like, it's almost like a rhythm strip. You have V1 through V5 here, and then you've got some of the limb leads here. It's kind of a strange setup for this particular ECG machine. But if you pick any lead, you can actually see that there are P waves in front of each beat, and the PR interval is fairly normal. And the rate here is maybe a little by 78 beats per minute or so. So you've got a normal sinus rhythm at 78 beats per minute. And you've got 1, 2, 3, 4 beats that all seem to be normal. And then you've got this beat, and it's a premature beat. But when you look at the QRS complex, it looks very similar, if not identical, to the underlying QRS, to the conducted one. See, in V1 this is down. In V5 it looks a little bit shorter, but it's almost identical in every single lead that we're looking at. And so it looks like it might be an atrial premature beat. But when you look at the T wave preceding this premature beat, you don't see a P. This T wave looks exactly the same as this T wave. There's no P preceding it. But what you do see is a P following that beat, and it's inverted. In fact, you can see that it's a retrograde P. That means it came from below and it's traveling upwards towards the sinus node. Well, what does that mean? If the beat looks almost exactly the same as the normal beat, but the P wave comes later, you have to think of normal physiology here, and I'm just going to try to get you to understand what's happening. Okay, if here's your AV node, and you've got your bundle branches going down, the QRS complex looks like it followed the normal bundle branch system because it looks the same as the underlying beat, but the P wave was retrograde in that it started down in the lower part of the atrium and traveled upwards. And so the beat must have arisen from somewhere in the AV node. Somewhere in the AV junction, this beat occurred, and then it traveled down rapidly down the Purkinje system to give you the QRS complex, and then after a short delay, emerged out these transitional fibers to the atrium and gave rise to a retrograde P wave. And we call this a junctional premature beat, or JPC for junctional premature complex, or contraction. So this is an example of how an ectopic beat can arise from the AV node and give you a QRS that looks almost exactly the same as a normal beat, and yet there's a retrograde P wave that follows it. Okay, now just to let you know that sometimes these junctional premature beats can arise from a little higher up in the AV node. For example, if the beat arises from the top part of the AV node, it will emerge from the AV nodal complex first and then manage to get down the Purkinje system. So junctional premature beats can sometimes look like this, with a retrograde P wave just in front of the QRS complex, usually with PR intervals that are way shorter than 80 milliseconds. But sometimes what you'll see is a junctional premature beat that looks exactly like the underlying QRS, but no P wave visible. And that's because it arose from the middle part of the AV node and wound up going retrogradely and antegradely down the His bundle system at the same exact time. So the P wave is actually buried in the QRS complex, and you just don't see it. So these are three different forms of junctional premature complexes, and you'll see it now and then, but it's kind of a rare finding. Okay, the last thing I want to show you is this very interesting ECG. And if you scan the forest, you can see that for the most part, it's fairly regular, except that there are these premature beats every now and then. It's regular, 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 and then you have a premature beat. Now, does the premature beat look exactly the same as the underlying rhythm? No, it does look a little bit different. In fact, if you look at this beat here in lead 3, it's going in the opposite direction from the underlying conduction system. So it does not look like a junctional premature beat, but yet there's no P wave either before or after it. So what is this beat? Is it coming from the atrium? Is it coming from the ventricles? Well, let's take our calipers out and see if we can figure out what's happening. So if we take these calipers and we put them on top of a P wave and establish what the P to P interval is, that helps us a lot, because then when we move it over to the next P wave, we see that the sinus beat should have landed right about where this QRS is. And then if we measure on to the next beat, we see that this P wave occurs on time. Sometimes, in fact, it's helpful to look at two P waves. So let's stretch our calipers out here so that we're spanning two P waves. Okay, so that's the beginning of two P waves, and you can see that that's pretty consistent. And if you look at the next P wave here, you can see that it lands right on time. But when you measure from this preceding P wave, you can see that this one, in fact, is on time as well. So if there's a sinus P, it's buried in the QRS complex. I think, in fact, you could probably see a little tiny piece of it right here at the tail end of the QRS complex. I think this sort of like little bump after the QRS is, in fact, the sinus P going on. Well, Could that sinus P have caused this QRS complex? Obviously not. The P can't conduct at the same time. Could this be a junctional premature beat? No, I don't think so, because it looks so different from the underlying QRS complexes. What we're dealing with here is a premature beat that arose from the ventricle. It's a ventricular premature beat, yes, but it had to follow part of the normal conduction system because it's so narrow. It's really very narrow. In fact, it's not much wider than the underlying QRS complex. If we were to create some space here and then draw a little heart, my very fancy conduction system heart. Okay, so if the conduction system, if you have your AV node and you have your bundle branches, you got the right bundle here, you got the left bundle, which is much heavier, splits into hemifascicles. Okay, now where did the beat come from? It had to arise somewhere down in the bundle branch system. Maybe the right bundle branch, maybe one of the hemifascicles. Okay, but it must have arisen from part of the conduction system. And then what happens is it follows that conduction system out to the rest of the heart. But the premature beat arising from this part of the conduction system would have to go back up in a retrograde direction, reach the His bundle, and then turn around and then go back down the opposite bundle. And so what happens is it gives rise, in this case, to a little R prime here. So you have like an RSR prime pattern. It's like an incomplete right bundle branch block pattern. I talk about bundle branch block patterns in the intermediate course. When you're reading 12-lead ECGs, of course, you need to be able to recognize this. But the point is that beats can arise from part of the conduction system, and then what happens is they can wind up taking an aberrant course through the conduction system and give rise to a slight widening of the QRS complex, but not a full-blown bundle branch block pattern. In fact, it's conceivable that this beat arose from just below the His bundle, somewhere in the left bundle branch. So if it arose from the left bundle branch, just below where the two branches split, it didn't have to go far to get down the right bundle again. And so instead of having a narrow QRS complex, what you get is a little bit of an aberrant conduction. It causes the QRS to become a little bit wider, but not quite so wide that you can call it a true ventricular premature beat. But in reality, it's arising from below the AV node. And so what I like to call this is a narrow VPC, or you can even call it a hemifascicular premature beat, because it's arising from the Purkinje system, it's arising from the conduction system itself. Now, this is kind of unusual, but I just want you guys to think about the physiology, think about where these beats are coming from, and keep in mind that they don't always look like the textbook. If you understand the physiology, you can figure out what it is. You have to use your brain, you have to analyze the signals and the tracings, but eventually you can look at something and know what it is because you understand the physiology. And on that note, I'll end this discussion of premature beats, and we'll go on to the next section and start talking about atrial tachyarrhythmias. So, for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hey, this is Dr. Nick with the Ecg Academy, and we're going to start a new section on atrial tachyarrhythmias. That means fast heartbeats coming from the top chambers. That's all that means. Atrial referring to the top chambers, tachy meaning fast. All right, now there's a whole bunch of different kinds of atrial tachyarrhythmias, and the videos in this section are going to discuss each and every one of those and try to put things into perspective. So, what I've done here with this pie chart is give you an idea of how often you'll see the different kinds of tachyarrhythmias. Atrial fibrillation is a very common atrial tachyarrhythmia that has its own section in this basic ECG course. Atrial fibrillation occurs when the electrical signal in the top chamber is going all different directions in a very disorganized, chaotic fashion. And that causes a very specific type of rapid heartbeat coming from the top chamber. Atrial flutter, on the other hand, is a rapid heartbeat coming from the top chamber where the electrical signal is basically traveling around in a circle, and the atrial rate is somewhere between usually 225 to 325 beats per minute, somewhere in that range. Anything slower than that will generally fall into the category of supraventricular tachycardia or atrial tachycardia. Atrial tachycardia is generally an abnormal rhythm originating in the top chamber at rates anywhere between 100 and 200 beats per minute. It can be faster as well, but when it gets over 225 or so, we start to think of it more like as atrial flutter. Although you'll see that sometimes it's kind of hard to tell the difference, and it's really kind of a matter of what you'd like to call it, depending upon what it looks like. So this section is going to be talking primarily about atrial tachycardias as a type of supraventricular tachycardia. That's what SVT stands for. Supraventricular just means it comes from above the atrium. So this includes a whole bunch of different kinds of atrial tachycardias, including some that actually originate from the AV node itself. We'll talk about those in more detail in the advanced course, but for now we'll show you what they look like and familiarize you with how to diagnose supraventricular tachycardia. Well, in the grand scheme of trying to organize this discussion of atrial tachyarrhythmias, there'll be 4 chapters. This chapter is going to be about atrial tachycardia and paroxysmal supraventricular tachycardia. The two of these are often grouped together because sometimes it's hard to tell the difference. But let's just say that atrial tachycardia, you can generally see the P waves in front of each beat, whereas in PSVT, the P waves may or may not be apparent. So we're going to start with our first strip here. And in this rhythm strip, if you kind of glance across and look at the forest, you'll see that there seems to be a sinus beat that kind of stands by itself in the beginning. And then suddenly it appears that the heart rate increases significantly. This sinus beat does have a P wave in front of it, and the PR interval looks to be at the upper limits of normal, probably 180 to 200 milliseconds. And the next sinus beat seems to be over here, with a heart rate about 300, 150, 175, 60. So it's a little bit faster than 60 beats per minute, probably 65 or so beats per minute. And you'd expect the next beat to occur in here someplace, but you can see that there's a P wave here that starts off something here, something rather fast. The first beat occurs somewhere above 100 beats per minute, but you can see that there's a slow increase in heart rate. By the end of this, we're talking about just over 150 beats per minute, like maybe 155. One thing you can characterize this as having a gradual increase in heart rate. It's a rapid heartbeat, so it's a tachycardia. You see P waves that start the tachycardia, and the QRS complex looks exactly the same as the underlying QRS complex. So it would appear to be coming from above the ventricles, so it's supraventricular, and you see this P wave that starts it off, so it's appropriate to call it atrial tachycardia, or AT for short. Now, one thing about atrial tachycardias is they can occur at rates anywhere from 100 up to 220 beats per minute. This one happens to have a particular pattern in that it warms up. A warm-up phenomenon means that the heart rate gradually increases as the arrhythmia progresses. Now, what you need to start doing now is pay attention to the little bitty details, because this is how you'll make the diagnosis. If you look in front of this beat looks the same as that beat, so where did it come from? You'll see that this T wave, which was very smooth, and if you compare it to this T wave, what do we see? We see a bump. And that bump, of course, is the P wave that gave rise to this QRS complex. So clearly there's a P that is in front of this beat, and if we look at the next one, we see a P here, and we see a P here. So there are P waves preceding each beat, and it starts to get interesting as you get to the end of the tachycardia. Because where are these P waves? Well, I think it's clear that there's one here, but now what happens is there are 2 bumps. Now, which is the P and which is the T? You'd expect that maybe this is the P because it's in front of the QRS complex. But remember, we have a PR interval that's somewhere out in the 180 to 200 millisecond range. So if you measure back from this QRS complex, you'll see that this is probably the P wave. And you'll say, come on, are you sure about that? And I'll say, well, look at the next one. Now you still see 2 bumps, but they're much further apart. Which one has moved? Which one looks like it's associated with the QRS? You figure, well, I think that's the P wave, because that's closer to the QRS. But it turns out that this is the P. Now, how can you say that? How do you know that? Well, it wasn't here, and it's unlikely that the T wave moved because the QT interval cannot suddenly shorten. So because this is the signal that's moving, it's likely that that's the P wave, but I can prove it to you. Because when you look at this beat, you can see a bump right there, and that cannot possibly be the T wave because that QT interval is not physiologically possible. And this conducts to this QRS with a fairly long first degree, somewhere about 280 milliseconds. And then this happens to be the last beat of the tachycardia because here there's no P wave, but what you do see is a T wave that looks exactly the same as this T wave. This T wave and this QT interval is the same as this QT interval and this T wave. So this T wave, that's the T right here, and the P wave is this bump that comes after the QRS. Isn't that cool? So if you carefully dissect this strip, you can get the sense that the P's can march around and they can change their position with respect to the previous QRS complex, and that gives you a hint that that's the P. It's kind of marching on through. But in fact, what we had here, if you count this as the first beat, you have 1, 2, 3, 4, 5, 6, 7, 8 beat run of atrial tachycardia with a warm-up phenomenon that started at 100 beats per minute and sped up to about 155. At the end, had a bit of a first-degree AV block, but that's exactly what you would diagnose this tachycardia as. So we are getting into some complicated territory over here. And I hope you guys keep up, but the beauty of internet learning is that you can play this back over and over again until you truly get it. Get it? All right, let's go on to the next one. This one might be a little bit easier to see, but it does have a slightly different flavor here because the QRS is wide. This patient has an underlying bundle branch block, and that makes the QRS duration somewhere about 120, 140 milliseconds. But clearly you can see P waves that precede these QRS complexes, and it looks like you have a normal sinus rhythm at a rate of about 70 beats per minute. You have an atrial premature beat here. You could see there's a P in front of it, but it looks kind of pointy compared with this P wave. So it probably came from a slightly different spot in the atrium. And then you have to start to wonder whether this is another P wave because it's a sharp bump that occurs on top of the T. This has to be the T here because it looks the same as this T wave. And so that's another P there that gave rise to this QRS. Then you have a little bit of a pause here, a compensatory pause. So basically what you had here was an atrial couplet. You had 1 and then 2 premature beats in a row that gave rise to this atrial couplet. Now you have a little compensatory pause. You have a very tall P wave here, and some people would call this an escape beat since the P wave looks different morphologically than the sinus P wave. But then this looks more like a sinus P, and we're back to a rate of about 70. And then we start to see another APC, and maybe this is an APC as well that conducted to here. And now you see an abnormal P wave that conducts, and then suddenly the heart rate takes off like a shot. Now what we have is a heart rate of about 145 beats per minute, and it's quite steady, heading on. In fact, at this point, you have 150 beats per minute, and it's still running until right here, when it ends and you have a compensatory pause. You have no P wave here, so most likely this is a junctional escape. And then there's an APC right here that gives rise to this QRS. And then you have a P wave that conducts, another P wave that conducts, and you kind of have, you're not exactly back to sinus rhythm. This is obviously a patient with a lot of different complex atrial arrhythmias. But this is the part I want to show you. This atrial tachycardia right here at 150 beats per minute, you can diagnose it because look at these T's. Look how peaked they are. They're a lot taller than this T wave, and that's because you have a P wave buried in the T. There's a P here and there's a P here, and each of these P's conduct antegradially down the AV node, giving rise to the QRS complex. So you have all these P's. Now you're saying, come on, Dr. Nick, how do I know there's a P there? Just because it's tall, what's the big deal, you know? Well, if you keep on looking, look what happens. The P and the T start to split apart, and now you have 2 bumps. Remember, like the last strip, you had 2 bumps? The question is, which is the P, which is the T? I have a feeling that the first one is the P for the same reason, that because it's a fast rate, you get a longer PR interval, you get slowing of AV conduction, and the QRS complex will occur late, but the T wave remains somewhat delayed because your QT interval here is pretty long, about 400 milliseconds. But you can see, look at that, how this is a little bit wider, and then it gets a bit more narrow. These two bumps are independent. One is the P, one is the T, and you can pick them out. You can pick out that P wave apart from the T, and you can say, there's a P wave in there, and this is an atrial tachycardia, until it finally breaks here, and then the patient's back in some kind of escape beat and then a sinus rhythm of sorts. So this is a kind of a tracing that you're going to see on telemetry all the time. What do you call it? Will you be surprised? A lot of monitor techs will look at this and call it atrial fibrillation, but it's not. You can see these discrete P waves marching on through, each one associated with the QRS complex. So what is this? We would call this atrial tachycardia with one-to-one conduction. That's what the correct diagnosis is. It's an atrial tachycardia with one-to-one conduction. You can see that the beats are coming from the atrium. The atrium is driving the ventricles. There's a little bit of irregularity in that the PT intervals are varying slightly. So there's just a slight bit of irregularity to this arrhythmia, which is very common for atrial tachycardias. So that's how you diagnose atrial tach. It is a kind of supraventricular tachycardia, but I think supraventricular tachycardia is a little bit more vague in that it only tells you that it's coming from above the ventricles. Atrial tachycardia is more specific in that it tells you basically that the mechanism is that the atria are beating rapidly. The atria are beating rapidly. It could be due to a focus that's firing, or it could be due to some other kind of short circuit. But the implication in the diagnosis of atrial tachycardia is that the AV node is passively conducting the impulses down to the ventricles. In other words, these electrical impulses are originating in the top chamber, and they go down the AV node to the bottom chamber, and the AV node is not part of the circuit. In other types of supraventricular tachycardia, the AV node is part of the circuit, but that's an advanced topic, and we're not going to get into that at this basic level. At any rate, atrial tachycardia implies it's coming from the atrium, and the AV node is simply conducting the impulses to the ventricle. Now, I've shown you two examples of non-sustained atrial tachycardia. These are bursts, or sometimes we call them salvos, of rapid heartbeats that start and stop. The word that we use in cardiology for arrhythmias that start and stop and start and stop is paroxysmal. A paroxysm is like an attack. It's a non-sustained burst or an episode. So paroxysmal atrial tachycardia, or PAT, is actually the old term we used to use. But I think PAT is overused. It's often used when someone's not sure of the mechanism and they just see this atrial arrhythmia that starts and stops and they call it PAT. But PAT is kind of a generic term, and I prefer trying to get a handle on exactly what the mechanism is of this tachycardia. And in the advanced course, we talk about the electrophysiologic mechanisms of tachycardias, and that helps decide how you're going to treat it in terms of which medications to choose for the patient. In the next video, we're going to talk about sustained atrial tachycardias and the whole concept of paroxysmal supraventricular tachycardia, or PSVT. So until then, this is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and this chapter is about a certain kind of atrial tachyarrhythmia that we affectionately refer to as SVT, or supraventricular tachycardia. Now, you might say, well, what's the difference between atrial tachycardia and SVT? Well, to tell you the truth, it's a little bit of semantics, but what I like to say is that if you can see discrete P waves in front of each QRS complex, then we like to call it atrial tachycardia because we know it's coming from the atrium. But sometimes rapid heartbeats from the top chamber actually originate within short circuits involving the conduction system. And often it's better to call them supraventricular tachycardia to basically distinguish them as being from tissues above the ventricle, but not necessarily directly from the atrium itself. Now, in the last video, I talked about paroxysmal supraventricular tachycardia, or PSVT, and that's more of a clinical diagnosis, meaning the patients will feel a rapid heartbeat that starts and stops fairly suddenly, and it can go on for minutes or hours or even days. Now, the kind of mechanisms that cause atrial tachycardia we'll discuss in the intermediate section when we deal with mechanisms of arrhythmias. But suffice it to say that sometimes atrial tachycardia can occur because the electrical signal is traveling round and round in a circle. We call that re-entry. And sometimes atrial tachycardias can arise from one little spot in the atrium that starts to fire rapidly, and the signal sort of spreads outwards. And we call that more of an ectopic focus or ectopic atrial tachycardia. But that's diagnosis that is sometimes difficult to make just from the ECG. And if you just call it atrial tachycardia, that's generally enough. Of course, we'll deal more with this in the advanced course. But we'll talk about PSVT because PSVT is a very common problem. We see it in the emergency rooms, and we can see it on Holter monitors and whatnot. Now, with PSVT, basically the problem is coming from above the ventricles somewhere. One of the more common arrhythmias that we'll see originates from the AV node itself. And you see these transitional fibers. They're the anterior fibers here and the posterior fibers here. Well, sometimes you can get the signal getting stuck, going down one pathway and back up the other. And you have this signal that basically chases itself round and round in a circle this way. And that's probably the most common cause of PSVT. That's actually known as AV nodal reentry tachycardia, or AVNRT. As I said, we'll go over this in great detail in the advanced course. The other mechanism that we'll sometimes see, we touched on briefly in the section on interventricular conduction disturbances, or IVCDs, because people can sometimes have an accessory AV pathway, like a WPW kind of syndrome. And there, the electrical signal can actually get stuck going down the AV node to the ventricles and then back up this accessory pathway to the atrium, giving rise to a very large reentry circuit, sometimes known as macro reentry. Now, this is getting into some advanced stuff, but basically it causes a rapid heartbeat that starts suddenly, arises from above the ventricles, and gives rise to a narrow QRS complex, rapid regular arrhythmias. Now, on occasion, you'll see what looks like PSVT, but it's actually arising from the atrium itself. Sometimes you'll actually have atrial tachycardia where the signal is either going round in a circle or whatnot. Sometimes you can have ectopic atrial tachycardias as well, but they'll be hard to distinguish from the other kinds of arrhythmias that I mentioned. But at least you can kind of lump them together as supraventricular tachycardia, and that would be the correct diagnosis. Well, let me show you the first example of a sustained tachycardia where it's unclear what the exact mechanism is, but you can at least diagnose it as supraventricular tachycardia. Now, here's one example of supraventricular tachycardia, and this would be a patient who maybe walked into the emergency room with palpitations or lightheadedness. And this is a 12 lead, and when you scan across, you can see that the QRS complexes appear to be quite regular. And if you look for a QRS that lands on a solid line, you can count off 300, 150. It's about maybe 120 something. But remember the trick, look for two QRS complexes and count off that. So here's one and here's another. And those are exactly, let's see, 300, 150, 100, 75, 60. So if you count 60 beats per minute for 2 beats, then 1 beat has to be 120 beats per minute. What you should recognize immediately when you look at the P waves in front of each QRS complex is that they're inverted. They're upside down, they're inverted in the inferior leads. And that tells you basically that the P wave vector is headed towards the head. That means they have to be originating somewhere down in the low part of the atrium and then traveling upwards. And it couldn't possibly be sinus tachycardia. It has to be some kind of ectopic focus. So we can call this ectopic atrial tachycardia, which gives us a little bit of a sense of what the mechanism is. But some people would just simply refer to this as supraventricular tachycardia. And it is sustained. You can see it just goes on and on and on, and this patient was in it for hours. So the mechanisms that cause tachycardias like this are variable. Sometimes it may be due to a focus that's firing rapidly, but in this case it turned out to be a short circuit involving the AV node. I want you to be able to recognize this kind of supraventricular tachycardia as being regular, narrow QRS complex with a P wave that's generally one-to-one association between the P and the QRS with a fixed PR interval, and you'll sometimes have to actually give the patient medications to get it to break. Now, this kind of sudden onset, rapid regular rhythm is often referred to as paroxysmal supraventricular tachycardia, or PSVT. And PSVT is generally considered to be due to short circuits, often involving the AV node. Just be able to recognize this as an abnormal rhythm because you see these inverted P waves, and so you're safe to call it an atrial tachycardia. You know that these P waves are inverted, and so the arrhythmia came from somewhere outside of the sinus node, so ectopic atrial tachycardia would be a little bit more specific. And if you want to suggest that this is a mechanism perhaps involving the AV node, then PSVT would be an appropriate diagnosis. But this has a lot to do with how the tachycardia behaves. The behavior of the tachycardia is how it starts, how it stops, what kinds of symptoms it causes, and how it responds to medications. And PSVT is more of an electrophysiologic diagnosis, whereas if you just take the cardiogram at face value, it's reasonable to just call it an atrial tachycardia. And finally, I'm going to show you this electrocardiogram, which most cardiologists would simply label this as SVT, supraventricular tachycardia. The mechanism is a little bit difficult to determine, but if you look at the forest, you see it's a very regular tachycardia. It's quite fast here. If you take two QRS complexes and measure the rate, it's 300, 150, 100. So we're talking 200 beats per minute. So at 200 beats per minute, it's regular. It's narrow complex. Are there P waves that you can identify? Not easily. In the advanced course, I'll show you how to look for evidence of P waves in this kind of a tracing, but it's safe to say that the P waves in this tracing are not really visible. They're almost certainly buried within the QRS complex. And in fact, you see a little tiny negative deflection at the tail end of the QRS that's likely the P wave peeking out from behind the QRS. So you would call this supraventricular tachycardia if the patient described that it started suddenly and he came to the emergency room and got an injection of something like adenosine or diltiazem and it breaks suddenly, then you would call this paroxysmal supraventricular tachycardia. But again, that's a diagnosis that's kind of based on the behavior of the arrhythmia. It's more of a clinical diagnosis. The electrocardiographic name for this would be SVT. You don't see those discrete P waves in front of each QRS complex, so atrial tachycardia would be less appropriate under these circumstances. It's getting a little complicated, but watch these videos over and over again and listen to the rest of the videos in this section, and it'll make sense to you. And you'll get lots of practice reading these things on the Chalk Talks if you subscribe to those weekly discussions on unknown ECGs. That's where you'll really get used to reading these more difficult tracings. So, for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and this chapter is going to be about atrial tachycardia with AV block. So we're going on to the next section here. Atrial tachycardia with block. It's a common problem, and you see it because of the way the AV node behaves. Remember that the AV node is not capable of rapid conduction, in part because the cells of the AV node depolarize because of calcium currents that run into the cells, and the action potential has a much slower upstroke than the sodium-dependent cells of the bundle branches and the Purkinje fibers. So the AV node behaves in such a way that if the atrial rate is excessively rapid, the AV node will fail to conduct all those impulses. We've seen something like this when it comes to non-conducted PACs. So if the atrial rate reaches a certain point, the AV node will not be able to let those impulses through on a one-to-one basis. And you'll start to see AV block occur by virtue of the rapid atrial rate. So atrial tachycardia with block is a very common diagnosis, and it's based on the way the AV node behaves when the atrial rate gets too fast. Now, it doesn't matter if you have an atrial tachycardia that's due to reentry, or if you have an ectopic focus that's firing rapidly. If they're above whatever rate the AV node is capable of conducting, then you'll encounter some degree of AV block, and we'll show you different presentations of this. So here's an example of an ECG. It's a 12 lead, and as you scan across, you look at the forest first, you'll notice that there seems to be some kind of irregularity, but there's a regular pattern to it. So you could call it regularly irregular. Specifically, I see groups of 4 QRS complexes followed by a pause, 4 QRSs and a pause, and so you have group beating. Each group is 4 QRSs in duration. Now, when you hear group beating, you should think AV block. You have to start to think Wanky back, because type 1 second degree AV block often presents with group beating. And I tell people, when you see group beating, the first thing you have to do is look for P waves and see if you have AV block going on. If we scan this cardiogram, where's the best place to look for P waves? Well, I think the best place to look for P waves is in the little pause here, because when you have a period where there are no QRSs, it gives you a good chance to look for P waves. And I would say that this is one right here. Let's look at some other leads. During the pause, indeed, you have P waves here, which you see in another lead. And in fact, you have one here in lead 1. So at the end of each pause, there appears to be a P wave that conducts to the QRS complex with a borderline PR interval. It's close to 200 milliseconds. But look at the P wave morphology. It's up a little bit in 1, but you notice it's negative in AVF. In fact, 2, 3, and AVF are all negative. And so this P wave is originating from somewhere in the low part of the atrium and traveling up towards the head. So this is clearly some kind of atrial arrhythmia. It's not sinus. The trick is to try to figure out where the rest of the P waves are. So if you kind of scan in between, I hope that you would actually notice that this very sharp deflection here, midway between the two beats, is the next P wave. And if you kind of scan across, you see another one here, and then one that's even here. Now, what you should notice is that the relationship between the QRS complex and the subsequent P wave is changing. Notice that this R to P interval is longer, and then the P comes a little bit earlier, and then the P comes even earlier still. The relationship between the P's and the QRSs are changing. If you look at the PR interval, in fact, you can see the PR is getting longer and then longer still. Now, the question is, are these P waves regular? Because if they are, then we are looking at type 1 second degree AV block. So let's pull out our calipers. Now let's move our calipers around, and if you put it on the first P wave, and then I've set it up so that you are on the next P wave. Now let's march them on through, and you can see this P wave occurs at the same interval. It's on time. And this P wave seems to be on time. And if you keep on moving it, you see this negative deflection here. And if you put your calipers, you see that this occurs on time as well. So the P to P interval is regular. The rate, if we put the calipers on a heavy line, is about 120 beats per minute. So you have this ectopic atrial tachycardia at 120 beats per minute, and the PRs are getting longer, and then this P wave right here fails to conduct, and then the next P wave occurs on time and conducts with the shortest PR of the whole cycle. So the diagnosis here, we know it's not sinus, it has to be atrial tachycardia with block. Now, what kind of block? We can call it Winky back. Some people will call it type 1 second degree. Well, what's the ratio between the P's and the QRSs? Remember, the second number of the ratio is the number of QRSs, and there's always going to be one more P wave. So since there are 4 QRSs, we know that this is 5 to 4 conduction. So that's the ratio, the number of P waves to the number of QRSs, 5 to 4. So this is atrial tachycardia with block, PAT with block, however you want to call it. But you've got to be able to look for these P waves, map them out, determine the relationship between the P's and the QRSs. Notice the P's were coming earlier and earlier in the R to R interval, and that's because the PR was getting longer. And then this one clearly occurs on time, and it fails to conduct to the ventricles. It's not a non-conducted atrial premature beat. That P wave occurred on time, and it blocked in the AV node. All right, so let's go on to the next example. Now here's a rhythm strip, and I'll tell you time and time again during this course that you should never believe what you read. In other words, if you're looking at a rhythm strip and someone has written 3.6 second run of AFib, always check it yourself. Never believe what anybody else has written, because you're going to be the ECG expert. When we scan across, we do see this rapid irregular rhythm here. I think everyone would agree that there does seem to be a P wave followed by the QRS complex with a PR interval that's at the maybe a little bit longer than normal, maybe 210 milliseconds or so. But this certainly seems to be a sinus beat that leads off this strip. And then all of a sudden you have these irregular rapid beats, and you're trying to figure out if there's a pattern to it. Maybe there is, maybe there isn't, but let's look at what the atrium is doing. Well, if we look at this R to R interval and we scan around, we see a nice T wave here, and then there's this sharp deflection right here. This would appear to precede this QRS complex. So this sharp signal, remember P waves have high frequency components to them as opposed to T waves. That sharp deflection is a P wave. I don't see any other P waves in here. And this conducts with a first degree AV block to the ventricles here. Now let's look at the next T wave, the T wave of this QRS complex. What does it look like? It certainly does not look like this T wave. It's got this really deep, sharp-looking squiggle. It's almost like a shark came by and took a bite out of it. And if I get rid of some of my annotations here, I think it's safe to say that this signal right here looks a lot like this signal right here. So sure enough, this is another P wave. And what's the rate? The rate's about 150 beats a minute. Now this conducts with a very long PR interval to this QRS complex. But you get in a pattern here that you have a slightly longer PR, a very long PR, and if we try to map out, well, where would the next P wave occur, look about 150 beats per minute or 200 milliseconds about, and you see a little bump here. That bump was not present here. If you compare the QRS complexes, you've got a little tiny spike at the beginning of the QRS, a little tiny spike here, but now you have a very large bump. That is the next P wave, or at least the beginning of the next P wave. And sure enough, it occurs on time. Now, if that's the next P wave, where's the QRS complex that follows it? There doesn't appear to be any. Well, let's keep looking at the P waves. Do they map out? Well, if you look another 400 milliseconds out, you see this signal. And then you see this signal. And then you see this one. You have to use your eyes and try to pick these signals out. And here's the next one. And the next one. And so what's happening is that you have this atrial tachycardia that's proceeding through the strip at a rate of about 150 beats per minute. Once I point these out to you, don't you notice that they're there? As soon as I sort of like put the dreaded arrow sign here, doesn't that jump right off the page at you? You say, oh my goodness, I should have seen that. How did I miss that? So what you have here is a run of atrial tachycardia at 150 beats per minute. But what's happening to the AV node is the AV node cannot keep up with it. The AV node is blocked up. You have a PR that gets longer. This one blocks. This one conducts with a fairly long PR. This one obviously didn't go anywhere because there's no QRS following it, so that blocked. This one conducted to this QRS, this one conducted to this QRS, and then this one blocks. So you have this weird kind of unusual winky back-ish kind of pattern, and then this is the last P wave of the tachycardia. Well, I guess it's kind of debatable whether there might be one buried in this QRS complex, but I don't think so. The P here is very wide. It's a wide P because obviously the patient has a lot of intra-atrial conduction delay. It takes a long time for this signal to get around the atrium, so the P wave is long in duration. And if it had started here, I think you'd probably see the tail end of it on this side of the QRS. So my feeling is that this is the last Mohican. This is the last P wave that conducts, and then the tachycardia stops. And you have no QRS after that. What you have is a compensatory pause until the next sinus beat kicks in and conducts at the sort of the baseline PR interval of about 220 milliseconds or so. And then you're back in sinus rhythm. So if I hadn't pointed those P's out, you might say, oh, look at that, a run of atrial fibrillation. Well, of course, we didn't cover atrial fibrillation in this course yet. We're going to do it in the next couple of sections. But atrial fibrillation would clearly not look like this. This is atrial tachycardia with AV block, and you should be able to recognize this if you take the time to look at the little details. Becoming an ECG expert means you have to carefully analyze these strips for the subtle details, but now that I've shown you what it looks like, and after you practice a few times, those little details will pop right off the page. You'll be able to pick those up right away. The last one I want to show you is another 12 lead, and it's very deceptive because when you first start to look at the QRS complexes, you see that they are clearly regular. They're kind of marching on through. And when you look at lead 2, you'd say, this looks like a nice P wave here. And it almost looks like just sinus rhythm with a first degree AV block because the PR is about maybe 260 milliseconds long. You'd say, okay, no big deal, sinus rhythm first degree AV block. And in fact, the cardiologist who read this ECG called it just that. But when you look at all the P waves, make sure that they're really sinus P waves. Remember, they should be up in AVF, and they should also be up in 1. But when you look at this P wave in 1, it looks kind of weird. It's very low in amplitude, it has a little double bump, and it really kind of doesn't look like a sinus P wave. Well, that's where you have to start looking at all the P waves. And when you look at V1, you see this kind of P wave-ish looking signal in front of the QRS. Well, you need to be able to ask yourself, what am I missing? Is this really just sinus with first degree, or is there something else? And I always teach people, when you see a P wave that doesn't look like a regular P wave, look in between the two P waves. And if you just look in between, what you'll see is a sharp little bump on the T here in lead V1, okay? And if you look at lead 1, you'll see the same sharp deflection on the T wave here. So what you're dealing with here is an atrial tachycardia with 2-to-1 conduction to the ventricles. It's harder to see the bumps in the other leads, but what I can show you here in lead 3, remember that this P wave is upright. This P wave is upright. If you look halfway between those P waves, look at this bump on the ST segment. ST segments aren't supposed to go up like that. ST segments are supposed to be flat. So that's a clue here that what you're dealing with is an atrial tachycardia with 2-to-1 conduction to the ventricles. So if the ventricular rate here, if I measure it 300, 150, 100, it's about 85 beats per minute or so. So the atrial rate must be twice that. So that's 170 beats per minute. So we have an atrial tachycardia at 170 beats per minute with 2-to-1 AV block, you can call it, or 2-to-1 AV conduction. Now, remember, I like the word conduction better than block because if a normal person's atrial rate suddenly got to 170, it would be very likely that the AV node would fail to conduct all those impulses. So that's why I prefer the term conduction, 2-to-1 AV conduction, because the word block makes you think there's something wrong with the AV node. And under these circumstances, the AV node would simply be exhibiting normal behavior. So now that you've seen a few examples of atrial tachycardia with block, we'll go on to the next chapter, which deals with atrial tachycardia and aberrant conduction. It's one of the most difficult ECG diagnoses to make, but I think it's the most fun. So for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to continue our discussion of atrial tachycardia in this section. This chapter is on atrial tachycardia with aberrant conduction, or aberrancy. This is the bane of most monitor techs because they're constantly trying to figure out if a wide complex tachycardia is atrial with aberrant conduction or is it ventricular tachycardia. Now, there'll be a whole section in diagnosing wide complex tachycardias in the advanced course, but for the sake of this discussion, we'll talk about what atrial tachycardia with aberrancy looks like and how to try to identify it on a rhythm strip. So imagine you have some kind of atrial tachycardia that's going round and round at a rapid rate. You know the AV node may or may not conduct them 1-to-1, but let's assume the AV node is good at conducting. What happens if this tachycardia reaches the bundle branches and encounters a functional bundle branch block or some other kind of rate-related interventricular conduction delay? Well, you're going to get widening of the QRS complex because this rapid beat will not be able to get down one bundle, but can go down the other bundle and then sort of like dipsy-doodle very slowly through the rest of the myocardium, giving you a wide QRS complex. The things to look for when you're trying to diagnose an atrial tachycardia with aberrant conduction is that, of course, the wide complex tachycardia should start with a P wave, and you should be able to see P waves marching through at a relatively normal or slightly prolonged PR interval. So remember, P waves can be superimposed on a T wave, and they'll look like a very sharp deflection, up or down, depending upon where it's coming from. And then the QRS will be wide because of interventricular conduction disturbances. And if you're lucky, you should be able to map out the P waves as they're marching through this arrhythmia. Well, let's take some real examples here. As I mentioned in the last chapter, don't ever take what you read on a rhythm strip as being the truth. Always figure it out for yourself. This patient supposedly had possible 12 PVCs in a row. I think you would normally call that non-sustained ventricular tachycardia, but we'll go over that in the last section in the basic course on ventricular arrhythmias and how to name them. But if we look at this rhythm strip, we can see that it starts off with something that looks like a sinus beat with a fairly normal PR interval. And then when you look at the forest, you see that there's this run of a rapid arrhythmia in 12 beats. And if you look at the QRS complex, it looks different than the underlying beat. It's deeper, it's a little bit wider, but it's not very wide. And you have to wonder, why is this looking different from the underlying rhythm? Is it because of an interventricular conduction delay or aberrant conduction? Or could this be some kind of ventricular arrhythmia? Well, how does it start? If we examine this T wave, it looks fairly flat, but obviously this T wave has a P wave superimposed on it. And this P wave precedes the first beat of the tachycardia, and the PR interval looks to be even just a little bit longer than the underlying PR interval. So that would make you think that this P wave is an atrial premature complex, or APC, or atrial premature beat, and it resulted in a widening of the QRS complex because it landed right at the point where one of the bundles, or at least part of the conduction system, was refractory. And so you had an APC with aberrant conduction here. Well, what comes after that? You have another QRS complex, which looks exactly the same as this one, and there does appear to be a P wave in front of it. If you look at the PR interval, it's even gotten slightly longer. And if you scan across, I think it's easy to see that there are P's kind of marching through, each one superimposed on the previous T wave. And in fact, what I demonstrated in earlier videos is that the relationship between the QRS complex and the following P wave varies. So you can see this one comes a little bit sooner, and then this one comes a little bit later. So it's not part of the T wave. It's separate from the T wave. It's moving around, and that gives you more evidence that this is indeed a P wave, and each one of these P waves does appear to conduct one-to-one to the ventricles with variable PR interval depending upon how fast the tachycardia is, until this P wave, which is the last P wave of the tachycardia, and it conducts to the ventricles. And then notice that this T wave doesn't have a bump on it. And so there's no P, and of course there's no QRS following it. So this was a run of atrial tachycardia, but the QRS widened out because of the rate, and I think it's fair to call this a rate-related interventricular conduction disturbance or rate-related aberrancy. So it's atrial tachycardia with aberrant conduction. Well, it was mislabeled on the strip, but I'm sure you won't make that mistake the next time you see a strip like this. Okay, let's go on to one more example here. And this actually looks really nasty. Yeah, I mean, a lot of people would look at this and seriously consider whether this could be a run of ventricular tachycardia, which, of course, we'll get to in the next couple of sections. Looking at the forest, you have 3 fairly normal beats and then this run of a wide complex tachycardia what looks like a normal beat again, and then another different wide complex tachycardia. It's 4 beats of a wide QRS, but it looks different than these beats. But remember what I told you about atrial arrhythmias with aberrant conduction. What you're trying to do is look at how it starts. You need to see how it starts in order to get a clue as to where it came from. So here we see a nice P and a QRS complex, and here's another sinus P and a QRS complex. So everything is fine up until this point, but here's the key, is looking at this T wave compared with this T wave. Is there a difference? Do we see anything that looks like a P wave? And yes, indeed we do. Right there, there's a little notch in the T that did not exist either here or here. Always look at the T wave, that's where the clues are. So if there is a P wave and it's premature, because obviously the next sinus beat would have occurred somewhere here, this is a PAC, and the QRS complex that follows that PAC has a fairly normal PR interval, a little bit longer, in fact, I think, than the intrinsic PR interval. And that's because it's a premature beat that encountered a little bit of delay in the AV node. You have this wide QRS complex that occurred because of a functional bundle branch block. And it kind of, let's assume that this is V1, it kind of sort of has this left bundle branch block looking pattern with a deep QS kind of appearance to it. But then where'd all these come from? Well, let's look in front of each QRS complex and see if we can identify a P wave. So here's this QRS complex. Is there a bump on the preceding T? Yes, indeed there is. It's right there. And let's look at this one. I think this T wave looks very pointy right here. And here again. And here again. And look, there is a P wave that's clearly identifiable in front of every one of these QRS complexes. This one becomes a little bit difficult to see because the P's and the QRSs are slightly moving apart from each other. But if you take your calipers, and I'll pull them up right now, if you take these calipers and put them on the P waves, you'll see that they actually do map out. It's quite regular. And if we put our calipers on a heavy line, we can see the rate here is about 200 beats per minute. And those P waves march out, and they're coming right on time. And I would say that this is a run of atrial tachycardia with aberrant conduction. But you want to see something really cool? Here, you can see that there's a bit of a pause. And following that pause, there's a P that occurs that's on time, if we're considering this to be an atrial tachycardia. And then the next one occurs on time as well. Now, why did this QRS become narrow and normal looking? I'll tell you why. Because this P wave blocked in the AV node. You had a second degree AV block that occurred right there. So this P conducted to the QRS, but this P blocked. Now you have the pause that refreshes, and the bundle branches recover. This P now conducts with a fairly normal PR interval down the bundle branches that are both capable of conducting. But then this P, which is also part of the tachycardia, I showed you it came on time, now, of all things, encounters a different bundle branch block. Look at how this QRS complex is going in the opposite direction. So this is a left bundle pattern, and this is a right bundle pattern. And the PR looks a little bit long, but if you take those calipers and move them, you'll see that here's the next P, and here's the next P, and here's the next one. And so these P's are marching on through. But what you had was one bundle branch block, and then you had one P wave that failed to get down the AV node. That pause that resulted allowed for normalization of the QRS complex because now both bundles are conducting. But then the next P wave from this tachycardia wound up finding the other bundle blocked. And then you have a run of the opposite bundle branch block. Now, this is not the same as bilateral bundle branch block or anything crazy like that. This is simply one aberrant conduction, and then it happens to be followed by aberrant conduction in the other direction. This doesn't necessarily mean that the bundle branches are diseased, because it's coming at a rapid rate. This is 200 beats per minute. And so it's a functional bundle branch block. It doesn't mean necessarily that the bundles are sick, but under these circumstances, they did not function properly. But this is a great strip here. I think if you showed this strip to a lot of people, they would not get that as being an atrial tachycardia with aberrant conduction. So I hope this lesson straightens things out for you and gives you some ammunition in fighting the idea that every wide complex tachycardia is ventricular in origin. The last video in this series is going to talk about unusual types of atrial tachycardias, and I hope you enjoy that one as much as this one. So this is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to finish up this section on atrial tachyarrhythmias with a discussion here on wandering atrial pacemakers and multifocal atrial tachycardia. In fact, these are like two of the same problem, except one's faster than the other. By definition, a wandering atrial pacemaker would be less than 100 beats per minute, while multifocal atrial tachycardia would be greater than 100 beats per minute. Well, what are these arrhythmias anyway? Well, remember the normal sinus rhythm comes from the sinus node, and you should have electrical signals originating from the sinus node and spreading rapidly across the atria. Well, of course, this brings the atrial vector down into the patient's left, and you should see positive P waves in lead 1 and also lead AVF. You know that atrial premature beats arise from somewhere else in the atrium, and because the electrical signal is going in a different direction, the P wave will look differently. Well, imagine if you have more than one spot that's causing APCs. Imagine if you had, let's say, 2. Well, if you count the sinus node as being a third site, you should see 3 different P waves. And that's what we look for in diagnosing either multifocal atrial tachycardia or wandering atrial pacemaker, is a minimum of 3 different P wave morphologies. Imagine that you're looking at a rhythm strip like this and you're thinking, oh, look at that. Well, these look like normal sinus beats here with P waves and QRS complexes. And this is clearly an early beat. It's a premature atrial contraction. And then there seems to be a compensatory pause, another sinus beat. And then here's another PAC, but the P wave looks different. This one is a biphasic P wave, means it goes up and then down. It goes in 2 different directions. That's what biphasic means. But this P wave only goes down and not up. And so what you have here is sinus rhythm with multifocal PACs. Now that's different from multifocal atrial tachycardia. These are multifocal PACs, but you can see that the predominant rhythm is a sinus rhythm. So when you see sinus rhythm with multiple atrial premature beats that have P waves that look different from each other, you can call it multifocal PACs. Okay, now what does MAT look like? Okay, MAT would look like this. You have some P's that are going up. You have some P's that are going down. You have some P's that look tall, and some P's that are biphasic, and so on and so forth. And there's not one single P wave morphology that predominates. So you really don't have sinus rhythm with multifocal APCs. What you have is multifocal atrial tachycardia, or MAT. This is commonly seen in people with lung disease, like bad COPD. They'll often come with arrhythmias like MAT. Well, here I've drawn it with a rate of somewhere around 120 on average, thereabouts. But imagine seeing the same kind of arrhythmia with a rate less than 100. Then you wouldn't call it multifocal atrial tachycardia, because after the tachycardia means greater than 100, you would call it wandering atrial pacemaker. And what does that mean? It just simply means that the P wave is not coming from the same spot all the time. It's not originating from the sinus node. It's kind of moving around. Now, we're not talking about P waves that just vary slightly, maybe just get a little bit flat sometimes, because the sinus nodal complex is actually a large area. We'll talk more about that in the advanced course, but even during sinus arrhythmia, you can see minor changes in the P wave morphology as the electrical signal emerges from different spots from the sinus nodal complex. But here you clearly see there are some P waves that are completely upside down. Some are biphasic, some are taller than others. And so this is an example of what multifocal atrial tachycardia looks like. Well, let's look at a real tracing here. And this is actually an arrhythmia that does not occur too often. And this is a real tracing from the hospital. There's a little bit of noise here, some high-frequency artifact that unfortunately you have to look past. But if you just look at AVL, you can see that some of the P waves are inverted. This one is flat, and this one is clearly upright. You can see in other leads, this is very tall, and then this one is actually a lot flatter. Here you have a biphasic P wave. This one is inverted, and this one is upright. So even in lead 3, you have 3 different P wave morphologies. Unfortunately, the rhythm strip is not as clear because of the artifact, but you have a sense that there is not one fixed P to P interval that is occurring on a regular basis that would suggest that there's an underlying sinus beat. Maybe this longest interval here, and you see a sort of a tall P wave, and that kind of looks the same as this longer interval with a sort of a tall P wave, and maybe here. So maybe there's a little bit of a sinus rhythm that's trying to break through. But the majority of the P waves are coming from all different spots in the atrium. Okay, so this would be an example of MAT. Here's another example that I found. And again, if you kind of glance across, you see that the rate here is just a little over 100 on average. And when you look at the P waves, some of them are flat, some of them are biphasic, some of them are flatter, some of them are taller. This one is very tall. This one is very early and seems to have 2 phases to it. So it's almost like the electrical signal is originating from different parts of the atrium all at the same time, like they're competing with each other. So we'll actually learn in the advanced course that the electrophysiologic disturbance most likely to cause MAT is a disturbance in calcium handling within the cells. And often these patients respond best to calcium channel blockers like verapamil. But as I said, this is a kind of a rare arrhythmia. We don't see it too often, but you should be able to recognize it based on the variable P wave morphology. Remember, you need to see at least 3 different P wave morphologies to say that either wandering atrial pacemaker or multifocal atrial tachycardia is present. And on that note, we complete this section. It was a long, complicated one, but I'm glad we got through it. In the next section, we're going to talk about a related arrhythmia known as atrial flutter, and I hope that I'll be able to give you some insights into atrial flutter that you hadn't thought about before. So, this is Dr. Nick. Thank you for being a subscriber to the Ecg Academy, and remember to sign up for the weekly Chalk Talks so I can keep challenging you with more difficult tracings and get you to become an ECG expert too. Hi, this is Dr. Nick with the Ecg Academy, and we're starting a new section now on atrial flutter. Now, atrial flutter is not as common as some of the other atrial tachyarrhythmias that we'll see. We've already covered supraventricular tachycardia or atrial tachycardias. And you can see atrial flutter maybe accounts for about 1/4 of the atrial arrhythmias you might see in an emergency room. And it's a very specific kind of arrhythmia that's caused by rapid signals originating in the top chamber. So imagine you've got this electrical signal that's going around and around in the top chamber. And you say, well, that's a lot like atrial tachycardia. The difference is the rate. In atrial flutter, what you expect to see are rates in the range of maybe 225 to about 350 beats per minute. So if you see heart rates in that range, then you can correctly classify it as atrial flutter. Now, there are different kinds of atrial flutter, which we'll talk about in the advanced course, and the differences have to do with where this atrial flutter is coming from. If it's coming from the right side of the heart or the left side of the heart, it'll give you a different appearance on the electrocardiogram. But for the sake of this basic course, I want you to understand that anytime you see atrial rates in this range, we're talking about atrial flutter. But there's one thing that sets atrial flutter apart from other arrhythmias like atrial fibrillation, and that flutter is an organized arrhythmia. That means that all the beats look the same. If you look at this animation that I created to show you what atrial flutter looks like in action, you can see that here in the right atrium, I've essentially created what looks like an electrical signal traveling round and round in a circle. But you can see every time it goes around, it takes the same pathway. It may cross through Bachmann's bundle to the left side as well. And of course, the AV node is going to conduct as many impulses as it can to the ventricles, depending upon what kind of shape the AV node is in. But the point is the signal is going round and round in a circle. Now, sometimes atrial flutters can come from a focal source, and we'll talk about that in a later lesson. But because the atrial signal is consistently going around in a circle or consistently arising from one spot in the atrium, what you see is characteristically a sawtooth pattern of electrical activity in the atrium during atrial flutter. Now, sometimes it's a nice-looking cross-cut. I like to call it the Black and Decker syndrome. How many people are going to get that joke? But sometimes you'll see different kinds of sawtooth patterns. The point is that during atrial flutter, the atrial signals always look the same. On occasion, you'll see more of a sinusoidal rhythm, and what you're really looking for is a heart rate somewhere in the range of about 225 or 250 to 350. So that's how you're going to make the diagnosis of atrial flutter. Of course, you'll see QRS complexes in this rhythm every now and then, depending upon how rapidly the AV node is conducting. Well, let's show you a couple of examples. This is an example of a rhythm strip in a patient who has atrial flutter. And in this case, at least, you can believe what's written on the strip. I vouch for it this time. But what you see is when you look at the forest, in this case, you have irregular QRS complexes. And if you measure the rate as 300, 150, 175, so right about 75 beats per minute, and it's really quite regular. And then when you look for P waves, what you see in between the QRS complexes is this very clear sawtooth pattern. And if you ignore the QRS complexes, you'll see that that sawtooth pattern marches on through. It's very consistent, and in this case, pretty unmistakable. Now, following the QRS complex, you see that this downgoing sawtooth wave doesn't go down as far as the rest of them. You see how deep these are? And this is very, very deep. And then right following the QRS, it's not so deep. Why do you think that is? Well, it's because the QRS has a positive going T wave, and when you get the positive upgoing T wave and the downgoing deep flutter wave, when they sort of mush together, the sum of those two signals is a lot flatter than either one alone because they're going in opposite directions. So that explains why you see how this T wave is going to depress the depth of the flutter wave, and that explains why you have to be careful, because you don't always see the flutter waves as clearly as you do in this strip. In fact, sometimes you have to look for them. So here's a great strip, and when you look at the forest, you see that it is very irregular here. You've got a few very long intervals and an even longer one, and then you've got a bunch of short intervals, and it seems to be irregular but without any pattern to it. Most of the QRS complexes are very narrow, but you do have one wide beat here. So now when you start to look in between the QRS complexes, you are looking for P waves of some sort, something that you can hang your hat on. And you see a bunch of junk in here, and you don't see a discrete P wave necessarily, although you're starting to see little sort of negative deflections here, and you wonder, could that be a P? And then in the front of this beat, there's a kind of a negative deflection here, and then in front of here, there's a negative deflection. But when the baseline kind of settles down, and you look in between these long R to R intervals, you should be able to start to recognize that there's this repeating pattern. There are these downgoing squiggles that actually represent the flutter waves. People refer to these as F waves instead of P waves. And in this case, they don't have a nice gradual up and down sawtooth pattern, but rather they're more flat, and then you get a sharp downward and a little overshoot, and then another flat area, and then a sharp down signal, an overshoot, and then another flat area. So this is just a different appearance to the flutter waves. But let's say if we blow this image up a little bit, and we take a pair of calipers and put the calipers down on these flutter waves, you can see that they do map out very nicely. And there's somewhere, if you put the caliper down, somewhere at a little bit less than 300 beats per minute, about maybe 275 or 280 beats per minute. The cycle length of the atrial flutter is about 220 milliseconds. You get 272, so that's pretty close. Well, anyway, getting back to this strip, what you see are these flutter waves indeed marching through at a steady rate. The AV node occasionally passes every other impulse down, so that you get ventricular rates in the range of about 140 beats per minute, which is roughly 1/2 of the atrial rate. And so in this region right here, you have basically 2 flutter waves for every QRS complex. And we refer to this as atrial flutter with 2-to-1 conduction. I'm going to spend more time with 2-to-1 flutter in the next lesson. But in this case, I want you to notice that at times this AV node breaks up. Remember, the AV node determines what the ventricular rate is going to be. And so sometimes you'll get more block in the AV node and less impulses will get to the ventricle. So in this case, you have 1, 2, 3, 4 flutter waves in between these 2 QRS complexes. So this is 4-to-1 flutter, as is this. So you can get a sense of how well the AV node is conducting by the ventricular rate, which is a function of how many flutter waves are actually getting through the AV node. The key to recognizing atrial flutter is that you have to look for it. It's very important to try to nail down what the atrial rate is and notice that every flutter wave looks the same. Even though there may be some variations because of superimposed T waves, for the most part, every flutter wave is looking the same. And that just verifies that what you have is an electrical signal that it's either going round and round the same pathway each and every time, or less often you may have one fixed focus that's firing at a rapid rate, and the signals are spreading across the atria in a very organized fashion every single time. So with this introduction to atrial flutter, go on to the next video, and we'll discuss 2-to-1 flutter and how it can often masquerade and be difficult to diagnose unless you're looking for it. So for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick, continuing our discussion of atrial flutter. And what I want to talk about on this chapter is atrial flutter with 2-to-1 conduction. It's a very common arrhythmia that you need to be able to recognize because sometimes it masquerades as other things. So let's review what atrial flutter is. We're talking about an electrical signal going round and round in the atrium. And keep in mind that the AV node ultimately determines the ventricular rate, and it's affected by a number of things, including age, the presence of drugs, the autonomic nervous system, which means that if somebody does some exercise and their adrenaline levels go up, the AV node conduction will be enhanced. On the other hand, while they're sleeping and the nervous system is in a relaxed state, the AV node conduction may not be as good. And so the conduction of the atrial flutter, remember, atrial flutter, we're talking about 225 to about 350 beats per minute. The ventricular rate can vary dramatically. Let's take, for example, if you have 300 beats per minute. Under some circumstances, for example, if the patient walks up a flight of stairs, you can get 2-to-1 conduction, and that gives you a ventricular rate of 150. On the other hand, if they're a little bit more relaxed, you can have 3-to-1 conduction, which gives you a ventricular rate of 100. And if they're sleeping, they may get 4-to-1 conduction, which gives you a ventricular rate of 75. And so heart rates can vary dramatically depending upon the patient's activity, depending upon what drugs they may be taking. And in fact, if you come to the emergency room, intravenous medications can be given to block the AV node, medications like adenosine or verapamil or diltiazem. And these will have a marked effect on the conduction through the AV node. In fact, we often use these medications as a diagnostic tool in the emergency room. All right, well, let's take a look at the first ECG for this chapter. Or when you look at this 12-lead ECG, the first thing you notice is that the QRS complexes are pretty fast. In fact, if you kind of like scan across in the beginning, you can see that the R to R interval is less than 400 milliseconds. We're talking 300, 150, so it's maybe 152 beats per minute, 155 perhaps. For those of you who train your eyes, you can see that the QRS is slowly moving to the left of the heavy line. So you can see that it's a little bit faster than 150, and I'm sure you can calculate it if you took 6 seconds worth and counted up the R to R intervals. We're talking about a very rapid ventricular rate. And when you look for P waves in front of each QRS complex, you notice that there are signals that precede the QRS complex, but they don't look like discrete P waves. There's no isoelectric interval before or after the P wave. There seems to be sort of a slanty appearance to it. And this is something that you really have to recognize as being evidence of atrial flutter. Remember, most atrial flutter gives you a sawtooth pattern, and what you're seeing is a slanty part of the sawtooth that's apparent. And when you start to see that, you have to start looking for evidence of atrial flutter. And with this ventricular rate of 152, then you're most likely dealing with 2-to-1 conduction. So let's try to prove it. Where are the flutter waves? Well, here's a great hint. Look for the QRS complex that's smallest in size, that's most isoelectric. And this way, the QRS doesn't get in the way and you can see what the atrium is doing. And I think if you look very carefully, you can see that there are flutter waves here and here and here and here. And in this lead, they seem to be going up a little bit and then down and up and then down. And so you've got this repeating signal going through here at close to 300 beats per minute. Looking at other leads, you can see the same kind of sawtooth pattern. But if you notice that when you have 2-to-1 conduction, sometimes it's very hard to see the flutter waves. That's why you should look at the whole forest. So if you scan the forest and look through, you'll actually see right here, the QRS complexes break up a little bit, and over here as well. And that's when you can actually see the flutter waves very clearly. You see them going down and up and down and up. Right there, you can see these flutter waves very clearly. And in fact, if you look in V1, that's a very good place to look for flutter waves. You can see them marching through and get a sense that, indeed, this is flutter. With variable conduction over here, we say variable conduction when it's not a fixed ratio of 2-to-1 or 3-to-1. And then look at the very end. And pretty much the flutter waves are very obvious in this one little spot. So mostly this is 2-to-1 flutter. But as I mentioned, it's sometimes hard to see those flutter waves, and you really have to look very carefully for periods in the ECG where either the signal breaks up a little bit, here the AV node just kind of slowed down briefly, and it allowed you to see those flutter waves marching on through, or then sometimes you have to just use your imagination. Well, you say, what? Use your imagination? Well, let me show you the next ECG here. Here's a patient who comes to the emergency room with palpitations. You can see the QRS complexes are very regular throughout the whole thing, and it's quite fast. Here, if you look at a heavy line, you can see the next QRS complex is just a little bit over 400 milliseconds, and it's marching away from that heavy line as the beats go across. So we're talking a heart rate of a little less than 150, maybe 148 beats per minute. And it's very regular. It's like a clock. Whenever you see heart rates in the range of 150, actually anywhere between 120 and 170, always think atrial flutter with 2-to-1 conduction, because those rates are consistent with this arrhythmia. Now you look for P waves and you see what looks like a P wave in front of the QRS complex. You say, oh, well, maybe this is the P wave here, because it's very consistent in front of each beat. But again, P waves usually have an isoelectric PR segment in front of them. Not always, but this just doesn't look like a regular normal P wave. And what you have to notice is this slanty part of the signal and this rapid upstroke, and see this as, okay, well, this may be a flutter wave. And in fact, if I was reading this ECG, I would definitely call this flutter with 2-to-1. Well, how do you prove it? You kind of have to look at each different lead, and you have to get a sense on whether you can maybe perhaps see that second flutter wave. The problem is that often the second flutter wave is buried in the QRS complex, and it's hard to see. V1, as I mentioned, is a great place to look, and you can see these upright signals. And if you take your calipers and you measure these signals, it's about 400 milliseconds. So look in between and see if you see something that falls right in between. And I think that this bump following the QRS complex is indeed the second flutter wave. It's deceptive because it almost looks like it's part of the QRS complex, but it's not. It's actually the flutter wave. So you're saying, well, how can I prove this? Well, sometimes in the emergency room, you can't really prove it unless you somehow affect AV node conduction externally. Now, there are lots of different tricks that you can do. For example, carotid sinus massage can activate a vagal reflex that slows AV node conduction down, but you can certainly do it pharmacologically, and this patient, in fact, received a dose of intravenous diltiazem, and this is exactly what we saw. This is the same patient after diltiazem, and now those huge flutter waves become apparent, and you can see that they have this very classic sawtooth pattern. Right? If I show you that original EKG, you can see those sawtooths are there. They're just hard to see when you have 2-to-1 conduction. So this is a special situation. 2-to-1 atrial flutter is sometimes difficult, But when you see ventricular rates in this range, have a high index of suspicion and try to prove it one way or the other if you're at the patient's bedside. Do an ECG and do carotid massage if you need to, or give something pharmacologic that will break up the AV node, slow the AV node conduction down so that the ventricular rate falls back, and then you can easily see what the atrium is doing underneath. This is an example of an atrial arrhythmia where the AV node is a bystander. Bystander means that the AV node is just simply passively conducting the impulses to the ventricle, and it's not involved in this circuit. It's not part of the tachycardia circuit. This is just a physiologic concept that you need to remember, because in the advanced course, we'll start to talk about different kinds of supraventricular arrhythmias and classify them according to whether the AV node is part of the circuit or not part of the circuit. Well, in the next video, I'm going to be talking about atrial flutter that doesn't look quite like atrial flutter, and ways to look for flutter waves that allow you to make the diagnosis when it's not as obvious as it should be. Well, for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and we're going to finish up our discussion on atrial flutter. And this chapter is about flutter that has an unusual appearance, flutter that looks deceptive and makes you think about something else. Here's a picture of a chameleon that kind of blends into its surroundings. And think of those flutter waves as kind of blending in and looking like something else. So let's get right to it. Now here's a 12 lead that I really enjoy showing people. When you look at the forest here on the rhythm strip, you see that it looks quite regular. The QRS happens to be a little bit wide, if anybody noticed. It's about 150, 160 milliseconds in duration, so there's definitely an interventricular conduction disturbance. And when you look for P waves in front of the QRS complex, you see what looks like a pretty nice looking P wave with an isoelectric segment following it. And it seems to be in most of the leads. You're looking at P waves. And if you measure this PR interval here, it's a little bit long, about 280 or 300 milliseconds or so. And people would be very tempted to call this normal sinus rhythm with a first degree AV block and an underlying IVCD, maybe a left bundle branch block. But if you call it that, you'd be wrong, because it turns out that this is not sinus rhythm. And the clue is to look at the forest, but then start looking at trees and make sure you look at every single lead to make sure you know what the rhythm is. And here's the clue, is in V1, you have very large, very prominent flutter waves that are marching through. And unless you looked at V1 and specifically analyzed the atrial activity, you'd miss them. You can see them a little bit in V2, but they're much, much smaller. But these big, giant flutter waves are marching on through. If you measure two flutter waves, you get a rate of about 100, and so the atrial rate here is around 200 beats per minute. Which it turns out that the patient's on an antiarrhythmic drug and their flutter rate has slowed down somewhat. If you look at some of the leads, you actually get a sense that there is a sinusoidal pattern. It looks like a sinus wave. And you see those flutter waves very, very subtly, but only in certain leads. So it only looks like a sawtooth pattern in some leads. And that's why I would call this a slow atrial flutter rather than a rapid atrial tachycardia. Because atrial tachycardia, I prefer seeing discrete P waves at a rapid rate with a fairly long isoelectric interval in between them. At this rate of 200 beats per minute, it's really on the border, and it's only the appearance of this sort of sawtooth pattern in some of the leads that would make me call this a slow atrial flutter with 3-to-1 conduction, because you have 1, 2, 3 flutter waves, the one superimposed on this QRS complex, corresponding with this QRS, and then you have 1, 2, 3 again. So this is really a slow atrial flutter with 3-to-1 conduction. The word slow in this case I'm using to denote that the atrial flutter rate is only 200 beats per minute, which is a little bit slow to be flutter, but we can see this when a patient's on a drug, and let's say that you have the atrial flutter that's going round and round in a circle, but under the effect of this antiarrhythmic drug, that electrical signal is slowed down to the point where the rate falls below 225. So this is kind of an unusual appearance, but it's flutter nonetheless, and that's why it will fool a lot of people into thinking that this is just normal sinus rhythm with a first-degree AV block. That's clearly not what it is. So make sure you always look at V1 to look for P waves, because you'll frequently see an atrial rate that's faster than what you initially measured. Okay, let's go on to the next one. Now in this 12-lead ECG, if you scan the forest, you see that the QRS complexes are irregular, and there does not seem to be any specific pattern. Some of these complexes are fairly fast, about 100 beats per minute, and this one's a little bit faster, about 120, and then you have a little break in the action. It slows down briefly, and then it speeds up, and then it slows down again towards the end. So there's no pattern to it. It seems to be irregularly irregular, and that makes you think that there's some kind of atrial arrhythmia going on. When you look at the QRS complexes and look for P waves in front of them, there do seem to be discrete P waves in front of some of the QRS complexes, but not everyone. This one does not look like the same P wave. This one looks like sort of in between, and some people would be tempted to start thinking about multifocal atrial tachycardia. You see, this one seems to be upright, and then there's one here that may be inverted. But the key here is to look at the long intervals, because that's where you'll see more atrial activity, because there's no QRS complexes to get in the way. And immediately I see that there are 2 bumps in a row. And even if you look at AVR, there's 2 negative bumps. And when you look at the rhythm strip here in lead 2, you see 2 bumps in a row. That basically establishes the atrial rate. The atrial rate here is about 250 beats per minute. Now, do we have very pretty sawtooth flutter waves? The answer is no. What we have are very short, discrete flutter waves with a long isoelectric interval in between them, so it looks more like this. It's flutter nonetheless because the atrial rate is 250 beats per minute. In some areas you have 2-to-1 conduction, but towards the end it looks more like 4 or 5-to-1. But this is a kind of an atypical appearance to atrial flutter, and in fact, we call this atypical atrial flutter. It's one of the types of flutter that you can recognize on a 12-lead, and we'll cover the different types of flutter in the advanced course. Just be able to recognize that you have an atrial rate of 250, and the fact that it looks like you have P waves in front of some of the beats is just coincidental. It happens when a flutter wave just happens to land in front of a QRS complex and gives the appearance that it's a P wave, but in fact the atrial rate is much faster because the other flutter waves are buried here on the T wave, and this one's buried on the QRS complex, and then you have one, and then it's buried in the ST segment, and so forth. So it's a sneaky kind of flutter that resembles something else, but you need to be able to recognize it in order to make the right diagnosis. Okay, we'll take one last example, and I think this is a little bit easier to recognize. When you start looking at the forest, you see there are some narrow complexes, there are some wide complexes. The narrow ones are kind of sort of regular, but not exactly. Sometimes the R-to-R intervals are a little bit longer. Sometimes they're shorter. Then there's these wide beats. So this is a bit more of a complex tracing than you've seen in other examples. When you start to look for atrial activity, and you'd say, oh, I know, Dr. Nick said look in V1. You really don't see anything that looks like a nice P wave. In fact, this, which you think is a P wave, is actually the T wave from the previous beat, as is this. And you don't see that here because the PVC throws a T wave off, but this is the T from this beat. So these are not P waves, they're T waves. And in V1 and V2, you really don't see any kind of atrial activity that you can hang your hat on. But again, you have to use your imagination. You have to look for patterns in the underlying baseline. Essentially, ignore the QRS complexes and try to see what's happening underneath them. If you do that, you'll be able to see these little bumps in lead 1, and you'll be able to see this kind of a sinusoidal pattern. It looks like a sine wave. What do I mean by sinusoidal? Mathematical sine wave is something that you learn in physics, and it looks kind of like this, where it's spending an equal amount of time above and below the baseline. And so it kind of looks like a sine wave. That's why I use the word sinusoidal. It's not a true sine wave in the mathematical sense, but doesn't look as sawtoothy as some of the other examples that I showed you. Probably the only one that looks like a sawtooth here is an AVF. So this is atrial flutter with variable conduction. And then what are these wide complex beats? Well, they're ventricular premature beats, or PVCs, whatever you want to call them. There's 2 of them here. And so the diagnosis here is atrial flutter. Why? Because the atrial rate is, if you measure the rate here, take this flutter wave, measure 2 flutter waves over, and you get 300, 150, 100. That's got to be about 115, so it's about 230. So the atrial rate's about 230 beats per minute. You have variable conduction and frequent ventricular premature beats, and that would be the rhythm of this 12 lead. When you get to the intermediate course, we start to analyze the details of the QRS complexes and looking for other things like ST and T wave abnormalities. But for this basic level course, what we're concentrating mainly is the rhythm, because that turns out to be the most complicated part of the ECG. So even though I call this a basic level, in fact, you're getting some very complex physiologic lessons and insights into reading rhythm strips, information that you won't get in any other course on the internet. And I'm very glad that you subscribe to the Ecg Academy. That's why I'm doing my best to turn you into an ECG expert. In the next section, we're going to cover atrial fibrillation, which is a very common arrhythmia. And the last section in this basic course deals with ventricular tachyarrhythmias. Well, until then, this is Dr. Nick with the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick, and we're starting a new section now on atrial fibrillation. As you can see in this pie chart, it makes up over 2/3 of the arrhythmias that we're likely to see in an emergency room, and so it's something that you'd be recognizing on cardiograms quite frequently. So let's talk about what atrial fibrillation is. Atrial fibrillation is an electrical disturbance in the atria where the electrical signals are chasing themselves round and round in different directions in a very disorganized fashion. And people have described multiple wavelets of reentry going round and round in different directions. Now, that's the classic idea of atrial fibrillation. And I'm planning to talk a little bit more about atrial fibrillation and the different types of AFib you can find in the advanced course, because in the last 10 years we've learned quite a bit about atrial fibrillation and where it comes from, and the idea of the trigger foci versus reentry circuits. But for the sake of diagnosing it on an electrocardiogram, I think this mechanism is pretty clear. Now I have my animation here, and I've shown you what looks like this random chaotic electrical activity in the top chambers. Now keep in mind that the AV node is going to pass some of those signals down. It can't pass them all down, but the AV node is designed to act like a safety valve, and atrial rates during atrial fibrillation usually exceed 350 beats per minute. Now the AV node really determines what the ventricular rate is going to be during atrial fibrillation. And we use the term ventricular response to refer to how fast the ventricle is going during atrial fibrillation. So you can have atrial fibrillation with a rapid ventricular response, a moderate ventricular response, or some people call it controlled ventricular response. And you can also have it with a slow ventricular response. And this refers to how fast the ventricles are going, and that's determined by the AV node. Remember, the AV node will not conduct as well at high rates. So even though someone's heart can go quite fast if they're in an organized atrial tachycardia, let's just say, or even sinus tachycardia, put it this way. When someone gets on a treadmill and we get behind them with a cattle prod and we have them run to their predicted maximal heart rate, their maximal heart rate or predicted maximal heart rate is 220 minus your age. So if someone 50 years old gets on a treadmill, you'd expect them to be able to reach about 170 beats per minute. Well, when someone goes into atrial fibrillation, even at the age of 50, it's very unusual to see rates that high. You'll usually see them in the 130 to 140 range if someone has a healthy AV node. And that difference between a predicted maximal heart rate during an organized atrial rhythm like sinus rhythm and the atrial rates during atrial fibrillation has a lot to do with this phenomenon of the AV node conducting worse when the atrial rate is very high and the AV node is being bombarded in all different directions. But just remember, it's very important to understand the concept that the ventricular rate is determined by the AV node itself. I hear a lot of cardiologists, when they see atrial fibrillation with a slow ventricular response, they'll call it sick sinus syndrome because the heart rate is slow. But in fact, you can't really tell what the sinus node is capable of doing because the patient's in an arrhythmia, atrial fibrillation, and their sinus node at that point is taking a nap. Now, if they were to go back into a normal sinus rhythm, their heart rate might in fact be quite normal. The slow ventricular response is more of a reflection of poor AV conduction and AV nodal dysfunction. So just keep that in mind as we go through these tracings. Now, recognizing atrial fibrillation on a cardiogram is actually quite easy because instead of having discrete atrial activity, because you have this continual chaotic activity, what you generally see on the ECG is a very wavy, disorganized electrical signal, and then every now and then you see a QRS complex, but there's no discrete P waves during atrial fibrillation. It just looks like electrical noise, in fact. Now and then, the atrial fibrillation can become very coarse. We refer to atrial fibrillatory waves that are very large as being coarse atrial fibrillation. And sometimes they can get so big that it almost looks like a P wave because it coincidentally lands in front of a QRS complex. But you have to make sure that if you're seeing what you think are P waves, that they're consistent in front of every beat. Those are just a few important considerations. Now let's get to the first tracing. When you look at the forest, what you expect to see during atrial fibrillation is that the ventricular rhythm is irregularly irregular. That means that there's no pattern to it. There's no group beating that you can recognize groups of twos or groups of threes. What you see is maybe 3 or 4 fast beats and then a pause, and you got a couple of fast ones and a little less of a pause and a little bit more. So there's no pattern to the irregularity, and that's why we call it irregularly irregular. Now, when you try to calculate the rate, this is where 3-second marks can come in very handy. The idea is to count up how many R to R intervals there are in 6 seconds and then multiply by 10. Now, this rate is somewhere in the range of 70 or 80 beats per minute when you take into consideration these long pauses. And when we look to see what the rhythm is, we're looking at the baseline and we see all this sort of rapid undulating effect. These little peaks here are less than 200 milliseconds apart. And so the atrial rate is clearly way above 300 and likely faster than 350 beats per minute. Sometimes you get big fibrillatory waves, and sometimes they get to be so small you can barely see them. Look at this long stretch in V1. This is pretty typical for what's known as fine atrial fibrillation, where that means you can see it, but it's very small and it's almost hard to recognize, especially here in V2. So just make sure that you're dealing with an irregularly irregular rhythm, that you see that there are fibrillatory waves on the baseline in between the QRS complexes, that there's not a consistent P wave in front of each beat that you could sometimes see if you're dealing with, let's just say, a sinus rhythm with very frequent atrial premature beats. And the more you see this, the easier it becomes to diagnose because you begin to recognize it almost immediately. And then it's just a matter of analyzing the individual QRS complexes for abnormalities such as IVCDs and bundle branch blocks and so forth. And that's going to be covered, of course, in the intermediate course when we deal with 12-lead ECG interpretation. Well, that concludes this introduction to atrial fibrillation. In the next video lesson, we'll go over more tracings with rapid and slow ventricular response, looking at fine and coarse atrial fibrillation. And then in the last lesson, we'll deal with more unusual kinds of atrial fibrillation, including aberrant conduction and something you've all heard of, but I'm sure you don't understand, and that's called the Ashman phenomenon. So, for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hey, this is Dr. Nick with the Ecg Academy, and we're going to continue our discussion of atrial fibrillation in this video. I'm going to show you a bunch of examples and show you how easy it is to diagnose it, but I also want to show you some things that you need to worry about so that you don't make the wrong diagnosis. Anyway, looking at this ECG, taking a look at the forest, you can see that there is some irregularity. The QRS complexes are clearly not marching through at a regular rate. And if you try to look for a pattern in it, you won't find one. And that's the hallmark of atrial fibrillation, and it's irregularly irregular. There's no real pattern to it. If there was, you would call it group beating and start looking for some kind of second-degree AV block. But atrial fibrillation should be irregularly irregular. The rate over here is on average about 80 or 90 beats per minute, and we'll keep that in mind when we go to label this arrhythmia. Looking at the R to R interval, the longer intervals are where you're more likely to be able to see what's happening. And what you can see is this sort of undulation of the baseline. The key here is that the baseline does not have a consistent electrical signal. Remember, the difference between atrial fibrillation and atrial flutter is that in atrial flutter, the signal is going round and round in a circle. Or less often, there's a focus that's firing rapidly and the signal is spreading rapidly across both atria in a very consistent manner. Either one of these situations gives rise to a very discrete, very reproducible, very consistent atrial signal that is regular and each beat looks the same. These flutter waves should look the same in the same lead over time. So the difference is atrial fibrillation is more of a chaotic problem. The signal is traveling in different directions, and it never really takes the same pathway twice. And so there should be no pattern to the electrical signal that you'll see. In fact, if you look at V1, you might be tempted to call this atrial flutter. You got these large, kind of fluttery-looking, almost sawtooth waves here in V1 that clearly are going upright. But at this part of V1, you can see that those waves are now going down. And so this is really more of a polymorphic or a variable, constantly changing rhythm. And even though it's kind of on the slow side for atrial fibrillation, we call it coarse atrial fibrillation to refer to the fact that the fibrillatory waves look very large and chunky looking, almost like flutter. And in reality, the atrial rate may slow down briefly where it could be in the range of 300 beats per minute. But at other times during the arrhythmia, it actually may be quite a bit faster. Here is clearly 350. The rate's constantly changing. The signal is constantly changing as well. And that's why we call this as a polymorphic arrhythmia, meaning the appearance of each individual signal varies over time. To sum it up, we have this irregularly irregular rhythm with this polymorphic, chaotic-looking baseline. In some areas, it looks like flutter, but clearly it's changing, and so it's not flutter. It's atrial fibrillation with a moderate ventricular response. Okay, let's look at the next one. This is the kind of cardiogram you'll see frequently in an emergency room, and when you first see it, it's very impressive, and the patients are usually rather uncomfortable. Glancing at the rhythm strip, you can see it's really quite rapid. The average heart rate here is over 150 beats per minute. It has to be in the range of 165 to 170. It's irregular. There doesn't seem to be any pattern. You get very rapid beats here, in fact, exceeding 200 beats per minute. If you look at this beat and this beat, it's less than 3 boxes across. So we're talking over 200 beats per minute in this one little brief area, and then it slows down a little bit further down here. But there's no pattern to it. So you have this irregular rhythm with a very rapid rate. Trying to accurately diagnose this as atrial fibrillation now is a bit of a challenge because you're really obligated to rule out other things. Things like multifocal atrial tachycardia or atrial flutter with variable conduction. And so it's important that you look in front of every single QRS complex, especially the ones with the longer R to R intervals, to see if you can get a sense of whether there is any kind of a consistent P wave in front of each beat or whether there's a consistent flutter wave that's marching through the entire strip. You really have to look at every single lead, especially V1 and the inferior leads, to look for flutter waves. Once you're satisfied that you don't see anything that looks like a discrete P wave or some kind of organized atrial activity, then you can call this atrial fibrillation with a rapid ventricular response. Some people use the term rapid AFib, and that's kind of a confusing term because the atrial rate is rapid all the time. It's 350 beats per minute or better during atrial fibrillation. So all atrial fibrillation is rapid, even the kind that has a slow ventricular rate. You get my point? Does the word rapid refer to the atrial rate or the ventricular rate? When you say rapid AFib, it's a little vague. So atrial fibrillation with a rapid ventricular response would seem to be the more accurate diagnosis, the better way to say it. Okay, we'll go on to the next one. Now, the first thing that should stick out at you is that the ventricular rate is extremely slow. In fact, if you look at this beat right here, find a heavy line and count off the milliseconds. 1, 2, 3, 4, well, that's 1 second. 1, 2, 3, 4, that's 2 seconds. 1, 2, 3, 4. This would be 3 seconds. So at 3 seconds in between beats, an R-to-R interval of 3 seconds would be 20 beats per minute. So this is more like 22 beats per minute or so. So with a ventricular rate of 22 beats per minute, what could this be? Well, you'd want to look for P waves because this could be a severe sinus bradycardia. And you look at this and you say, wow, does that look like a P wave? Maybe it is. But then again, it's not really present in any other leads. And so I suspect that's just artifact. I'm pretty sure the patient just simply moved. What you should be able to notice is that the baseline has this very, very fine undulating pattern to it. It has this little sense of atrial fibrillation, continuous, irregular, almost noise-looking signal. And so the atrial rhythm is a fib. But now, would we call this an atrial fibrillation with a slow ventricular response? Or, well, with a rate of 22, why don't we call it atrial fibrillation with an extremely slow ventricular response? Well, that doesn't really cut it either. If we take our calipers and move it to the first R-to-R interval and set it there, and then check the next R-to-R interval, we'll see it's about the same. And the third R-to-R interval is as well. And so the ventricular rhythm here is regular. Now, we talked about the hallmark of atrial fibrillation being an irregularly irregular ventricular rhythm. So how do you explain the fact that these QRSs are very regular? Well, this has to be some kind of escape rhythm. In other words, during atrial fibrillation, the AV node determines how fast the ventricular rate goes. But because you've got these very rapid signals hitting the AV node is going to let sort of a random signal get down to the ventricles, and that gives rise to this irregular ventricular response. But if you have complete AV block, then what happens is none of the atrial fibrillation signals gets through. And instead what you get is some kind of escape rhythm coming from either the AV junction or the bundle branch or Purkinje system. So the fact that you've got this heart rate of 22 beats per minute and the QRS is rather wide, it's looking at about 180 milliseconds wide, you'd have to call this an idioventricular escape. Idioventricular probably coming from the Purkinje system. But the rate is consistent with an idioventricular rhythm, and the fact that it's regular tells you that it's an escape focus and not just simply slowly conducting atrial fibrillation. So you'd call this strip atrial fibrillation with complete heart block and an idioventricular escape rhythm. Now, of course, you can have AFib with a slow ventricular response, and you can see rates in the 40s and 50s, but the R-to-R interval should be irregular. If it's not irregular, if you have regularization of atrial fibrillation, that implies that you have complete heart block. And sometimes people will read it as atrial fibrillation with a competing junctional escape or fusion or regularization, implying that the AV node conduction is hanging by a thread and there are a lot of junctional escape beats that are sneaking through. You can see that if the majority of the R-to-R intervals are very long and fairly constant. Anyway, let's look at one more ECG. And this is actually a rhythm strip that I got from the telemetry unit. If you look at the forest, you can see the QRS complexes do appear to be irregular. This is a bit shorter, and then it's longer, and then shorter, and then longer, and then a couple of intermediates, so there's no pattern to it. Looking in between the QRS complexes, there does appear to be sort of an undulation in the baseline. There doesn't seem to be any discrete flutter waves. Rather, there's sort of this polymorphic electrical signal that's going on. Here you might say, oh, gee, that looks a little sawtoothy looking. But that's not consistent. You don't see it here, and you don't really see it anyplace else. So you'd call this atrial fibrillation with a moderate ventricular response. But now let's look at the second strip. Now the QRS complexes appear to be quite regular. And if you try to figure out a rate, you have 300, 150. It's a little under 150. It's probably about 135 or 140 beats per minute. So you have a regular rhythm at 140 beats per minute. Remember what I said, don't ever believe what someone else has written on a rhythm strip, because it says here, patient converts to regular sinus rhythm sinus tach at 136 beats per minute. Well, this is usually a patient who's just lying there watching the Discovery Channel, and having a sinus tachycardia at 140 beats per minute would be highly unlikely. You do see discrete atrial signals in front of the QRS complexes. I think that bump right there could easily be interpreted as a P wave. But given that the patient was just in atrial fibrillation a short time ago, it's much more likely that the patient's chaotic atrial fibrillation became organized into an atrial flutter. And what you have down here now is atrial flutter with 2-to-1 conduction, where one conducts and this one blocks, and one conducts and this one blocks. So you have this atrial rate at 280 beats per minute, and it's just every other signal is getting to the ventricle. So this kind of rapid regularization of atrial fibrillation is indirect evidence that what you're dealing with is atrial flutter. And people can have atrial fibrillation and atrial flutter that are sort of going back and forth between each other. You don't usually have them both at the same time, although a lot of people will kind of use the term fib flutter to imply that it's kind of somewhere in between, although one could argue that there is no such thing. It's either flutter or it's fibrillation, but not both. Well, that's a debate I can have with myself in the advanced course, but for now I think we've talked about atrial fibrillation enough, and I hope you have a better idea of how to diagnose it. In the last chapter in this section, we'll talk about atrial fibrillation with aberrant conduction, which can give rise to some really confusing-looking wide QRS complex tachycardias, and I'll explain to you what Ashman's phenomenon is, and how you can use that knowledge to distinguish between atrial fib with aberrancy versus some kind of ventricular tachycardia. So for the ECG Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the ECG Academy, and we're going to conclude our discussion of atrial fibrillation with this third lesson on atrial fibrillation with aberrant conduction. Well, you should know all about aberrant conduction from my section on interventricular conduction disturbances. So think of atrial fibrillation with aberrant conduction as having a wide QRS complex because of some abnormal interventricular conduction. Now, this is a cardiogram showing a wide complex tachycardia, or WCT. So that means the QRS is wide, and some people just call it a wide QRS complex tachycardia or a wide complex tachycardia. So when you look at the QRS complexes, they are indeed 120 milliseconds or so in duration. It's not terribly wide, but as you scan across, you can see it's rapid, but there is some irregularity to it. So most of the time, the heart rate is running somewhere around 170 or so beats per minute, but sometimes it slows down. Here, this interval is more about 125 beats per minute, and then it speeds up again to more like 180. So it's irregular, and there's no apparent pattern to the irregularity. You can see it gets faster and then a little bit slower, but the QRS always stays the same. It stays that same 120 milliseconds or so. So we would call this atrial fibrillation with a rapid ventricular response, indicating that the AV node is actually very healthy and is conducting these impulses very quickly. And then there happens to be a left bundle branch block, and that's what's making the QRS wide. This happens to be a patient who has a sick left bundle branch, and when they went into atrial fibrillation, all the QRS complexes appeared to be quite wide, and it resulted in this wide complex tachycardia. Well, when you see a wide complex tachycardia and you see this irregular nature to it, it's a pretty good bet that this is atrial fibrillation with some kind of aberrant conduction. It's very unusual to see ventricular tachycardia to be this irregular, although it's not impossible, and we'll talk about that in the final section on ventricular tachyarrhythmias. But let's just say that in this case the patient has two different problems. They have atrial fibrillation, and they also happen to have an underlying left bundle branch block, and the two together gives you this wide complex tachycardia. Well, let's talk a little bit about physiology. So here's the heart in the conduction system, and if you remember, oh no, he's coming up with action potentials again. Well, the Purkinje system action potentials actually are very wide. They're actually wider than the ventricular myocytes. And it takes a long time for the Purkinje fibers to recover from their refractory period. Remember, if you try to stimulate a cell during the plateau phase, and even during phase 3, which is the repolarization phase, you won't get much of a response until the cell comes close to the resting membrane potential. Then at this point somewhere, you'll be able to get a response from the cell by stimulating the cell, and you'll get another action potential out of it. But there's a certain period, known as a refractory period, that the cell is not excitable. It's busy with this action potential, and this sequence of ionic currents has to reset itself before the cell gets ready to fire again. Well, now keep in mind that when the patient is having atrial fibrillation, the AV node is being bombarded with rapid signals, and it doesn't know which ones to pass. And so every now and then it's going to let a signal down to the bundle branches, and depending upon whether those bundle branches have recovered from refractoriness, that'll determine whether in fact that signal results in a QRS complex. But remember in my discussion of IVCDs that what sometimes happens is the left bundle branch may have a slightly shorter refractory period than the right bundle branch. If this is the left bundle and this is the right bundle, then what can sometimes happen is the AV node may let a beat down right at this moment, and it reaches the left bundle, which is able to conduct the signal, but the right bundle is going to be refractory and will fail to conduct the signal. And this will result in a functional right bundle branch block. Well, this happens quite often during atrial fibrillation because the AV node is passing signals down in a rapid, somewhat random, chaotic fashion. The coupling interval, or the time in between beats, will vary from one beat to another. So let me show you what can happen. Here's an example of atrial fibrillation. When you glance across at the forest, you can see it's quite irregular. There are longer intervals at around 110 to 120 beats per minute. There are shorter intervals that are much faster, and there's no pattern to it. And looking in between beats, you can see the slight undulation in the baseline, which is consistent with atrial fibrillation. There's no discrete P waves, although sometimes you get big fibrillatory waves that look like Ps, but not really. But now look at V1 and pay attention to the first 3 beats in V1. Well, this one's not right on the borderline. But these 2 beats in V1 look like they conduct fairly normally. And there are pretty long intervals in between those beats here, about 120 beats per minute, and this one about 110 beats per minute. But then right here you have 2 beats that come down much faster. If you measure back from this line, you can see it's about 160 beats per minute. But this is a very short coupling interval. And what happens is these 2 beats conduct aberrantly. There's an interventricular conduction delay that occurs. And if you know anything about 12-lead ECGs, you have an RSR prime in V1 that's consistent with a right bundle branch block. But the rest of the beats don't have a right bundle branch block. What happened is the AV node let this beat down so close after this prior beat that the right bundle branch had not recovered from refractoriness and was not capable of conducting the impulse. And so the impulse went down the left bundle and then came around the back door to the right side of the heart, giving rise to a widening of the QRS complex. So this is a great example of 2 beats that conduct very rapidly, and they encounter a functional right bundle branch block, and we refer to this as atrial fibrillation with aberrant conduction. It's easy to recognize this when you just see 1 or 2 beats, and this first beat is very closely coupled. But it actually happens much more frequently than you think. And there was a fellow many years ago who described a particular phenomenon. Now, let me go back to this action potential. We talked about the action potential duration and how there's a certain refractory period. But it turns out that that refractory period can change from one beat to the next. And it depends on the previous R to R interval. In other words, when the heart rate is very fast, the refractory period tends to be shorter. In fact, the action potential for these beats winds up being shorter than the situation where the heart rate is very slow, where in fact your action potential winds up being a lot longer, as I've drawn here. If you remember when we first talked about measuring QT intervals, the QT interval changes depending upon the heart rate. And at faster heart rates, the QT interval generally shortens. This is a reflection of the fact that at faster heart rates, the action potential gets shorter and the refractory period gets shorter. So with shortening of the action potential and shortening of this refractory period, the QT gets shorter. But what happens is this action potential duration changes from one beat to the next. And you see that especially with atrial fibrillation. So that if you have a couple of long intervals and then a short interval, this long R to R interval right here results in this beat having a relatively long action potential. So if another beat comes down quickly, it may encounter refractoriness in one of the bundles. This was described by a guy named Ashman, and it's known as Ashman's phenomenon. Now let me show you an example of that. Here's the rhythm strip that I got from the telemetry unit, and it's pretty easy to recognize this as atrial fibrillation. You have this jiggly bass line here. You've got a ventricular rhythm that's irregularly irregular. It's kind of fast here, and then it breaks up and it becomes very irregular here. And then down in the second strip, you've got a run of a rapid rhythm because the AV node sent a whole bunch of signals down. And then there's a bit of a pause because the AV node sort of took a little break here. And following this pause, you have a run of a wide complex tachycardia. Now, of course, you should never trust what you read on a rhythm strip unless you wrote it yourself. So this says possible 6 beats of V-tach. Of course, the word possible is how they hedge their bet versus bundle branch conducted AFib. Well, it turns out that this is a typical example of Ashman's phenomenon. Ashman's is commonly referred to as long-short. And by long-short, we mean that this long R to R interval, followed by a short R to R interval, results in aberrant conduction of this beat here. So this beat conducts aberrantly because the long R to R interval resulted in a long action potential of this beat. So when you have a long action potential, the next beat that comes down, if the AV node lets one down rapidly, results in aberrant conduction because one of the bundle branches hasn't recovered yet. Now you'd ask, well, why is it that you get a run of wide complex beats? Because if you look at beat number 2 over here, well, it doesn't have that long short pattern, so why did it conduct with a bundle branch block? Well, that's where this basic course introduces you to some advanced topics. Let's go back to the conduction system here. Let's say that you have an Ashman beat that blocks in the right bundle branch. Okay? It's not able to get down the right bundle branch. So what happens is the signal is able to get down the left bundle system. It gets to the left ventricle, but as it crosses at the apex and across the septum, it's able to enter the right bundle branch system. And since the right bundle branch system is excitable at that point because the signal never got there, well, it's able to travel retrogradely a certain distance until it encounters refractory tissue from that beat. Well, now, when the next beat comes down, this green one is number 2, well, the right bundle branch is refractory because it had retrograde, in other words, backward conduction, known as concealed conduction, in a retrograde fashion up the right bundle. And so when this impulse comes down, it finds the right bundle branch is still refractory. And so it has to do the same thing, go down the left side, and then it manages to get across again, and then back up the right bundle. So when the next beat comes down, it still finds the right bundle refractory. And so you can see that the result is a salvo of wide complex beats because of this phenomenon, with the signal going across the septum and retrogradely penetrating the right bundle and keeping the right bundle refractory. So isn't that kind of cool? Well, at some point, the right bundle has enough time here to recover, And so this beat winds up going down both bundles, and you get a narrow complex which finishes out this run of this rapid burst of atrial fibrillation. But this wide complex tachycardia right here is a beautiful example of Ashman's phenomenon, and you can be comfortable calling this atrial fibrillation with aberrancy rather than having to call it ventricular tachycardia. Well, we'll talk about ventricular tachycardia in the next section, and that'll finish this course in basic arrhythmia analysis in the Ecg Academy. But in the meantime, I hope you enjoyed this kind of high-tech discussion on atrial fib with aberrant conduction. Now, aren't you glad you subscribed to the Ecg Academy? Well, this is Dr. Nick. Thanks for subscribing. Hi, this is Dr. Nick, and this is the last section in the basic course on ECG interpretation. I'm going to talk about ventricular tachyarrhythmias. And this is a complicated subject, but we're going to try to make it clear for all of you out there. So this first lesson is really about the terminology and about classifying ventricular arrhythmias and trying to make some sense out of it, because although the books may show you typical examples of ventricular tachycardia and ventricular fibrillation, there's still some misunderstanding out there, and a lot of people have some incorrect ideas about what it should look like and what these arrhythmias represent. So let's get started. First, when you talk about ventricular tachyarrhythmias, you're talking about arrhythmias arising from the ventricle, as opposed to supraventricular arrhythmias, which arise from every tissue above the ventricle, including the AV node and the AV nodal tissues in the atria itself. All right, so we're talking about rapid beats that arise from the bottom chamber. There are two ways to classify these. First is the mechanism of the tachycardia. Is it due to an electrical short circuit that's going round and round? Or is it due to a single automatic focus that's firing? And I'll talk more about this in the intermediate course when we cover mechanisms of arrhythmias. But for this level, just understand that there are two different mechanisms that give rise to rapid beats. One is sort of an electrical short circuit, and the other is just a discrete focus in the heart that starts firing rapidly. Now, the other means of classifying these ventricular arrhythmias is based on rate. The rate kind of gives you major classifications. And so if the rate is less than 100 beats per minute, we generally refer to it as accelerated idioventricular rhythm. Remember that an idioventricular rhythm is something that we can recognize during very slow heartbeats, such as during complete AV block, when the idioventricular rhythm serves as an escape rhythm. You've heard of idioventricular escape rhythms. Generally, they occur at rates of around 25 to 35 beats per minute or so. So if the Purkinje fibers out here are able to fire at, say, 35 beats per minute, so anything higher than that would be considered an accelerated idioventricular rhythm. So up to about 100 beats per minute, and some people say 120 beats per minute, and sometimes it depends on the way it behaves. Ventricular tachyarrhythmias in the range of 40 to 100 beats per minute are considered accelerated idioventricular rhythms. And the second chapter in this section is just about that. Now, ventricular tachycardia meaning fast heartbeat, of course, is considered any rates above 100, and some people say 120 beats per minute. But there is a category that some people have used, and that is ventricular flutter. Ventricular flutter is defined as rates between 250 and 350 beats per minute. Not everybody uses that terminology, but figure ventricular tachycardia is anything from 120 up to 250, and then above 250, you might refer to it as ventricular flutter. Ventricular fibrillation generally occurs at rates of greater than 350 beats per minute. And there are differences between these as well, having to do with how the QRS complex looks during these arrhythmias. In terms of the appearance and duration, most of the time we're dealing with ventricular tachycardia. So let's characterize ventricular tachycardia. You can have sustained ventricular tachycardia or non-sustained. Now, sustained usually implies that it just keeps on going and going and going and doesn't stop unless someone sort of interferes with it, let's say with an electrical shock across the chest called a cardioversion. But in fact, the definition of sustained is 30 seconds or more of ventricular tachycardia, or if the patient is cardioverted out of ventricular tachycardia in less than 30 seconds because they have no blood pressure, let's just say. So if someone gets shocked out of VTAC, that's what we refer to it as VTAC. If someone gets shocked out of VTAC, then kind of you might as well just call it sustained, because who knows how long it would have lasted. But the true definition of sustained is greater than or equal to 30 seconds. Non-sustained, of course, means it stops by itself, and it may last anywhere from 3 beats all the way up to 30 seconds. Now, why do I say 3 beats? Well, let's go back to the ventricular ectopy. If you remember that if you have 2 beats in a row of ventricular ectopy, if you have 2 PVCs in a row, we call that a couplet. And if you have 3 beats in a row, some people actually call that a triplet. But to be accurate, 3 beats in a row or more is really considered non-sustained ventricular tachycardia. Finally, we characterize ventricular tachycardia as either monomorphic or polymorphic. Now, what does that mean? If you look in one lead and all the QRSs look the same, that they have a very consistent appearance to them, we call it monomorphic. On the other hand, polymorphic refers to the morphology or the appearance of the QRS complexes, and poly means many. So this arrhythmia may start as a monomorphic, but then it changes, and you'll have different QRS complex morphologies. Some of them may be going down, some of them may be going up, some of them may be very small. The idea is that it's changing, and we'll get to specific examples of this in the last chapter of this section. Now, the other thing I want to touch on in this chapter is that if you have a rapid heartbeat going on in the ventricle, and you have ventricular tachycardia, let's just say, what happens to the atria? That depends, for the most part, on how the AV node behaves. As I mentioned in some older lessons, the AV node in some patients is capable of conducting in a retrograde or backwards direction. But that depends on a lot of things. It depends on how the AV node is actually wired. And so each patient is an individual, and some people can't conduct no matter what. It also depends on the autonomic nervous system and how much adrenaline is in the patient's system, because retrograde or backward AV node conduction is enhanced by adrenaline. And under certain circumstances, you can get conduction in a backward direction on that basis, whereas if the patient is relaxed, they won't conduct backwards. Finally, the rate has a lot to do with it. At slower rates, if a patient were to have a slow ventricular tachycardia, you may in fact get 1-to-1 conduction up the AV node, and you'll actually see retrograde P waves following each QRS complex, kind of what we saw in the ventricular ectopy section of this course. But just like the AV node conducts worse at faster rates in an antegrade direction down the AV node to the ventricles, and you get things like Wenke back and second degree AV block in an antegrade direction, the same thing happens to the AV node in a retrograde direction. And so if the ventricles are going faster than the AV node is capable of conducting, you can see retrograde AV block. Sometimes it's a typical Wenke back kind of phenomenon with the R2P intervals getting longer. And sometimes there'll be 2-to-1 block. And sometimes, in fact, you'll have complete block of conduction up to the atrium. And in that case, what happens is the sinus node simply fires as if nothing else is going on. And you have sinus P waves that you can actually map out with calipers marching through this ventricular tachyarrhythmia. Now, whenever the ventricle is going faster than the atria, and we can see P waves going through this arrhythmia that are slower than the ventricle, when the atrial rate is less than the ventricle, we refer to this condition as AV dissociation. Now, AV dissociation is a little bit different from AV block. True, when you have complete AV block, the atria and the ventricles are disconnected from each other, and they're at different rates. But in that case, the atrial rate is faster than the ventricular rate, and we call that complete heart block or complete AV block. But if the ventricular rate is greater than the atrial rate, you can still have a situation where the A and the V are doing different things, beating at different rates. But if the ventricular rhythm is faster, basically the ventricles are setting the pace of the heart, and then we call it AV dissociation. It's a subtle difference, but you need to be able to appreciate the distinction, because AV dissociation is really the hallmark of ventricular tachycardia. And I've seen people mislabel strips because they don't understand the difference between these two terms. Okay, well, I think that's enough theory and physiology. So if you go on to the next video in this section, we'll start talking about the first of these ventricular tachyarrhythmias, and that is AIVR. So for the ECG Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the ECG Academy, and this brief lesson will be on accelerated idioventricular rhythm. The reason I say brief is because that's kind of the nature of this rhythm. It usually doesn't last more than a few seconds or a minute or so, and so it's kind of hard to catch it on a 12 lead. So I don't have a lot of examples of it. And in fact, it tends to be rather benign. People generally don't even have symptoms from it, but it is important that you be able to recognize it. Now, for one reason or another, accelerated idioventricular rhythms occur because of abnormal signals that arise from the his Purkinje system, and sometimes the ventricular myocardium, but that's less common. They occur at rates of greater than 40 beats per minute, but less than 100 beats per minute. That's the rate that you'd expect to find it at. Now, how do you recognize it? It's not just the slow rate, it's also the appearance of the QRS complex. Because these signals are not taking the normal his Purkinje system, you will not see a narrow QRS complex, but rather, like a PVC or ventricular ectopic beat, the signal travels slowly through cell-to-cell connections rather than over the rapid his Purkinje system. And so the electrical signal takes a long time to get around the heart. And instead, what you see are these very wide, bizarre-looking beats that look like a PVC. But there'll be a whole bunch of them in a row. And in fact, they can be regular, but it can be sometimes a little irregular depending upon what's causing this disturbance of impulse generation. So these impulses are being generated abnormally by this abnormal focus in the heart. Now, this can be firing because of any number of reasons. Sometimes it can happen because of an insufficient oxygen supply, so it can be due to ischemia. Sometimes it can be due to electrolyte disturbances or drug overdoses like digoxin. But what you see is this continuous ventricular rhythm between 40 and 100 beats per minute. And you should generally see some evidence of AV dissociation. So the P's are doing their own thing, and they're often beating at a similar rate or maybe a little slower or a little bit faster, and it's common to see the two rates competing with each other. So here's an example. As you glance at the forest, you can see that the R-to-R intervals are fairly regular. And if you find a QRS complex that lands on a heavy line, this one comes close. You can read the rate as 300, 150, 100. It's a little over 75, maybe 78 beats per minute. But the QRS is clearly wide, and when you look in front of each QRS complex, you do not see a P wave anywhere. So you'd say, well, why isn't this just like some kind of junctional rhythm with a bundle branch block? Well, that is a consideration, but if you look very carefully at the T wave, you'll see that there is a P superimposed on the T wave, and here it is again. So there are P waves, but the time from the beginning of the QRS to the time of the P wave is a little long for these to be retrograde Ps. And when you look at where the P wave lands with respect to the QRS complex, you'll see that it changes. In fact, if you look down in V3, you can see the P wave is now just at the very end of the QRS complex. Compare that with this P wave, which is on the T. So what's really happening now is the sinus rate is a little bit faster than it was back in the beginning of the strip. And the sinus rhythm is now overtaking the ventricular rhythm. And in fact, you can see that this P wave and this beat is now gone. It's disappeared because the P's are catching up with the QRS's. It's like a time warp. Now the P here is sort of in the middle of the QRS, and now look at that. It's peeking out from in front of the QRS complex. So in this part of the strip, the atrial rate is accelerating, and it's starting to take over the rhythm, but it hasn't gotten there yet. If we were to continue to see this strip, we'll actually see P waves that come further and further in front of the QRS complex, and you may get a fusion beat, and then eventually the sinus rhythm will take over again, and the P wave will manage to get down the Purkinje system and give you a narrow QRS complex again. So basically you have two separate rhythms that are going on, and they're competing with each other. One is arising from the ventricle, And we say that because the QRS complex is wide, and the P wave that we see in the T wave is dissociated from it, so it's not a retrograde P wave. And then you can see that the atrial rate slowly accelerates, and eventually it's going to take over again. So as I said, it's kind of hard to find AIVR unless you're really looking for it, and it often doesn't last long enough to catch it on a 12 lead. More often than not, you'll see it on a rhythm strip. Okay, now I want you to appreciate that there are actually like 3 ways that AIVR can get started. You can have a sinus rhythm, and then what may happen is you may get a pause because of, let's say, AV block. Here the PR got longer, and then you have a block. Now what happens is there's such a long period of time that a Purkinje fiber decides to escape. It decides to fire as an escape beat. And now what happens if you march these P's out, the next P would occur right here, and it didn't get a chance to do anything. And so now you have this accelerated rhythm that's going on. And when does the next P wave occur? Well, it may occur here, and you might get a little blip of a P, but the accelerated rhythm is only a little bit slower than the sinus rate. And so eventually the sinus rate takes over, and then you may get a fusion beat, and then finally the sinus rhythm declares itself to be the faster of the 2 rhythms, and then you'll get a normally conducted beat again. In this case, the AIVR started as an escape rhythm because of a pause. The second way it can get started, if a Purkinje fiber starts firing in the ventricle, and it starts to fire just a little bit faster than the underlying rhythm, what you may get is a fusion beat, here where the QRS is a little bit wider, the QRS starts a little bit earlier than it should because you don't get this PR segment. And then it takes over, and then you may wind up with some sinus beats that peak out from the other side of the QRS complex right here. And then what happens is usually the AIVR resolves and the sinus rhythm kind of takes over again. The last way that it can get started is with a PVC. So here's an example of AIVR that got started with a PVC. In this case, you have a sinus rhythm with a little bit of a first degree AV block. You have another sinus beat here, and these 2 strips are running simultaneously, so you can see the P waves very nicely here and here. And then what happens is the patient has a PVC, which you see in 2 different leads. The PVC, it's clearly a PVC because there's no P wave in front of it. It's wide and bizarre, looks clearly different from the underlying QRS complex. And in fact, you see a retrograde P wave that occurred after the PVC. But what happens is, after the PVC, what we generally see is a compensatory pause. And this is actually more likely to occur in someone who has sick sinus syndrome. Why? Because if you measure the P-to-P intervals, if you take a pair of calipers out and you bring it down to the P-to-P interval, take the onset of the P waves here, you see that these P waves are occurring at a rate here of, let's see, 300, 150, 175, about 70 beats a minute. But what happens is the P wave should occur here, but the PVC got in the way. And then you wound up with another P wave that kind of reset the sinus node. So now you have this very, very early coupled atrial event that was due to the PVC. It's a retrograde P, but it gets into the sinus node and it resets it. And in fact, because of overdrive suppression, the sinus node gets suppressed. It's almost like you get a post-tachycardia pause, even though the tachycardia only lasted for 1 beat. And so if you measure out, you see there's no P wave here. Why isn't there a P? Because I said the sinus node gets suppressed by this retrograde P, and you wind up with a pause. Well, that pause allows the AIVR to get started. So now the same spot where this PVC arose winds up firing again, here at a rate in the low 40s. So now you have set up this AIVR that's marching through at a rate of about 42 or 44 beats per minute. What are the P waves doing? Well, you can actually see one start to peak out right here. So right here, you see the sinus node is trying to come back from being suppressed by this retrograde P wave. So the sinus node is beginning to accelerate, and in fact, here you finally get a sinus P that's still a little bit slow compared with this P wave because it's just coming back from being suppressed. But it does conduct down to the ventricles with the same PR interval that you saw in the beginning of the strip. So this PVC set off this chain reaction that resulted in a brief run of AIVR because of suppression of the sinus node and slowing of the sinus rate, but then the sinus node finally came back and took over again. So as I mentioned before, it's often the two rhythms are competing with each other, and you can actually see AIVR sort of come and go, especially if the two rates are very similar. So it's a kind of a quirky arrhythmia, but you need to be able to recognize it and call it as such. Now, sometimes when AIVR gets a little faster, especially when it starts like this, with this sort of sudden onset, rapid rhythm, and let's say if it's a rate of about 90 beats per minute, a lot of people will call this slow VTach. And the distinction is difficult to make sometimes. People say that slow VTach is more regular and that it has an onset with a shorter R-to-R interval than the usual AIVR that usually occurs as an escape rhythm. In fact, it's probably the same mechanism, just a different rate and a different mechanism of onset. Clinically, you would treat it similarly. Most patients won't even feel symptoms, but if they do, you generally manage it conservatively. You don't run in there with a syringe full of lidocaine or anything. And it's usually self-limiting, and long-term therapy for this is almost never needed. Well, in the next video, we're going to be talking about ventricular tachycardia, the monomorphic variety in particular. And you'll see some of the same ideas of AV dissociation and wide QRS complexes because of abnormal interventricular conduction. But that's something you see much more commonly, and we're going to spend quite a bit more time on that. So for the Ecg Academy, this is Dr. Nick. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and this lesson is on ventricular tachycardia. Now, we're going to be talking for the most part about monomorphic VT because that's what we generally see on cardiograms. It's fairly easy to recognize, but we're going to cover in detail what kinds of things you should be looking for. For the most part, ventricular tachycardia occurs when the electrical signal is going round and round in a circle at a rapid rate in the bottom chambers. Now, what rates? We're generally talking 100 to 120 beats per minute, depending upon which definition you use, and it can go all the way up to about 350, although from 250 to 350, monomorphic ventricular tachycardia is often referred to as ventricular flutter. On rare occasions, there can be a focus in the left ventricle or the right ventricle that's firing at a rapid rate and taking over the heart rhythm, but those are much less common, and we will cover automatic ventricular tachycardias in the advanced course. But for the time being, let's talk about the usual variety of ventricular tachycardia, and that's re-entry ventricular tachycardia due to a short circuit. Where does it come from? Most of the time, as this animation shows, ventricular tachycardia comes from a scar someplace in the left ventricle, an old heart attack perhaps, or sometimes the ventricle may be diseased diffusely because of a condition known as cardiomyopathy. And what can happen is short circuits in the left ventricular wall can result in delayed conduction, slowing of conduction, and this allows the development of short circuits in the heart muscle. Now what happens is a premature beat in the ventricle occurs, or maybe a couple of PVCs in a row, and the electrical signal gets stuck going round and round in a circle you can see here in the left ventricle. Because of a short circuit at the edge of this scar, the electrical signal has an opportunity to get stuck in a re-entry circuit, and that causes a very rapid heartbeat. Now notice what's happening in the atria. In this case, I've drawn it so that there's no retrograde AV conduction, and the sinus node is just kind of like firing at a regular rhythm, and that's how you can actually get a chance to see AV dissociation, which is what we call it when the ventricular rate is faster than the atrial rate, and the atria and the ventricles are beating independently of each other. So what's this going to look like? Well, remember, if you're looking for ventricular premature beats, you expect to see the ventricular beat start without a P wave in front of it, or you may see a P wave, but the PR interval will be too short to have conducted. And the ventricular tachycardia will get started, and it will look distinctly different from the underlying complexes because it's following an abnormal course through the ventricular myocardium, not using the Purkinje system for the most part. Pretty easy to recognize. It's the kind of thing that creates a sense of panic when the nurse looks at the monitor and yells, VTach! Well, here's the first strip I want to show you. The first thing is, for those of you who work on telemetry units, please don't stamp labels on top of the QRS complexes because it makes it a lot more difficult for us to look at it afterwards. You can see there are regular narrow QRS complexes on the left side, and then you have a 4-beat run of this wide complex tachycardia. Well, in front of these narrow complex beats, you can see there's a normal P wave, and the PR interval looks to be about 200 milliseconds. Everything is fine, and then this starts. Now, the first thing you need to do is look to see how did this start? What's in front of this wide complex rhythm? And you have to look at this as, well, is this first beat a ventricular beat, or is it some kind of APC with aberrant conduction? That will often give you the best clue as to what this is. Well, if we take a pair of calipers and bring it down to the P waves, we can see the P waves are going at a rate of just above 50 beats per minute, maybe 54. And the P waves march through pretty nicely. Well, what happens when we put our caliper on the last of the sinus beats is we see indeed that there is a P wave here in front of this QRS complex that looks exactly the same as this P. But what happened to the PR interval? It got shorter. Here, this PR is maybe about 240 milliseconds. This PR interval is only 160 milliseconds. The PR segment is missing. You can see a PR segment here very clearly. This PR segment is missing. So this P wave did not have enough time to reach the ventricles, and therefore this beat must have originated from the ventricles themselves. Now, of course, there are exceptions to that rule, which we'll cover later on, and the main exception would be some kind of pre-excitation. But without confusing the issue, 99% of the time, when you see a wide QRS complex with a short PR interval, then this first beat is a ventricular beat, and it's followed by 3 additional beats that have a similar morphology. Now notice it is rather irregular. There's a little bit of a warm-up associated with this 4-beat run of non-sustained ventricular tachycardia. It starts out with a rate of about 120, and it speeds up to maybe 165 beats per minute. But we see that commonly in non-sustained ventricular tachycardia. Now what happens if we move our caliper from this P wave into the middle of the tachycardia? We actually see a very interesting bump here on the T wave of this beat. And I think if you use your imagination, you can clearly see that this T wave looks a lot different than this smooth T wave, and that high-frequency little jiggle is likely the P wave that was inscribed in the middle of this run of ventricular tachycardia. Now, this is a little subtle, and I'll show you better examples of AV dissociation. But these P waves are kind of small in amplitude and sometimes difficult to see, plus this is a very short run, so it may not be the best example. But depending upon the patient's AV node and whether it's capable of conducting retrogradely, you may or may not see dissociated P waves or retrograde conduction, one or the other. Well, let's take the next example. Now, this is an impressive strip and would usually result in someone hitting the code button. But you can see there are 2 narrow QRS beats in the beginning, preceded by P waves with a normal PR. And then you have what looks like 4 beats right here. And each beat looks distinctly different from each other, as well as from the underlying complex. So what we have are 4 ventricular beats in a row. So this is polymorphic ventricular tachycardia. Polymorphic meaning the beats look different from each other. They have different morphologies. And that 4-beat run of polymorphic VT then gets stuck in a reentry circuit that immediately organizes into a monomorphic ventricular tachycardia, here at a rate of about 230 beats per minute. One's always tempted to say, well, is this truly ventricular tachycardia, or could it be some kind of AFib with aberrancy? That's always the controversy that arises. And the rule is, if you have a rapid wide complex tachycardia, always assume it's ventricular until proven otherwise. Statistically, about 90% of all wide complex tachycardias are ventricular in origin, that they're not supraventricular with aberrant conduction. So assume it's VTAC until proven otherwise. Well, how are you going to prove it? Well, the hallmark of VTAC is going to be AV dissociation, and that's what you really have to look for when you're analyzing a strip. That means you need to see P waves and QRSs that are not associated one-to-one. Now, how are you going to see P waves when you have these rapid, sharp QRS complexes? Well, the best place to look for them is in the smooth part of the T wave. And I think what you should be able to notice is that these T waves are very smooth, and then this T wave has a little bite taken out of it, and then this T wave is smooth, and then this one has a bite, and this T wave is smooth, and this one has a bite. And so there's this alternating pattern of smooth and sharp and smooth and sharp. And what this represents is 2-to-1 retrograde conduction up the AV node. So the ventricular rate here is 230, but the AV node is capable of conducting the impulses backwards at a rate of about 115. So what you have is a ventricular rate that's twice as fast as the atrial rate, and there is an association between the two, but it's 2-to-1. By definition, this is AV dissociation because the ventricular rate is faster than the atrial rate, and this allows you to make the diagnosis of ventricular tachycardia. You notice in the beginning you don't see it quite so clearly because there actually may be some winky back going on, but it's a lot harder to prove that on this rapid strip right here. The other thing that helps you decide that this is ventricular or not is that the QRS is fairly wide. It's about 140 milliseconds here, whereas the underlying QRS complex is less than 120. And obviously the QRS morphology is completely different than the underlying. But there are a number of rules that we'll get into in the advanced course when we talk about SVT with aberrancy versus ventricular tachycardia and how to recognize VT based on the 12-lead morphology. But for rhythm strip analysis, this is the kind of stuff you should be able to identify. These retrograde Ps and the presence of AV dissociation allow you to definitively make this diagnosis of VTAC. I think in general, people look for excuses to not diagnose VTAC. They're always making up some reason that, well, this might be AFib with aberrancy or something like that, because they're afraid of the consequences of giving a patient this diagnosis. It really does open up Pandora's box. But if you want to be an ECG expert, you have to be able to call it as you see it. And this is absolutely clear in my mind. But let's look at the next example. And this is actually a 12-lead of sustained monomorphic ventricular tachycardia. No one should ever try to call this SVT with aberrancy. There are a number of 12-lead morphologies that we can use to try to make this diagnosis. And just to give you an example, you have negative QRS complexes in lead 1, which tells you that the axis is going away from the left side. It's in here someplace. And having such a marked right axis deviation is one clue that you're dealing with ventricular tachycardia. The fact that this almost looks like a sine wave, you have this sinusoidal appearance to the QRS complex, is almost always a sign of ventricular tachycardia. If this rate was above 250 beats per minute, this would be a great example of ventricular flutter. Just think of atrial flutter as being rates of 250 to 350, so ventricular flutter has a similar rate. This sort of like sine wave monomorphic rapid tachycardia gets the name ventricular flutter in some circles. All right, the last strip I want to show you in this section is, again, this non-sustained monomorphic wide complex tachycardia that was originally read as atrial fibrillation because it does appear to be slightly irregular. There are longer RR intervals, about 150 beats per minute. Then it gets a little bit faster, up to maybe 160, 165. Then it tends to slow down a little bit over here. And it just is a little bit of a variability in the QRS complexes. But it clearly is wide and bizarre, and it's monomorphic because each one of these QRS complexes looks the same in one particular lead. And the key to making the diagnosis is seeing what are the P waves doing. So if we take our trusty calipers and put it on the P waves and measure the P to P interval, we can see that this QRS complex clearly started sooner than the P was expected to land, and there's no P in front of it. So that would make us think that this is a ventricular beat indeed. If we assume that there's a P wave in the middle of this QRS complex and move the caliper over, we don't see a P landing here, but let's carefully analyze what's going on between these QRSs, because that's where we'll see the AV dissociation. So you have this wide complex that we assume is ventricular, and this one looks exactly the same, except this T wave right here is very smooth, and this one has this very sharp deflection on it. That sharp deflection looks a lot like the atrial activity that we saw in the beginning of the strip. Well, let's keep analyzing. Here's a QRS. Now the T is back to being smooth. Here's a QRS, but now you have this sharp deflection on the ST segment again. And so now you can detect a pattern where you have a smooth T, and then a T with a P superimposed, and then a smooth T, and here again an ST segment with a P wave superimposed. And so we have the same pattern that we did with the other strip, except that it's much more apparent here. And that is AV dissociation with a ventricular rate that's a lot faster than the atrial rate. And we have 2-to-1 retrograde conduction up the AV node. And that gives rise to these P waves that follow every other QRS complex. So this is a really great example of AV dissociation, and that's what you should be looking for when you look at a wide QRS tachycardia. Well, we've gone over non-sustained and sustained monomorphic ventricular tachycardia. In the next video, I'll talk about polymorphic ventricular tachycardia, a very special kind of polymorphic ventricular tachycardia called torsade de pointe, and finally ventricular fibrillation. Well, this is Dr. Nick for the Ecg Academy. Thanks for watching. Hi, this is Dr. Nick with the Ecg Academy, and this is the last chapter in the basic course, and it completes the section on ventricular tachyarrhythmias. We're going to talk about polymorphic ventricular tachycardia, and we're going to talk about ventricular fibrillation. Now, polymorphic ventricular tachycardia, as its name implies, that the QRS changes. It changes from beat to beat, although there may be periods where the ventricular arrhythmia looks the same. And so it may have a few beats that look the same, and then it changes, and then you may have alternating stuff. So the idea is that it's not the same. So anything that's not monomorphic is considered polymorphic. It's very easy to recognize this, and just like most ventricular tachycardias, you expect to see heart rates between 120 and maybe 250 beats per minute. That can also get up to as high as 300 beats per minute, perhaps. When you get to a polymorphic ventricular tachycardia greater than 300 beats per minute, really that meets the definition for ventricular fibrillation. And the idea is that when you have less than 200 milliseconds in between beats and you have a polymorphic ventricular arrhythmia going on, that's almost always multiple short circuits in the ventricle all going at once. One of the things that you see with ventricular fibrillation is that in some leads you start to lose the QRS complex altogether, and it becomes almost just like a jiggly line with very little discrete QRS activity going on. But we'll see examples of this later in this chapter. Let me first show you polymorphic ventricular tachycardia. This is kind of a bizarre strip, and it's pretty brief, but it proves the point that you have a sinus beat in the beginning with a P wave and a QRS complex that looks fairly narrow. And then you have these wide, bizarre beats. There may be retrograde P waves in between them, but it's almost like no two beats look alike. You've got three going down, and this one's up, and this is almost biphasic, and then you have another run of crazy stuff. It's very, very irregular, at times even as slow as 100 beats per minute. And the interesting thing is that when you look at one of these beats and you examine the QT interval, it's only about 360 milliseconds. Now, this is very important. When you see a polymorphic ventricular tachycardia with a fairly normal QT interval, really that's what you need to call it, polymorphic ventricular tachycardia. And in fact, clinically speaking, this really is ischemia until proven otherwise. So you really have to start thinking about ischemia in these patients because polymorphic ventricular tachycardia really is like a sign of myocardial instability. But this is not torsade de pointe. Torsade is a completely different animal. Let's go back to our model here, and we'll talk about this very specific arrhythmia that comes from the French words meaning to revolve around a point or to turn around a point. And the initial idea behind this arrhythmia was that somewhere in the ventricle there was a reentry circuit that was going around, but that circuit was actually spinning in space very gradually, sort of like turning around on its axis and then kind of going upside down and around. And what you see is a polymorphic ventricular tachycardia that in the books kind of looks like it's get bigger and smaller and then bigger and then smaller again. And it's a very characteristic appearance in the textbooks where it says bigger and then smaller and then bigger than smaller. And everybody can recognize this. Oh, yes, of course, that's torsade de pointe. But it's not always torsade de pointe. Not every ventricular tachycardia that gets bigger and smaller is torsade. There are very specific requirements that you should look for before you diagnose torsade de pointe. And these are the ones I look for. First, you're looking for rates of 200 to 300 beats per minute. And so if you see rates in the range of 350 with less than 200 milliseconds in between beats, really you're looking at ventricular fibrillation. The second thing is you absolutely should see a long QT interval. Now, there are rare exceptions to that rule, but in almost all cases of torsade de pointe, The QT interval is long either because of drug-induced long QT syndrome, otherwise known as Dillquits, or congenital long QT syndrome, LQTS, and there's a whole bunch of those that we'll talk about in the advanced course, or some kind of electrolyte abnormality that results in a long QT interval. But this is very, very important. The long QT interval is a must, and I'll show you why. If you recall, at slow rates or long intervals, the QT interval generally is longer than it is when the heart rate is faster. And that's normal. When we talked about intervals, we talked about how you correct for the heart rate to get the corrected QT interval. And the way I've drawn it is that slow rates will result in longer QT intervals, and faster rates will result in shorter QT intervals. But as I mentioned, this changes from one beat to the next. And that's why you'll sometimes get functional bundle branch blocks because of prolongation in the QT interval. Well, what happens with Torsades is there's such a bizarre abnormality in repolarization that it results in ventricular arrhythmias, but it's especially worse after a pause. And so what you'll generally see is pause dependence, and I'll show you what that looks like. It means that there's usually a long interval before the normal beat that precedes the ventricular tachycardia. So it's pause dependent, and I'll show you examples of that. Lastly, the first beat of the tachycardia arises from the T wave. Because the QT interval is long, then that means the first beat of the tachycardia is late coupled, meaning that the rate is relatively slow when it first starts off. Let me just show you an example of Torsades. Now here it is, it's a polymorphic ventricular tachycardia, wide and bizarre, really big negative QRS complexes in the beginning, and then they get much smaller, and then actually becomes positive towards the end here. And then down here there's another run, but this doesn't look exactly polymorphic though, does it? It does a little bit here, but I want you guys to get away from the idea that it's always going to look like this, because it doesn't. What's more important is when you look at this normal beat with a P and a QRS, look at the T wave. Where the heck is it? It's over here. Look at how long that QT interval is. If you measure from here, it's 2, 4, 6, almost 700 milliseconds. It could even be 800 milliseconds. It's enormous. And that first beat of this polymorphic ventricular tachycardia arises from the tail end of the T wave. Look how slow it's coupled. It's coupled at a rate of about 68 or 70 beats per minute. And then you get sort of this takeoff. There's a little bit of a warm-up in the tachycardia before it kind of finally peters out, and then you have a normal beat again. Torsades de pointe can be non-sustained, or it can become sustained and can even degenerate into ventricular fibrillation. Now, when I said pause-dependent, I was referring to the pause that precedes the normal beat that kicks off the arrhythmia. So look at this interval right here. From the last beat, there's a long pause. This long pause right here causes this QT interval to become even longer than it was before. And then with this bizarre T wave, you get the first beat of tachycardia, you get a run of Torsades here, and then it finally stops. And then with a normal beat takes over, you have another run, and then there's a little bit of a pause here, and that causes this QT interval to become very long, and you have another run. So you actually get this kind of bigeminal pattern where you get a run and then a pause, and then a beat and then a run and then a pause. So you get normal beats kind of sandwiched in between runs of polymorphic VT. This is very characteristic of Torsades, but as you can see, it doesn't have that bigger, smaller appearance to it like you have seen in textbooks before. Let me show you another example that's even less characteristic. Here's an example of classic Torsades in someone who got the wrong medication and it wound up causing their QT interval to be very long. Now, if you look at the QT of this first beat, it's about 500 milliseconds. It's very long. And there's a PVC that arises from the tail end of the T wave. Well, that PVC results in a compensatory pause. And with this compensatory pause, you have a normal sinus beat, and the next T wave actually has like a U wave on top of it. So the TU complex becomes very long, and you have another PVC. As I said, that's like often a bigeminal pattern. Then with this compensatory pause, you actually have a junctional beat here. the P wave and the QRS complexes are occurring simultaneously. And with that beat, your T wave, look how big it is compared with this one. This is kind of a small T, then it got a little bit bigger. Now you've got this huge looking, very bizarre T wave, and the first beat of tachycardia rises from the T wave relatively slow, here at a coupling interval of maybe 100 beats per minute, but you get this polymorphic V-tach. But it doesn't look like it gets bigger and smaller, but clearly the QRSs are going down in the beginning, and then it sort of becomes sort of biphasic here, slowing down slightly, and then these QRSs are clearly going up. And so the axis of the QRS complex is changing, and that's what makes it polymorphic. And it's the long QT and the pause dependence that makes this torsade. It's the same thing down here. Actually, this is the same strip, just a little bit later, because now you can see another pause after the VT breaks, and then you see another short run of clearly polymorphic V-tach in this sort of bigeminal pattern. Make sure you look for all the ingredients of torsade before you call it that, because if it's not torsade, then it's just plain old polymorphic ventricular tachycardia. The last arrhythmia I want to show you in this section is this, and I think this strikes fear in the hearts of men and women on the telemetry unit. It's ventricular fibrillation. It's ventricular fibrillation because it's polymorphic and it's at a very rapid rate. You can see over here, clearly rates faster than 300 beats per minute. And here, it's almost like the QRS complexes seem to disappear. Where's the QRS? It's almost just like noise here. So that's pretty characteristic of ventricular fibrillation as well. So it's polymorphic, is generally greater than 300 beats per minute. And this is something that's nearly always fatal, but on occasion it will stop on its own. So don't let people fool you into thinking that once you're in ventricular fibrillation, there's no hope. And with that, I hope that I've shown you how to recognize almost all of the more common arrhythmias that we see on rhythm strips. And that was really the purpose of this basic level, is to deal with arrhythmias that you'll see on a rhythm strip and to introduce a lot of subjects that you need to be familiar with if you're going to read 12-lead ECGs. The intermediate level of this course will cover all the nuances of reading 12-lead ECGs, including subjects like hypertrophy, atrial abnormalities, and STT wave abnormalities, so you can look for things like ischemia and acute infarctions. What the advanced course gives you is additional insight into the more complex arrhythmias like PSVT and how to recognize the presence of a concealed accessory pathway versus AV nodal reentry tachycardia, and other complex subjects like recognizing which side of the heart an atrial flutter is coming from, and even how to localize where ventricular tachycardias are arising from. The advanced course is going to be filled with great stuff. So if you're interested in becoming an ECG expert, then that's the level that you should shoot for. In the meanwhile, I'm glad you subscribed to this basic level, and I hope I was able to present this information in an interesting and understandable way. Well, this is Dr. Nick Tulo. Thank you very much for subscribing and supporting the Ecg Academy. With your subscriptions, I hope to bring you more and more information and help you master the electrocardiogram. Thank you all for your support. Hi, this is Dr. Nick with the Ecg Academy, and this tutorial is an essential one. It's dealing with assessing wide QRS tachycardias. Now, this is one of the most common problems that people face on a cardiac unit. Looking at a wide QRS tachycardia and trying to figure out, is it non-sustained ventricular tachycardia, or is it some kind of atrial arrhythmia with aberrancy? So we're going to discuss all these points that you should be using when you're assessing whether this is atrial or ventricular. You have to look for changes in the QRS morphology, examine how did it start, and whether there's a P wave that initiates the arrhythmia, or whether you can look for fusion beats at the beginning. Decide how premature was the first beat, and can you explain aberrant conduction, because functional aberrancy only occurs with rapid or premature beats. I'll show you how to look for AV dissociation, and you have to look at the big picture. What context did it occur in? Was there AFib underlying? And does the arrhythmia fit this aberrant phenomenon known as Ashman's? So let's quickly review what happens during the cardiac cycle. Of course, the sinus node fires and gives rise to a P wave. The signal gets into the AV node, is delayed for a split second and then normally would go down both bundle branches simultaneously, giving us a nice narrow QRS complex and a T wave with repolarization of the ventricles. But you have to recall from my lesson in IVCDs that one bundle branch may have a longer refractory period than the other bundle branch, and if one bundle branch or part of the conduction system recovers sooner than the other, well then if the AV node lets a signal down right at this moment when the green conduction system has not recovered, then that part of the conduction system will not be able to depolarize and will block. But the part that's drawn in purple has recovered and would be able to fire, but the green will just not get a response. And so what happens is with a premature or rapid beat, one of the bundled branches may block, but the other will be able to conduct the signal, and you'll wind up with a wide QRS because of slow intramyocardial pathways that have to make their way around the rest of the heart. So this idea of functional aberrancy is very important, and that's generally why the QRS gets wide. But the point is the QRS complex changes when you have some kind of aberrant conduction, and it also changes if the beat arises from the ventricle. If you have a focus down here that starts firing, the signal may get to one side of the heart very quickly, but then have to travel through slow intramyocardial pathways to get to the other side. And that's why ventricular arrhythmias are usually associated with a very wide QRS complex. But what if it arises from somewhere in the septum? Then it may engage part of the conduction system, and so you can't rely on the QRS width. In other words, ventricular tachycardia doesn't always look this way. It may be just a little wider than the normal conduction system. And that's why people who rely on just the appearance, when they examine a strip and they say to themselves, well, gee, it looks like VTach, that is a prescription for the wrong answer. So don't rely on wide, really bizarre-looking QRS complexes. I'll show you examples of when it doesn't look that wide, just a little different. So let's take a look at some examples and try to come up with an organized way to approach it. So here's the first example. And what you see are a couple of normal sinus beats here in the beginning. And then you have this tachycardia at a rate of about 160 beats per minute, and it's a little bit irregular, but the QRS complexes clearly look different than the underlying QRS complexes, right? But it is irregular, and it did start kind of late. Look at that. It started so late that, in fact, you can see a P wave in front of it. Look at that. There's a P wave. Here's a P wave. And this P wave occurs on time. It's a P wave that's on time, but look at the PR interval. Look at this compared with this PR interval. It's much shorter than the underlying PR interval. And the QRS is clearly different. Now that PR is so short that this P wave could not have possibly gotten through the AV node. Remember, the AV node delays the signal, right? Why would the AV node suddenly not delay the signal? How could this P wave suddenly get to the ventricles early? Well, the answer is it didn't. That this first beat had to come from somewhere other than this P wave. That means it's ventricular. And of course, they all look alike, so they all must be ventricular. Nevertheless, the person on the unit marked this as 3-second run of AFib, which brings in mind Tulow's law. Don't ever believe anything you read on a rhythm strip unless you wrote it yourself. So this is not AFib, it's non-sustained ventricular tachycardia, purely because of the way it started. First of all, why would this first QRS be aberrant? It wasn't very early. You cannot say that this is a functional bundle branch block because it didn't come early. So that doesn't support this being aberrancy. And the most important thing is, of course, this first QRS did not come from the P wave, so it came from the ventricles. The other thing that you can see, look at this ST segment, and then look at this ST segment. What you see there is a dissociated P wave. There's a P, and in fact you can see a really tall tip on this T wave compared with this one. So those are dissociated P waves because you have some degree of retrograde conduction from the ventricle back up to the atrium. So this has all the hallmarks of ventricular tachycardia, despite the fact that it is a little bit irregular and the QRS is not that wide. So don't use width or irregularity to decide whether something's atrial or ventricular. Here's the next example. Here you have 3 simultaneous leads, and you have 2 wide QRS beats and then a narrow one. So the question is, are these atrial or ventricular? And what you need to do, first of all, is say to yourself, well, okay, this did come early, so it could be aberrant. So let's see, how did it start? Where are you going to look for the P waves? Well, you're going to look for the P wave in front of this QRS complex. But generally, when you have a premature beat, you've got a T wave. And so therefore, you have to look for a P wave superimposed on a T. And the way you do that is to compare the T waves of the last couple of beats. Look at how nice and smooth those are. And now look at that T wave is distinctly different. Look at that tall peak on this. And you can see again here, this is a nice smooth T wave, whereas this one has a sharp spike on it. It's like Mount Everest over here. So this is the premature atrial contraction that conducted with a fairly long PR interval here. Why? Because it was early. Premature, right? It was early, and so it landed at a point when the bundle branches had not recovered, and you have functional aberrancy. You have a bundle branch block, and somewhere in here you can find a second P wave that gives rise to the second QRS complex, which looks very similar. So they're both aberrant, but then there's another P wave here that manages to get down both bundles at the same time, and so the third QRS is narrow. But what you have here is an atrial triplet. It's atrial, because you can see it started with a P wave, had a little bit of first degree AV block, and then you have this functional aberrancy that made the QRS wide. Remember, T waves have a very slow change in voltage, very low frequency signals within that T wave, but P waves generally tend to be sharp and spiky with a higher rate of voltage change, higher frequency components. And so when you see a T wave with a bump on it, or if you see a T wave with a bite taken out of it, that's usually indicating that there's a P wave superimposed on the T. And that's really key because most people don't look for P waves when they're assessing this wide QRS tachycardia. The rest of this discussion will be on part 2 of assessing wide QRS tachycardias. Hi, this is Dr. Nick with the Ecg Academy, and this is part 2 of assessing wide QRS tachycardias. So here's the next example. And this again came from a Holter monitor, so you have 3 simultaneous leads. And so you've got 3 sinus beats in the front. And then here it looks like a sinus beat. And then you have this wide complex tachycardia. So it's very rapid, and the first beat came early, so it could be aberrant. But now let's look for a P wave. Did it start with a P? Examine the preceding 2 T waves very carefully, and then look at the T wave before the wide complex tachycardia. Well, in this case, the T waves look the same. I don't really see that this T wave looks any different than the 3 preceding T waves. And so right now I have no evidence that this started with a P, making this, of course, more likely ventricular. So if you think it's ventricular, then you should start to look for the hallmark of ventricular tachycardia, and that's AV dissociation. If you see AV dissociation, then you know for sure it's ventricular. Where do you see AV dissociation? You're looking for P waves somewhere in the middle of this whole mess. Well, it's hard to see a P wave when the QRS is going. So you look at the ST segments and the T waves, and you look to see variations from one beat to the next, and there it is. Right there, there's a P wave that's dissociated. You see it, it's in all 3 leads, and it's present there, but it's not present anywhere else. You say, well, are you sure that's a P wave? Am I convinced? Well, I'll show you the next strip. This was a continuation of the same arrhythmia. And so a few seconds later, now when we examine the ST segments, we can see very clear evidence of AV dissociation, because the P is not there, but it is there. And it's gone, and it's back again, and it's gone, and it's back again. So what you see now is likely 2-to-1 retrograde conduction, and then it begins to break down. Now you don't see any P's, but then here it is back again, and when the arrhythmia finally stops, you see the patient's back in sinus rhythm. But those dissociated P waves are absolute 100% proof that you're dealing with ventricular tachycardia. Now, sometimes you'll find a wide complex tachycardia in the middle of atrial fibrillation, and that's where we talk about the context. When does it occur, and how can we tell if we have just aberrantly conducting AFib versus VT? Well, here you have to kind of look at the rate of the underlying rhythm, whether the QRS morphology changes, and you also have to look for this Ashman's phenomenon, which is a long-short, which has to do with the fact that the action potential duration and the QT interval is going to change from beat to beat depending upon the rate. Then if you have a very slow interval, the QT will be longer. That's why we correct the QT interval. And if you have a very short interval or a very rapid rate, the QT shortens. Well, the QT is a reflection of the action potential duration in the myocardium, and with long R to R intervals, you get more heterogeneity So those bundles depolarize at different times. And so when you have a long R to R interval, the bundles may depolarize so differently that if another beat comes down, it's going to encounter refractoriness in one bundle and not the other. So when you have a long interval, it sets up heterogeneous refractoriness of this beat. And then if the AV node manages to send a beat down the bundle branches very soon after, so you have a short interval preceded by a long interval, then this beat conducts with a bundle branch block. And this is Ashman's phenomenon. Now, let's look at this strip and decide what's happening. We can see the QRSs over here, but there are no P waves in front of the QRSs, and you see a little bit of jiggle to the baseline, and it's irregular. So we have a fib as an underlying rhythm. And the average rate here is maybe 60 beats per minute. Well, suddenly you have this wide complex beat at just about 150 beats per minute. And you have a short interval, so it was quite premature. But the interval preceding it wasn't that long. And the fact is that you have a marked increase in the heart rate. Now, here's how you have to approach this. During atrial fibrillation, what determines the heart rate? The AV node does. Now, the AV node from 1 second to another behaves in a fairly consistent manner. Now, it's subject to autonomic nervous system changes, and over the course of several seconds, you can see changes in heart rate. But from 1 second to the next, you don't really get marked changes in AV conduction. So tell me, why should the AV node be conducting at 60 beats per minute over here, and then suddenly start conducting at 150 beats per minute, and then suddenly start conducting back at 60 again? You see, in the context of this atrial fibrillation, and in the context of this slow heart rate, this sudden increase in heart rate and widening of the QRS tells you it has to be ventricular. It's not Ashman's, because you don't have this characteristic long-short interval, and the fact that the rate was so much faster tells you in your head that this has to be ventricular because of the way the AV node behaves, and it wouldn't behave this way. You can predict what the AV node is going to do from 1 second to the next, and it just won't do this. So this has to be ventricular. On the other hand, here's 2 examples of Ashman's phenomenon. In the top example, this is a patient with atrial fibrillation. We can see the fibrillatory activity underlying, and of course there's this irregular rhythm that's going on with an average rate here of maybe 100 beats per minute. And then you have a bit of a pause just because the AV node decided to slow down a little bit, and this beat right here occurs very soon after the pause, so you have long short. And this is a typical example of an Ashman beat. It's wide, but it's not terribly wide. It's premature, but it was preceded by a pause. Now sometimes you can get single Ashman beats like this, but sometimes what happens is the first beat may come down and find a refractory right bundle, and so that beat can go down the left side and travel through the septum to the right side. But what can then happen is that signal can enter the right side of the conduction system and then go backwards up the right bundle. In the EP vernacular, we say that you have linking across the septum and retrograde penetration into the right bundle branch. Well, now the next beat comes down, and because the right bundle branch was activated retrogradely, when that beat comes down, the right bundle branch is refractory again, and so it blocks again. And the signal goes down the left and comes around to the right side, and again is able to retrogradely penetrate the right bundle branch. So you see, there's this repeating phenomenon where you have persistence of this refractory period in the right bundle branch that allows salvos of wide complex beats like the one in the strip below. See, what you have here is atrial fibrillation, and you have a long and then a short, which makes us think that this first beat is an Ashman beat. But what about the second beat? It doesn't fulfill this long-short pattern, but it's still an Ashman beat because of this principle of retrograde penetration of the bundle that's blocked, and you get repeated beats that are all aberrantly conducted. And then what happens when the AV node finally takes a rest and you have a little bit of a pause? Well, that's the pause that refreshes. And so the next beat can come down and find both bundles willing to conduct the signal, and the bundle branch block resolves. You may have to listen to that explanation a couple of times because that belongs in the advanced course, but I want you guys to understand why aberrant conduction can occur in salvos like this. Okay, so now this is your final exam. We're going to decide what this is. Is it atrial or ventricular? So you look at the forest first. You see there's 3 normal beats in the beginning, and then you have this wide complex tachycardia. It's not terribly wide. It is rather irregular. And of course, whoever wrote this on the strip called it a fib. Are they right or wrong? Well, it could be some kind of aberrantly conducted atrial arrhythmia because the first beat did occur early, and so maybe this first beat conducted aberrantly because the bundle branches were refractory. But prove it to me. Well, the proof is in how it started. That's when you absolutely have to look at the T waves of the preceding beats and see a nice long smooth ST segment and a nice smooth T wave. And now look at this one and compare it. Is it the same? Well, no, it's not. Look carefully. There's a nice long ST segment here, long ST segment. This ST is shortened. This T wave takes off at a funny angle compared with this T wave, which kind of has a very sharp upstroke. And this just looks bumpy to me. And so I'm convinced that there is a P wave here, and that started this tachycardia. And so if a P wave started it and it's premature, that would explain aberrant conduction. And so in this case, I would agree that this is an atrial arrhythmia with aberrancy, perhaps not atrial fibrillation, maybe atrial tachycardia. But I would not diagnose ventricular tachycardia in this case. And so to summarize, when you're trying to assess non-sustained VT versus atrial arrhythmias with aberrancy, you have to make sure that the QRS morphology changes to a significant degree, but don't rely on regularity or the width of the QRS necessarily, because you can get narrow complex ventricular arrhythmias that don't look like ventricular tachycardia. Always look to see how it started. Was there a P wave in front of it? And don't be fooled by fusion, which gives you a short PR, meaning that the P wave could not have conducted to the wide QRS complex, and so therefore must have come from the ventricles. Make sure the first beat was premature if you're going to diagnose aberrancy, because aberrancy doesn't occur when the first beat of the tachycardia starts very late. Always look for AV dissociation, since that's the hallmark for ventricular tachycardia. And in the context of atrial fibrillation, look for evidence of Ashman's phenomenon and understand why you can get single Ashman beats or salvos of aberrant conduction. Finally, keep in mind that during atrial fibrillation, the AV node conduction tends to be consistent, so sudden increases in heart rate are more likely to be ventricular. So I hope that was helpful, and this is probably one of the most difficult clinical problems that we face in electrocardiography. But keep watching my chalk talks, because I do show a lot of these wide complex tachycardias, and you can get more practice learning how to approach these more difficult strips. And so for the ECG Academy, this is Dr. Nick. Thanks for watching.